some time. I'll just need to make the presentation ready. I'll just share the screen after some time. It is 9:55. Now we have 5 more minutes to go. Deepak, so please make Evan Fernandez from the OpenFOAM team as co-host as well. Evan Fernandez and John Pinto and Manjil Situla. They all will present. And yeah, and Professor Chandan Bose will also join after lunch. So he also, when he joins, you can make him the co-host as well. Let me ask you all, have you ever tried OpenFOAM before? If yes, you can write yes. If no, you can write no. So, I mean, is it the first time that you are going to learn OpenFOAM, or have you tried learning OpenFOAM, but it was not very convenient? Okay. Okay. Yes from Abdul. No from, okay. First time. Okay. Good. Good. So whoever is starting for the first time or whoever is not studying for the first time, both of you will be finding this workshop very useful. It's a very brief workshop, only 1 day. Only 1 day is very less to, make you, I mean, it is effective to give you a start. The 1 day workshop is only useful to let you know how to start learning OpenFOAM. So we will just have the session today. I'll show you, I'll share the screen where we have the schedule for today. Okay, fine. Shikha, Pratibha, Jaswant, Atidev, Gautam, Ramisha. Okay, thank you for all your answers. Okay, I can see many more participants have joined. We are expecting more. So it's 9:59, almost 9, accurately 10 now. So let us wait for a few more minutes. And then we'll start the presentation and then the actual workshop. So I welcome all the participants who have just joined just now. I was interacting with the people who joined around 9:50. Could you please give us a brief introduction about how session schedule will go today? Okay, I'll just share the schedule after my presentation, and then you can see the screen. So we will start with a talk of Professor Janani Sri Muralidharan from IIT Bombay. She's a faculty in the Mechanical Engineering Department of IIT Bombay. And then we will start with the actual hands-on session, the demonstration session. The hands-on session will be taken care by the OpenFOAM team of IIT Bombay of FOSSEE. And then in the second half, we will have Professor Chandan Bose. We will have a session of Professor Chandan Bose, and then the hands-on session, we will go ahead. And then we will also show you the GUI, the graphical user interface that is developed by the FOSSEE team of IIT Bombay to support OpenFOAM. So we will have a session on that as well. And then we will conclude around 5 p.m. So this is the program for the whole day. Okay, thank you, Subhash. So I can see the participant count is steadily going up. I just want to wait for 2-3 more minutes and then we will start.
So, Payal, this is Janani here. Could I ask them a couple of more questions while we are
Yes,
waiting?
yes, sure, ma'am. Please go ahead, please.
Thank you, thank you. So, hello everyone. I am Professor Janani from IIT Bombay, from the Mechanical Engineering Department. So, before we get started with the day, to help us better understand how to help you out, want to know if you could tell me which year you belong to, second year, third year, fourth year. If you could just say what part of which year you guys are, that will help us. You can type into your chat window. Oh, okay, PhD, first year MTech, fantastic. Second year, fourth, okay. Okay, great. Happy to see a lot of PG students here. MTech, third year, okay. BTech second year, that's great. Actually, you're starting early out, and I think that's great. Okay. Great, fantastic, fantastic. So the other next question that I have is, have any of you undergone a proper technical CFD course? CFD meaning computational fluid dynamic course. This could either be like a coding course or whatever. Have you undergone a CFD technical course? Yes, one. Okay. Fantastic. Yes. Okay. All right. Oh, great. So then I can get your help in trying to do my lecture today. I can ask a few questions. Okay, great console. Okay. Good, good. That's quite helpful. I think Payal, we can begin. I think I've got my answers. So if you want to start, that's fine.
Yes, ma'am, let us begin now. 73 participants now. Okay, so welcome one and all, and a very good morning from IIT Bombay. So let me just present my screen and start the presentation. Second, I need to move this panel. Please allow me some time. Let me just stop the screen sharing and try it. Is my screen visible?
Yes.
Yes, it's visible.
Yeah, I have done just full screen. It's loading. Okay. So I am Payal Mukherjee. I'm working as a project manager at the FOSSEE project, which is being developed at IIT Bombay. This project is funded by the Ministry of Education, Government of India. And Professor Kannan Modgali is our team lead, we can say. He is our principal investigator. Okay. So let me just mention that though FOSSEE is a project from IIT Bombay and it is being developed at IIT Bombay, but it is not limited to IIT Bombay or IITs or NITs. Okay, it is for all the Indians because it is an initiative from the Government of India, and we are working for the National Mission on Education through ICT. So FOSSEE actually presents you a training program that each and every Indian student has the right to, take the opportunity. Okay, so let me talk about the FOSSEE project now. FOSSEE stands for Free and Open Source Software for Education. Okay, so and earlier it was only for the engineering education, but now it is offered this training is including GIS, chemistry, physics, hardcore, statistics, okay, and so on. And this free and libre open source software, the word free is not just limited to free of cost. So this has 4 aspects. Number one, you can freely download and install the software in your own systems. You need not pay for the licenses because they come with the licenses, for example, GPL and BSD, which you can use legally. Okay, and you need not pay a single rupee fee to access the license and to use the software. So installation is free. You can also modify the software. That is the second aspect of freedom. You can distribute the software for free. That is the third aspect of freedom. And the fourth aspect is you can distribute the modified version of the software for free. Okay, so this free and libre open source software stands for all these 4 components. Okay, so that is FLOSS or FOSS that we say. And as I mentioned, that it is funded by the Ministry of Education, Government of India. And the main purpose of this FOSSEE project is to reach out to every corner of India where the facility of teaching and educational institutes are not as far as they are in the cities. And due to some hindrances, for example, financial hindrances, for example, distance hindrances, all the students or all the Indian students are not, they cannot have the facility of getting admission in top-notch institutes of India. And that is where FOSSEE is useful. Okay, so FOSSEE's main function is training the students so that they are empowered to use the training to produce an output in the form of a practical project, which will help them to secure good jobs and also apply in higher education in India and abroad. Okay, so this training part is very important because we emphasize on skill-based education. Okay, it is in most of the colleges and education institutes, they are doing both the theoretical aspect of education as well as the hands-on part. Okay, but FOSSEE is focusing more on the skill-based education. Okay, so let me proceed with the next slide. So along with OpenFOAM, FOSSEE is offering training on all these softwares. Scilab, Python, Scilab is a alternative for a very famous software called MATLAB. You have heard of MATLAB. Python is actually, it's a free and open source software, but it is widely used. Okay, in my next slides, I'll just show you a chart which displays the commercial as well commercial software and the free and open source software, which is the substitute for that commercial software. eSIM for electronics, DWSIM and OpenModelica for chemical engineering, GIS or FOSSEE GIS or QGIS is a open source software for GIS mapping. R is for statistical analysis. OSDAG is for steel industry. Focal is for animation. Floss, Arduino, and OpenPLC, they are all open source hardware support from FOSSEE. Okay, SOL is for school students, basically. Okay, so you can, in this chart, you can just see the commercial software alternative to the open source software that we train. Okay, like MATLAB for Scilab and OpenFOAM for ANSYS Fluent, which is a very famous software used widely by the CFD users. Okay. DWSIM for Aspen Plus is also very renowned software. GIS for ArcGIS. So all these things are there. Okay, now let me discuss about how can the students participate in FOSSEE free of cost, and this participation will you will help earn you some money also. So we for all the case study projects, research migration projects, all the successful submissions, FOSSEE will pay you honorarium, as well as you will receive a certificate from FOSSEE. And the third and the most important point is your name, your work, and your affiliation. Everything will be displayed on the FOSSEE website. And this FOSSEE website is regularly, reviewed by the ministry people. So it is a very prestigious website that you can have your name at. Okay. So and this the repository where your name and work will be displayed is accessible throughout your life. Okay, so whenever you are applying for higher education, whenever you are applying for a job, you can always refer to your work because it will be always there in the FOSSEE website. So let me just briefly explain you. So all these are the projects or the output that I was talking about. So most of the training methods or training institutes will give you a training. They'll just make you sit for an exam, maybe a multiple choice question or something, and they'll give you a certificate. But here is the point where FOSSEE is apart. FOSSEE stands apart from those kind of training programs because FOSSEE will enable you, will empower you to use this knowledge to actually apply in your own subject and produce a case study, produce a research migration project, or contribute in a lab migration project. So in the OpenFOAM stream of FOSSEE, we mainly focus on these three outputs: case study, research migration, and lab migration. Okay. So cases are simple problems in CFD, which any learner from the CFD community or any user of the CFD community of OpenFOAM can use OpenFOAM and solve a problem in CFD. What is case study? This is about the case study project. Now let me come to the research migration project. So in the research migration project, what happens? The learners can refer to any research topic which is published in a renowned journal. That learner will have to take or refer the research topic and replicate it using OpenFOAM. Okay, this is majorly used by the research scholars. And the lab migration project is mainly for the institutes, the lab of the institutes which are using commercial software. We handhold them and we help them to migrate to a lab which will use a free and open source software and not a commercial software. ANSYS Fluent that is used by the CFD users, they come with a very, very heavy license fees, lakhs of rupees. And for every module, you have to buy a new license, and that is where the knowledge of FOSS, free and open source software, for example, OpenFOAM, will help you. How? Because it will give you a freedom. It will make you will be Atmanirbhar, and that is the key word now to make India a more developed country, to make you as a CFD professional or as a student independent. Okay, so because suppose your educational institute or the company where you are working in, they have bought a license because they have funding. But what if you want to go ahead with your own company? What if you want to apply the knowledge of CFD and OpenFOAM to make your own project? Then the knowledge of OpenFOAM or the open source software will come. Because this access of commercial software, it is just a kind of, dependence on finance. If you have that money, if you have that finance, you can access it. But what if you don't have that financial capability to buy the software? Then the knowledge of extremely important. So it is very, very important to learn FOSS or to have this knowledge so that at any point of time, at any point of life, you can use it as per requirement. Okay, now let me just mention about the semester-long internship and summer fellowship of that FOSSEE offers. The semester-long internship is it actually begins with the semester in the month of January, February, and it's a 3 months long course that is offered by FOSSEE. Okay, and it is a completely online program. So semester-long internship has already been started by FOSSEE, and very recently FOSSEE has announced the summer fellowship. So I will request after this workshop, please, I'll towards the end of the workshop, I will come to how to apply to summer fellowship of FOSSEE. So please apply for summer fellowship and try. So the selection criteria is only, this the screening task that we float, and we will not look at your report cards, your, performances, your earlier performances. The only criteria is the knowledge of the FOSS that you will apply through the screening task. Okay, so for all the faculty members, let me just share this screen because we have a program for the faculty members and they can collaborate with us as faculty partners. The main role is guiding the FOSSEE interns and fellows and whoever is wanting to learn OpenFOAM and come up with a case study. So the faculty partners actually handhold them. Okay, and they are actually replicating the work that the faculty members at IIT Bombay are doing for FOSSEE. And they are our esteemed faculty partners, and benefits are their name will also be reflected in the FOSSEE URL. After the internship and fellowship, they can continue the work with the FOSSEE interns and fellows to publish papers in renowned journals. And they can also have the opportunity to collaborate with the present group of faculty partners and also the industry partners that we have with us. Okay, they are called advisory board members of FOSSEE. For the industry people, you can join us as advisory board members. Your role will be to guide the FOSSEE interns as well. Okay, and the benefits that you are getting is you are getting pre-trained candidates for recruitment. For example, you can float a toy problem or a replica problem that you are working on at present in your company. So we are not saying that you have to tell us the exact data you are using or the exact project that you are working on. You can just replicate those processes and you can prepare a toy problem that you can float for the internship and fellowships of FOSSEE or also throughout the year, this opportunity is open. And you can also, collaborate with the faculty partners and other advisory board members. So towards the end of the workshop, I'll show you the URL and I'll introduce you to some of the faculty partners and the advisory board members virtually. Okay, so with this, my next slide will continue to show you the schedule for today's workshop. So just after, we are 5 minutes late. So 10:15, I'll stop. It is 10:20, so I'll stop now. And Professor Janani Sri Muralidharan will take over for the first session. And then we will have the demonstration or the hands-on session. And we'll continue with the afternoon slot. And you can see the schedule here. We'll continue with Mr. Manjil's session, Avan's session, and Deeptanshu's session. And at the last, towards the end of the workshop, we'll have 1 hour session by Professor Chandan Bose. He will join from the University of Birmingham. He's a principal investigator of the OpenFOAM team of FOSSEE now. So I'll just stop sharing my screen and I'll request Professor Janani to take over and begin your talk, ma'am. Thank you. Over to you.
Thank you, Payal. Thank you for that introduction. So we can, I think today begin. Payal has set the correct tone that it is a very empowering software that you are learning today. Some of you don't know CFD, some of you know some part of OpenFOAM. So it's a very mixed crowd. But right now we are going to view you all as same. And you can see that from each of your at your own pace, you can quickly learn the software. Okay, it's not too difficult. But one important point I would like to emphasize is attention to detail. So that becomes very, very important when you're trying to learn OpenFOAM, trying to understand CFD's application and how you can use OpenFOAM to enable yourself, either whether it be starting a company, starting a new job. Nowadays, companies like GE are all moving towards, of course, they use some part of their work to be commercial software based, but there is initiative to move towards OpenFOAM. And the applications in industry are not easy. So very quickly, the industries want people with a good grip and understanding. It is not like you've done the tutorials of OpenFOAM, and that brings you to a point, but you should also understand it. Now, why am I saying all this? In today's workshop, all of this today, you will have to, I expect you to ask questions, to have complete focus in what is being shown to you, because you have experts, the OpenFOAM team in front of you at your full disposal, if I have to say that. So I want you to fully utilize this opportunity to express your questions. And, the focus has to be learning OpenFOAM, learning CFD. Okay. So with that, let us quickly jump into today's first session. I'm not going to show you OpenFOAM, but my job here is to first bring everyone onto the same plane of very quickly understanding what CFD is. Okay. And I do understand that a few people have already gone through a CFD course. So I will seek your help in trying to fill the gaps. Okay. So let me share my screen first. We can probably quickly, in about, I think I have about 40 minutes. So let's get started. CFD. Okay. So things are written in front of you, but I would like people to, you can unmute yourself and answer, right? I don't want to look at the chat windows. So CFD means computational fluid dynamics. Okay. So the question is, I'm going to solve a set of equations, right? So does anyone know what are those set of equations? You can talk and interact out loud. The common set of equations that I will probably use for a CFD problem, a fluid dynamics problem.
Continuity, momentum, energy equations.
Okay, all right. Anybody else?
Navier-Stokes equations.
So Navier-Stokes equations. Okay. Anyone else?
Like if there is heat transfer is also involved, like some heating plate is there, so we'll be solving energy equation also.
Absolutely. There is a choice. If it is a heat transfer problem, you would take an energy equation, otherwise you will not. I think there are versions of compressible and incompressible equations as well. Yeah. Anyone, any other inputs you guys can give me?
Like it could be multi-physics problem also, like some apart
okay.
from fluid flow, there is like electrical, like say if there is ionic fluid is flowing, so that will consider electrical equations to be solved, like Poisson equation maybe.
Right. So essentially, what you're saying is, I have fluid flow, but maybe I have something else happening other than that. Maybe magnetohydrodynamics, because you're trying to find out how you can probably move a particle using magnetic force. So you have to solve an additional equation. But everyone is right. So there is this standard set of equations, which is conservation of mass, conservation of momentum, and maybe in some cases, conservation of energy. I think that is the fundamental laws we're looking at. And when we're trying to solve equations, we have to satisfy that. Okay, so maybe conservation of momentum is something we will take. And well, I know this very famous equation called F is equal to ma, correct? So mass into acceleration. And typically that's from your Newton's law, correct? But I do know that the Newton's law applies to, say, an apple, right? So mass times the acceleration. So typically in proper technical terms, this apple is called a system, right? So it is mass times acceleration of this system, okay? Now the problem is when I'm talking about fluid dynamics, right? Now I have to apply this conservation law, conservation of momentum to a fluid, and fluid keeps flowing about here and there. Now, how do I look at every particle in the fluid, or do I look at, take a bucket and carry it around? Or what do I do? Any thoughts on that?
We define a system to manage the entire system. So, behavior to the system.
You will have to be louder, Prithul. I couldn't hear you very clearly.
Sorry, ma'am.
Like we can change our approach from here. Like if as you mentioned, if there is apple which is like moving around, so in place of that we have fluid with millions of particles. So
Mm-hmm.
instead of considering a particular particle, we can consider a domain.
Mm-hmm.
So from there different forces, and maybe we can define the acceleration term of there only
Okay.
by
Okay.
as you mentioned in the Reynolds transport theorem.
Okay. So see, so to put this question in perspective, now either I have an option of tagging a bunch of particles and traveling with the particles. So I'm tracking in a way the particles, which is largely the Lagrangian frame of reference, which is kind of written on the screen for you. And the other part of it is called the Eulerian. Now, what does the Eulerian do? It says that, listen, for complex problems, I am not going to be following along the particles. What I'll do is I'll stand at a point and I will create a window in front of me. Okay. And I will see this particle or this, what happens to a bunch of particles as it enters my window and it moves out. Right. So my focus is going to be this small volume space in front of my eyes. And that is called the control volume. Okay, so the whole procedure is to look at several such control volumes at different points in space and come up with an understanding of what is happening to the flow. And that's called the Eulerian approach or the control volume approach. Okay, so the question lies, okay, I know that there are these systemic laws, F is equal to ma, where it's a solid apple which is moving around. And I now have a fluid where I say, okay, either I travel with the fluid or I create a control volume, like a window in front of me. And a large set of problems are in this control volume approach. So we'll be talking about the control volume largely in this case. So when I have the control volume, now my question is, okay, fluid is coming in and moving out, but how do I apply an F is equal to ma to this control volume? I don't know how I'm going to do that, right? So that's where you have something called the Reynolds transport theorem, where Reynolds proposed how to change this systemic law of conservation to, a conservation within a control volume. Okay, how do I define fluid is coming in and going out? How do I talk about conservation, right? So that's happening through the Reynolds transport theorem. Okay, so the first line here is the Reynolds transport theorem. Okay, anyone want to venture out what these two terms mean on the right hand side?
Like it's a conservation across the, like for the first term it is the some quantity n which is coming inside, like which is changing inside the control first term in the middle, which is like how that property is changing with time over the control volume, and this last term is like by what flux the quantity is like either coming like net transaction of the quantity with the control volume.
Okay, good, good. Anyone else wants to venture and say something? Okay, that's fine. So essentially what we're saying here is in a control volume, I mean, it looks all scary math, but it's not, right? So there is this control volume, okay, and I'm looking at it. So all that I'm saying is, listen, I'm going to have to try and see the change that is happening in this control volume. That's all that I have to do. Now, this change in this control volume equals to, if I have like some kind of, imagine I have a smoke generator within this control volume, and there is also smoke in and around, okay, and fan is blowing in. So within the control volume, because there is a smoke generator, smoke is going to get generated. So I'm saying change in this property called N over time within the control volume, CB, right? So I'm just integrating, saying over the entire control volume for a time, how much change. So something gets generated over time, there is a change. Plus, that change will also include if some external smoke comes in and goes out, correct? So the net amount of, if I have 100 as a number at a time, that 100 could be a sum of what gets generated per unit time inside plus what comes in and goes out. If 20 comes in and 30 goes out, right, there is some amount of generation. Net amount will be some summation of this, right? So that's what this equation says. This equation says that an overall change in a system, okay, N is that quantity, is equal to whatever is changing in the control volume plus whatever comes in and goes out. Okay, so this matches what the system means to a control volume. Okay, now if I apply it to what were the conservation equations we learned, we said conservation of mass, conservation of momentum, and also conservation of energy at a later point, right? So similarly, Reynolds transport theorem essentially talks about converting. So the left-hand side, I've just written the conservation equation and the momentum equation like you would know in a normal Navier-Stokes case, like this, okay? So basically, system on the left-hand side, system rule is no net mass generation. Of course, not phase change, normal cases, no net mass generation. So that is equal to what changes in the control volume and then what goes in and comes out. Okay. And you also have the momentum case, which is the force. F is equal to ma. So F is equal to two forces, body force, which is your like your gravity force or something like that, and your surface forces, right? So F is here is equal to ma, okay? Mass times acceleration, okay? Or change in momentum. That's what you see here. Okay. So very quickly, what did we talk about? There is always systemic laws of conservation. That conservation is actually converted to your mass, momentum, and energy conservation equations of Navier-Stokes. Why? Because this system law will not apply for a fluid. So they converted that for some fluid that is flowing through a control volume, and you get this structure. Okay. All right. So the next step we have is fine. This is, all erudite PD equations. But how do I do CFD with it, correct? So for CFD, always you will have to have a good coding practice. Let me just say that, right? So a good coding practice, if you write a normal Python code or something, and I say, if I is equal to 1 to 100, do this. If I is equal to 101 to 500, do the next step, correct? Now, does it make sense if I say I is equal to 1, do this, like 1 plus A plus B is this, and then I is equal to 2, same A plus B is this? That's not code, right? You put it in the loop because then let it go figure out and do the loop itself. You won't be writing that in a repeated step, correct? Same way, we have to recognize patterns in mathematical equations to see if you can easily solve it through a loop or through a structure. So forgetting the fact of these are representations of physics, correct? We talked about, what did we say? This is your momentum change is equal to summation of fluxes, summation of forces, right? That was a momentum equation. That's the physics. But now let's look at it mathematically, because I have to now break it down into common patterns, right? So that's why I'm talking about governing equations from a mathematical perspective. Numerical we'll come to later. The mathematical perspective may ignore the first equation, okay? Because that is like a control condition. Okay, am I going 10 steps forward and there is one stop line? Okay, have I reached the stop line? No, I have not. So move again. So that's like a control statement. So mass, is my mass 0? Is my mass balance done? Otherwise, go solve again. So this is like a control problem. But the main equation is, say, your momentum equation, and in some cases, the energy equation, correct? So do you see patterns in the equation? Any one of you? It's momentum and energy, two different things. Do you see a pattern in the equation?
Yes, ma'am. Like
Momentum
every
and energy,
equation
or
has
is
a
it just a
temporal term.
momentum equation?
Yes, Smriti. Can you be louder? I want to hear you really loud. Smriti.
I'm sorry, ma'am. So both the momentum and energy equation, it has a temporal term, like where it's changed with time. That is the first term.
Hmm.
And then the second term, I think is the advection term, like how the flux, like mass flux changes.
Okay.
On the right hand side, momentum equation has like various forces like pressure force and gravity force, which doesn't exist in energy.
Huh.
But the diffusion term, like the grad square V and grad square T.
Okay.
that
Okay.
is-
Okay. Good. Asma, do you have anything to add to this?
Yeah, it's the same thing. It's kind of like, the parameter, the velocity, with respect to momentum, the velocity has been considered over there, while we have the same pattern with respect to the temperature in the energy equation. We have the same gradients and the derivative over there. On the right side of the energy equation, we do not have as many forces as we can see in the momentum equation. That's what I would like to say.
Okay. So see, I think you've got the pattern. So firstly, before going into what is advection and diffusion, the first one, of course, is a temporal term. Okay. Second one has a mathematical operator called divergence, V dot del, right? And of course, these are pressure forces. We can neglect that for the time being. And then you have something called the Laplacian term. Okay. So essentially, you can see that there is a lot of common main math properties. And one would think, why, right? So the reason is basically here you're talking about transport of momentum. And here we're talking about transport of energy. Okay. So if one would just kind of collapse both equations together, you would get a general transport equation. The phi being, you could put U for momentum, and you could also put T for temperature. Okay. And S being the source term. Of course, there'll be one or two other terms, but largely this is your transport equation. So the transport equation now has a temporal term. We will not talk about that for the time being, but we have two main terms, which is, as someone pointed out, Smriti pointed out, it's an advection term and a diffusion term. Okay. So one needs to understand momentum hai, energy hai, but you're talking about something like transport of either of these. So if it is a transport of either of these, what kind of transport? Auto mein baith ke ja rahi hu, or am I sitting in a bus, or am I kind of walking, right? So what is the type of transport that's happening? And that is kind of summarized by either the advection or the diffusion. What does advection mean? Advection means a bulk movement. So if I'm having a fan and I'm blowing air in one particular direction, there's a bulk movement. That's advection. Diffusion means if I just kind of, if you hold a matchstick, strike a matchstick and just hold it, you will see this smoke doesn't, I mean, of course it rises in the top direction, but there's a lot of dispersive movement, right? So that is called diffusion. Diffusion is largely because of vibrational movement of the molecules. Okay, so this transmission is through vibration and that doesn't have a particular direction. Okay, so either there's a bulk movement or there is a vibratory movement from all directions. And typically movement is a combination of these two. It's not one or the other. It's a combination of these two. Okay, so essentially we have understood that there is advection and there is diffusion. Okay, and they have slightly, advection means you have only del dot something. Diffusion means you will have gradient of the gradient. Why? For example, think of temperature. Particular temperature will only move from high temperature to low temperature if there is a gradient, correct? So that is why grad of a gradient. Okay, so now once you've talked about this equation, let us look at the numerical aspect of it. Okay, so till now we have looked at the mathematical. What was the mathematical objective? 3 equations, mass, momentum, and energy. Mass is just a control equation. You have momentum and energy equation, which is, it's a transport equation. Once you've collapsed that equation, you identify there are 2 terms, which is diffusion and advection. Now we'll have to handle it numerically. Okay. Yeah, go ahead.
Yeah, I have a question regarding the momentum equation. So you talked about Laplacian. So could you give a brief explanation of what is the Laplacian doing, the Laplacian operator doing in the momentum equation? What is the physical aspect of it?
So when you talk about movement, like I told you, if I'm going to model this smoke that is coming from a matchstick that I've struck and I've kept it, right? Typically the advective term, so what do you see when you hold it and you hold it up and maybe it goes off, right? It goes off, so you see this smoke plume that is coming up. So typically a large part of the plume will go up, right? So that will be a movement of a directional movement. Why? Because of this natural convection based movement, right? So that will be an advective component. But you will also see strands that are moving in all other directions, which is not really, you will see some plume that's coming down and going up. That is typically local gradients in density, which is going to drive it. Okay, so this difference in a gradient, like a vibratory motion. So the smoke particles are vibrating and they also push the adjacent particles which are stationary. So that movement gets propagated. So what we're talking about in momentum transport is transport where a bulk amount of these particles move up because of the gravity driven differences. The other is because of their vibratory motion, hotter temperatures, they push the additional particles which are stationary into a vibratory mode, and there is transmission of movement. That's what we mean essentially. Is that clear?
Yeah, if I'm right, it's the so the Laplacian basically is talking about the dispersion of the molecules in different directions. Is that what it essentially means?
It is a dispersion of the momentum.
Okay, momentum. Okay.
It is dispersion of either the momentum or the temperature.
Okay.
All
Got
right.
it.
So
excuse me, ma'am. Sorry for the interruption.
Go ahead.
Ma'am, is there any necessary for energy equation if the flow is considered as isothermal?
Right. So, see, the reason we take a temperature difference kind of expression is it is easier to visualize. Okay. But in the absence of temperature also, a momentum equation will see both advection and diffusion movement. A very easy way of seeing this is if you in a flowing river, if you just let a dye streak go through, you will see that it will not just go down the advective direction, it will also disperse in other directions. That is another indication that there is also diffusion as well as advection. Okay, was that your question? I was not sure.
No, ma'am. No, no.
Go ahead. What was your question?
Ma'am, I'm saying that if the flow is considered as isothermal, then is there any necessary of energy equation for that property?
No, sorry. When you said isothermal, I thought your question was without the energy equation is momentum valid. If isothermal, you don't have to solve the temperature equation. No.
Okay. Thank you, ma'am.
Yeah. Okay. So now moving forward, let us come to I probably have about 10, 12 minutes. Okay. So when we are now looking at these equations now in mind, mainly the transport equation, right? We'll have to now see how CFD is going to solve it. So the first part of the solution is I have equations which I have to solve. But what is the control volume that I'm going to solve it under, right? So the smaller the control volume, the more accurate your solutions are going to be. You will understand why. So at a later point in the talk. So for it to be small control volumes, that means I should do spatial. So if this is a room that I'm sitting in and I'm interested in the airflow, it will obey the conservation equations which I'm talking about. But the point is, if I just divide it into 5 big boxes, it will not be accurate, right? So I'll have to kind of divide it into smaller boxes, which is called spatial discretization, okay? And in all these small boxes of the room, I will solve the conservation equation. So this first step of dividing a domain into smaller control volumes is called meshing. Once you've done the meshing, you will solve the governing equations, this transport, mass, momentum, and energy equation in each of these control volumes. Now, when you're solving in each of these control volumes, what happens is it's a PDE, right? A partial differential equation. A partial differential equation is essentially an equation which says at every micro point, the equation is valid. But I have a finite sized control volume, right? So essentially, I will have to integrate that equation to apply to that entire control volume. We will see how. Correct. So first step is dividing it into smaller boxes, the domain. Then applying whatever equation I have to for that entire control volume. Now, even if I do that, I still have a kind of a differential form, right? And a computer will not understand how to go ahead with it. So I have to convert it into an algebraic form, right? So these are the 3 steps in any CFD. Okay. So now let's take an example. So I've just taken a 1D steady state equation. Okay. So when I say 1D steady state, then you have the conduction equation, which is d by dx k dt by dx plus the source, right? So this is only your Laplacian term because we know conduction is mainly only diffusion. There is no advection. Okay. So we have, say, a rod, and I have divided it into 3 control volumes. That is the first step, which is meshing, right? And the second step is writing the PDE equation, partial differential equation. And the step is I have to integrate this, correct? So if I'm going to integrate this, right, and I already answered the question that this is diffusion, right? So if I have to integrate it, I have to integrate it from one place to another. What did I say? For the entire control volume, correct? So if this is my rod, right? And I have a control volume, say P. Okay, I divided it into 3 control volumes. So let me talk about the central control volume. Okay. And the control volume to the left is the west control volume. The control volume to the right is the east control volume. And you have the present P control volume that you are actually interested in. Okay. Now, I divided it into 3 cells. So the control volume will have faces, right? Boundaries. The boundary of the control volume is depicted by the yellow line. Okay. Now, between the present P, center point of the cell, and the center point of the next cell, this boundary lies. So I will call it the east boundary because it's between P and E, right? So I'm calling it with a small e. Similarly, the west boundary will be a small w. Okay. So what did I say? First, you write the PD equation, but then you will have to apply it for the entire control volume. So I'm integrating it right from the west wall to the east wall, correct? Left to the right, full control volume I'm applying. Okay, this is only one dimensional, not 2 dimensional. Okay, so I have this equation which I am now having to integrate. Now, if I integrate d by dx of this into dx, this will just come out, right? So k dt by dx, upper limit minus lower limit. So upper limit is the eastern face, lower limit is the western face. K dt by dx plus, now this term s delta x. Dx is actually delta x because this is the length of the control volume distance, delta x. Okay, s delta x is equal to 0. So now we've got somewhat of an algebraic, but there are still differential terms there, right? So now I go on to, this is the equation that I have. This is the control volume. So now let us look at the first term, which is k dt by dx at the east face. East face is this yellow line, right? So I want dt by dx of that face, right? So then I take an approximate. I don't know the gradient or change in t in the x direction right at this face. I only will know here at this central point and this central point, right? So then I make an assumption of a linear gradients. This is where the assumption lies, which is why smaller the control volume, more accurate will you be. If you have a large control volume, it will not be a linear variation, right? Smaller control volume, I say TE minus TP by delta X. The smaller delta is this distance, okay? So I take this minus for the west wall also, I do the same thing, okay? And then what do? I just open up all the brackets and combine all the TPs together, TEs together, TW. Coefficients and all I've clubbed together. That's all. Now this is an algebraic equation. And what are the coefficients? Coefficients are the thermal conductivity and the distance between the cells. Thermal conductivity, you know, of any material. And the distance is your choice, right? You're dividing it into a control volume. So this is mainly a constant. So APTP is equal to AETE plus AWTW plus B being the S delta X, the source term. So this is an equation for one cell. Now you will have several cells. So you will have a system of equations. So now we have only looked at which term? Diffusion term, correct? Because this is a 1D conduction alone. Okay. Now, for example, I am not interested only in conduction, but the temperature or whatever. There is the transport equation, which is having advection and diffusion, correct? So you will have, I'm ignoring the temporal and the source term for now. So you have the advection and diffusion term together. One in the left, one in the right, right? So similarly, I will be writing the integrated form of it. That's the first step. From the west end to the east end, right? Lower limit to the upper limit, okay? And I am integrating it. When I integrate d by dx of rho u phi, only this rho u phi will come out. Upper limit minus the lower limit. equal to, similarly, d by dx of this one will come out. This is diffusivity or whatever you want to call it, d phi by dx, east minus the west. Okay? So when I finish the integration, this is my form. Now I need phi. Phi can be anything, temperature or velocity, right? For now, let us look at the perspective of temperature maybe, right? So phi E meaning at this, what is the temperature? In the previous case, what did you see? dt by dx. That is this one. So you need gradient dt by dx, but in this case, I need t. Okay. So t means then I am taking a average. Tp plus Te by 2. This is again an approximation. Okay. And I've made a choice or a scheme choice for this. And I have taken Tp plus Te by 2. And when I substitute this you already know how to calculate by linear approximation is one approximation. I will open up, combine all the coefficients together, and I will get an algebraic form. So what are we saying? Advection के लिए एक approximation है. For diffusion also you have an approximation, and these control your errors in your CFD code. Okay. So what is a recap of the procedure? First is write down your equations. Correct? System, from a systemic equation, you have to convert it into a control volume equation. Okay, which is your mass, momentum, and energy. Then you will apply the finite volume method, that is FVM, because you're working with control volumes, right? Where you will start to first mesh the domain. Then you will have integration of the governing equation that you have written. And then you will bring the algebraic equation by making choices for the advection and the diffusion schemes. And then you will get a system of equations, because that's not one cell. There's going to be n number of cells. So when I say system of equations, what will happen is you will get a matrix, right? APTP is equal to AETE into B, correct? So what will happen is you will bring all the coefficients to one side into this A matrix. T will be your unknown, is equal to B is your source term. So you will get some matrix like this, okay? And you will have several such matrices, one for the U, one for the V velocity, one for the Z velocity, then one for pressure also. So you will have several such matrices. So then comes the matrix solver choice, okay? Which is already default in OpenFOAM, but as you become more and more advanced, you will know how to solve these, what solver is best. Okay, there are some guidelines also. So this is this entire procedure for CFD. Okay, when you're writing a code. Now in OpenFOAM, this is going to be your case file. You will see in the coming sessions. The main thing is you will have the main case file. Case file, there will be a zero file. Zero file means initially what is the system? Everything is zero. Initially zero, and then I start the fan. Something like that, right? So initial conditions you will set. Then you will set constant conditions. What are constant conditions? Like thermal conductivity, properties, no? Transport, turbulence properties, something like that. So there is a zero folder, which is obvious initial condition. Constant folder, right? And then there is called a system folder. 3 main folders. Under that, you will have some subfolders. So there's a system folder. Okay. Now, this is the most important folder because you have 4 main things. And it maps on to whatever lecture I just gave you. First step was what? Meshing, right? So you have the block mesh file. Okay. Next thing was what? You have to set some choice of equations, correct? Choice of equations, and you know, time step initial condition kya hai, time step kya hai, all of that, boundary conditions kya hai, all of that is control dict, choice of the problem, okay? Then you choose approximations, which are schemes, which is FV schemes. And then you will choose matrix solvers, which are FV solutions. So the 4 map on very logically to the CFD methodology, BlockMesh, control of this problem, what are the governing equations, what are the boundary conditions, schemes or approximations, and then FE solution. Okay, so is the procedure of CFD clear, number 1? And where to look for what control in OpenFOAM, you now know. So it is very important you understand this background. Only then you will understand today's the important nitty-gritty points of the bottom point. So it's 11 and I will stop here. I will take any questions for the next maybe a minute or two. Payal, am I allowed to? Are we on time? Is it okay?
Yes, ma'am.
Okay,
Sure.
great. So any questions? Are we good? Okay, I think we are good. I don't see any questions. So we are good. So good luck. Have a great day today. And please ask questions because then it makes your understanding more stronger. Okay. All right. So Payal, over to you.
Yes, ma'am. Thanks a lot, ma'am, for your talk.
Yeah.
And participants, I would request you, like, for example, if you have any other questions on Janani ma'am's talk later on, after this workshop, you can always write to us through an email. We will share our email towards the end of the workshop. So please be with us. Okay, and then we will proceed with the next hands-on session now. So what to my team members? So I am there today along with my team members, Mr. Evan Fernandez, Mr. John Pinto, and Mr. Manjil Sitola. So they are there today. So what to you, Evan?
Yes, ma'am. Thank you, ma'am. So good morning, everyone. I'm Evan Fernandez. I'll just share my screen once. Okay. Yeah. So is my screen visible? Okay. So just minimize this. So Janani ma'am has given a basic overview of how CFD is and in OpenFOAM what to look for exactly. So I'll just go right through this. So just an outline of what we'll be seeing in this hands-on session. So most of you now, Janani ma'am has given you a overview of what CFD is. So this is quite clear. The applications also are quite clear right now. So I'll just give you a brief overview of what OpenFOAM is. So OpenFOAM basically stands for Open Field Operation and Manipulation. So it is basically used to solve CFD problems, but you're not restricted to CFD itself. You can go around with doing many types of simulations with it. And it was developed by Henry Weller in the late 1980s at the Imperial College of London. So it was first made as a foundation version. So you will have the basic OpenFOAM 1, 2, 3. Those were your foundation version. But in 2015, the company, basically what the people who are running OpenFOAM, they have branched it out into a foundation version and a .com version. That is basically you have the ASI version. That's why you have in the later versions, the basically OpenFOAM 2412, 2406, 2212, that way. So the main difference between both these versions is that the foundation version is basically they don't get too many updates quite often. And the ESI version is frequently updated after every six months. So you will have some new post-processing utilities or some new solvers that are introduced. So like if you see in OpenFOAM 9, you will have a set of solvers for your basic problem. Like if you have to do some supersonic flow, you're restricted to solving certain equations only. Whereas if you go with the .com version, you have a variety of types of solvers that are more stable compared to the foundation version. So there are a bit pros and cons of each of them. So you can look at it accordingly. It is widely used, OpenFOAM is widely used in academic and industry. So as ma'am said, that in case you have some preliminary simulations you want to run, running it on a commercial software would be quite expensive. And you might not know that whether that project is going to go into the next phase or not. So OpenFOAM is like that, how you say, like cost effective as compared to commercial solvers, softwares, and it is ready. There are readily available solvers. So if you have any specific problems in which you want to tinker with the equations, or you want something that will solve the equations according to your needs, so you can create your own solvers as well. So you can modify it as and when you need. And there are some important fundamentals you need to understand of CFD. That is your mesh generation, discretization, solver algorithms, everything. So now you've understood the background of the equations, how the equations are solving, how to connect the dots. So now we'll go to the process of CFD. So first you have your problem definition. So depending on the problem, you're going to go about it. So first you start with the problem definition. According to your problem definition, then you go into the next step, that is your geometry and mesh creation. Within this, you will basically see which part of your problem you want to compute. Like if I have a long pipe, and if I want to compute only one section of that pipe, so I will create a geometry and a meshing domain only of that section. I won't need to compute the whole pipe. Once you're done with the meshing, then you move to the solver selection. Which set of equations you want to solve, what is your end goal, what you want to find out. Once you're done with that, then you go to setting up your boundary conditions. Now keep in mind, setting up your boundary conditions is quite important. Otherwise, you might not get proper solutions, and your solution may not converge. So those comes to the next step, that is your solutions and convergence. Once you're happy with your solution and it is accurate enough, then you go to your post processing. If in case you want to find out some additional things from that simulation itself, like if I have an airfoil and I'm doing a simple flow over an airfoil, I've got my simulation result and everything. It's computed, converged perfectly well. And then I want to do some post processing of, suppose I want to find out the Strouhal number of the frequency shading, of the vortex shading behind that airfoil. So accordingly, I can do those post processing utilities. One good thing about OpenFOAM is you can use Python, or you can use any other softwares to write a custom code to compute something once your simulation is done. So now if I haven't, now I'll take the airfoil case. If I have that airfoil and through the simulation, I am getting some forces. Say I'm getting the pressure and viscous forces and all those. So through that, I can write a custom code in Python to find out the frequency, to find out the vortex shedding that is happening behind the airfoil. Along with that, I can also find out the coefficient of lift and drag all at once using the post-processing utilities. So some important things are, now in case your solution, so it's not just a one-way thing, like you start with your problem, then you move to your geometry, and then you're done with it, everything that way. So in case your solution isn't great, so you have to come back again to your, in case your mesh is not good enough, so you have to come back to your mesh and then restart the whole process. Again, if in case your solutions are not according to how you require it, then you have to go back, you have to check your boundary conditions. So there's a lot of, if in case you are starting a new problem in the beginning, there will be a lot of trial and error. So it is good that you make errors so that you learn better. So yeah. So as ma'am said, this is the case structure in OpenFOAM. First, you have your 0 folder. Now within this, you have your initial boundary conditions. That is everything that is set to 0. You specify your velocity, pressure, or temperature. If in case you have those, then you come to your constant folder. Now within this folder, you will have all the properties that are constant during your simulation. That is your, suppose you have your density, if in case it is constant, so you will specify that. Any fluid properties that are there, those will remain constant throughout the simulation. So those all are kept within your transport properties or your turbulence properties in case you're adding any turbulence. So those files can also be added. And lastly, the most important folder, that is your system folder. Within this, you will have your BlockMeshDict. This is where you will specify certain set of points to define your domain and to mesh it. Within, after that, you have your control dict. This is again controlling your simulation, your start time, end time, after how many time steps you want to write some data, how many sets of data you want to write, how much you want to delete, all those parameters. Within the control dict, you can also specify any post-processing utilities. As I mentioned, if I want to compute the forces or the coefficient of lift or drag, certain things like that. After that, you have your FV schemes and solutions. As ma'am said, these will basically say, these are the things that will solve your equations, how much relaxation factors you want to set, those all things. So now we will move on to the first step in CFD, that is defining a problem. Okay, so for this particular case, we've taken a simple cavity case. And now in this is a simple block, a single block used in, we are doing it by using BlockMesh. Okay, so this is a single block. The three sides, that is the left, bottom, and right, are walls, and the top wall is set to be moving. So we have a moving wall with a constant velocity of 1 meter per second. Okay, the whole domain is around 0.1 meter, and this is in your X and Y plane. Okay, so first of all, we will start with setting up the case in OpenFOAM. So this is a follow along session. So I will go very slowly. If in case you have any doubts or anything, you can unmute yourself and stop me at that point. So I will go back to any of the problems that you have. Okay. So first, let's open our terminal. You can open it through Ubuntu. If you're on, I guess most of you are on Windows. So I will go about using this thing. So I've opened my terminal. Okay. Has everyone done this? A simple yes or no will also do.
Yes.
Okay, great. So in case any of you are using multiple versions of OpenFOAM, so you will have to call the version. In case you only have one OpenFOAM, that is OpenFOAM 9, you don't have to do this. So now I have multiple versions, so I am sourcing OpenFOAM 9. So once you're done with that, within your terminal, you can type cd $foam run. Okay. So what this will do is it will take me to the run directory that we've created during installation. All of you must have created a run directory during your installation. So by typing cd $foam run, you're going to enter that run directory. Has everyone done this?
Even?
Yes.
No.
Can you increase the font size a little bit?
Okay, okay. Is it visible now?
Yeah, it's fine.
Okay. Okay. Now, once we're done, has everyone done this? Okay.
No.
So the very first thing we'll do is we will make a directory so that we can run a simulation within the run folders. We don't have multiple files just lying around. So we'll make a folder of say cavity case. Okay. So I will type mkdir, that will be making a directory, and I will type the name of the directory I want. Mkdir case, or I'll say cavity case. Okay. So once you're done with this, you can type ls. So now you see in my run directory, I had a previous folder called me412. Now there's a new case that has been created, cavity case. Okay. Has everyone done this?
Sir, what is ls command?
ls will basically list all your the current folders within the directory you're currently in. Now I'm in my run directory. So if I type ls within that, it will list all the files that are within that.
Okay.
Actually, your one shows cavity case. Mine shows cavity case fits daily. I'm not sure if it's
That because you must have, when you're installing, that time you must have copied the pitch daily also to check your installation. So you might have multiple files. So when you make this directory, you're saying cavity case, you've created this new one. You may have multiple files. So that's not a problem. Okay. Yeah. Okay. So once you're done with this, now we will copy a tutorial case. Okay. So if you see, I'll show you where all your tutorial cases are saved. So when you open your file explorer, you scroll down to the very end on the left side, you'll find a Linux. Okay. You click on this Linux, you open Ubuntu, you scroll down to OPT. Okay. Go to OPT. After that, within that, you will find OpenFOAM 9. You click on that, and then you have tutorials. Okay. So depending on the type of simulation you want to run, you have various tutorials based on that. So instead of starting your case from scratch, it is always advisable to take a template folder from these tutorials and copy it into your run directory and then make modifications according to your application. Okay. Now in our case, we want to run a normal incompressible flow. So we'll take incompressible. Within that, we have IcoFoam. Within that, we want to copy this cavity case. Within cavity, this cavity. Okay. So we want to copy this one. Now, I'll show you two ways to do this. So you can, the first way is simple. You just copy this. You press Control C and you copy it into your run directory. So your run directory will be in your Ubuntu. This will be in your home. Okay. So in home, you'll have your name folder, OpenFOAM. Now, in case you have multiple versions, it will show. In case you have one, it will just show you one folder. That's not a problem. And you'll have run folder. Okay. So this is the file that we just now created, cavity case. Okay. So the simplest way is to directly copy paste it. But a thing in with Windows is when you copy, it will start creating these zone identifiers. That's a little bit irritating at some point. After some time, when you have to copy multiple files, it will create each file's zone identifier. So that is a little bit irritating. So you can do another way. So if suppose I take,
Sir, I have an issue here.
yeah, what's the issue?
Yesterday while installing also in my system, there was no terminal for Ubuntu or Linux. So I have used one command to get the location of my files. I have used one command like explorer.exe.
Yes.
From there, I have got the file. So if right now I can use that command to get the location of my files.
Yes,
Because in my system, I'm not having any like terminal for Ubuntu and Linux. Yesterday that was the problem.
okay, you can do one thing. You can just now if you I think in your system you had multiple drives, right?
Yes.
So instead of copying it into your run directory, copy it to one of the drives and you just label it as say OpenFOAM or something.
Okay. So like to get that file itself, I should have to use that command explore.exe dot. Then only I can able to find that thing. In my whole system, I'm not having any Ubuntu or Linux portal itself.
Windows 10. Okay. So that only I'm saying that's why you in one of your drives, you just create one folder. Suppose in your E or F drive, you create one folder saying OpenFOAM and you put all your run, basically whatever files you want to run, you place it within that folder.
So how to get that file, like how to get that folders initially? I have created one folder, but what are the things that will be running? Simply you can go to Linux Ubuntu and you are getting that file, but I'm not able to get that file here.
Okay, so you're not able to get your tutorial file itself.
Yes.
I think you can change the directory to foam slash foam hyphen tutorials. From there, you can just copy it, I guess, directly going into the directory.
Sir, can you please give the command to copy instead
Hello?
of folder
Yes.
tutorials?
Like what command should I give?
I mean like CP command to copy that from tutorials.
Yeah, I'll come to that. But first,
when we have installed, the tutorials were not copied, not installed in the OpenFOAM.
Yeah,
See,
you can directly
tutorials
first
are
go to the
there by
tutorial.
default.
But
Tutorials you don't need to copy.
But where are the tutorials? I'm not able to find in my system.
Yeah. So do one thing. Others, please, you all don't speak now. 1 minute. Who's this? Who's having the problem? Can that
Mohammed
person
is
only
fine.
speak
Yeah.
up?
This Mohammed is fine.
Yeah. So others, please mute yourself. Yeah. So see, Mohammed, maybe because you are running on a different version, so some of the commands may not be working, or some of the things that we are like Windows 10, so that might not be seen. So you can run completely by the from the terminal as well. But since for beginners the terminal is difficult, that's why we were showing from the GUI version. So what you can do is in your terminal just type TUT and press
TUT.
enter.
So
Yeah,
what should I type?
TUT and press enter.
TUT.
Yes, TUT. Like Evan will show you.
Tutorial. Okay,
Evan is
tutorial. Okay.
demonstrating. So
Okay, okay, tutorial.
TUT directly takes you to the tutorials folder.
Yeah.
And from here you can copy whichever. So now if you want to view where this folder is, just type explorer.exe and .exe and then space and then dot. So it
Yeah.
will open that current directory in the Explorer. So
Yeah,
see,
right now
it
I
opened the
can.
tutorials.
Yes, sir. I've
Okay.
opened. Yes, sir.
So now once you do that, you have to copy which case. So now Evan, show them. So you have to go to incompressible, icofoam, cavity,
Yeah.
and in that cavity. So copy this folder. Copy the complete cavity folder, or you copy the contents.
Okay.
Okay, and then take it to wherever you want to create a run directory. Evan just demonstrate that one.
Yes, yes, sir. I did that.
So Evan is demonstrating that. So these are for people for whom that the Windows is not sorry, the Ubuntu file system is not seen in the Explorer. Okay. See, you can also whatever Evan is demonstrating, you can do that by running the command in the terminal. So Evan will demonstrate that also if you are having a problem. So there are two ways of doing that. Evan quickly demonstrate both of them. Whichever is working for you, you go ahead with that.
Okay, sir.
Yeah.
Yeah. So the very first one, wait, I'll just come back to my run directory.
Excuse me.
Yes.
Am I audible? I'm sorry to stop you at this moment. Hello.
Yes, yes.
Yeah,
Go ahead.
actually, yesterday when the session was for the installation of OpenFOAM and everything, actually I stay in UK, so I was at a different time zone, so I couldn't actually install it on my laptop, which is university controlled. So is there a possibility of having a session like that so that I can debug the problems which is occurring on my laptop? If after this workshop, is there a possibility? Because I tried that Google Meet link as well, but that was not working.
Actually,
Not right now, after.
not right.
Yeah.
Also, yeah, individual support is a bit challenge for us because we are short-staffed and we are very busy with the ongoing programs like the semester-long internship and the summer fellowship. But if you can you can try by yourself and you can take a screenshot of the problem that you are facing, and you can send it as through email. So in that way, we can communicate with each other and solve the problem.
Okay. Okay.
Yeah, because live session is a difficult because from 10 to 6 is our working hour as per the IST time. Yeah.
Okay.
So let us communicate through emails. You try by yourself and then you come back to us.
Thank you.
Okay, Evan. So let's continue.
Yes.
Yeah. Sorry for the interruption.
So as I showed you, this was one way you can copy the files manually, or I'll just delete this one. I'll show you another way. You can do it through the terminal itself. Now, so this is my cavity case. So the second way is to write this command cp-r and you type $foam tutorials. Okay. Now what you're doing is you're saying copy the whole directory, that is cp-r. Then where to copy it from? That is your foam tutorials. Within that, we had an incompressible. Okay. So within that, we had incompressible. I'll just backspace this. Within incompressible, we had icofoam. Now within icofoam, we had the cavity case. And within that, we had one more cavity case. Okay. Now, we are saying that copy from the foam tutorials, within that in your incompressible, within that inside your icofoam, within that cavity and again cavity. And then you press a space and you say that I want to copy it now within this cavity case that we've created. So you type in the name cavity case and you press enter. Okay. So once you're done with this, now this cavity case, it was empty. I deleted the thing. So you see there's a cavity created. Basically, from the tutorial itself, it has copied that whole cavity case and placed it within my run directory into the new file that I've created. Okay. So I'll just show this command again for those of you who are typing. So can all of you do this? Has everyone done this?
Yes, sir.
Okay, great. So now if you see within your file, it has not created any zone identifiers. So this is quite convenient if in case you're working on a Windows system. If you're working on a Linux system, directly copying it does not cause any issues. Okay. Now,
Sir, I also did that, but there was an issue. It is saying that missing destination file operand after this.
have you typed have you put a space and then typed cavity case?
Okay, okay. Before cavity case, there is a space.
Yes.
Okay.
Basically, you're saying copy from foam tutorials, incompressible icofoam cavity. Then there's a space, and then after the space, whatever name you type, it is saying copy to that folder. Okay. So whatever folder name you give, it will copy it within that.
Now it's done.
Yes. Okay. So now we have to enter this cavity case. So you type cd cavity case. Okay. You can always press tab. Once you're done typing half the letter, it will automatically fill in this case name. So you type.
Hello, sir.
Yes.
Actually, the thing is, even while going through the Explorer, I'm having the tutorials folder, but
Okay.
in that I'm not getting a incompressible folder specifically. I'm getting different folders like incompressible fluid, incompressible multi-phase viewer, and even after typing the command which you typed, that cavity case command just now, it is showing no such file or directory. So
Okay.
how to get to it?
Have you done your installation properly? Which version are you
Yes,
installed?
This is OpenFOAM 12.
Okay, so we are specifically told to install OpenFOAM 9 because of this reason only. Most of the files within OpenFOAM 9, between OpenFOAM 9 and OpenFOAM 12 are different. So to have that streamlined thing, that's why we are told to install OpenFOAM 9.
Okay, so is there any substitute I can use for icofoam?
You can check within your tutorials only. Icofoam will be kept in another folder. It won't be kept into the current one. The folder structure is also a little bit different. So you can just search that once on in which file exactly is icofoam kept in OpenFOAM 12.
Okay, sir. Thank you.
Okay.
Hello. Actually, I am also facing the same issue, but I installed the OpenFOAM 9.
Okay. But you can't find icofoam.
No. It's showing that no such file or directory after typing the command. Manually, I can able to do it by copying and
Okay,
I
so
paste.
again the same thing. Have you put a space after this? Wait, I'll just lower the font. So you see there's a space between cavity and cavity case. Have you done that properly?
Yes.
Okay. Just check for any typos in case there is on.
Yeah, I checked again, but there's none. I typed exactly the same thing.
Okay, so if you can copy it manually and it is working, then you can go ahead with that also.
Oh, okay, fine.
Yeah, just make a note that whatever zone identifier extra files have been created, just delete those because while running a simulation, it may cause a problem.
Okay.
Excuse me, sir.
Yes.
Hello, sir. Hello. Sir, actually, I have to copy that cavity folder. And after that, what I have to do?
Once you've copied the cavity folder and you've pasted it in your new cavity case that we've created. Have you done that?
In cavity case, where will I get it? Actually, they have installed it of my own, and maybe there was a problem. My files are in user, and here it is available in the user and share folder.
Rupindra, I
not
can't.
in the OPT. It is not in the OPT.
Your tutorials are not in your OPT file.
Yes, then do I have to copy all the folders in the OPT?
No, you don't have to copy all the folders from your OPT. Within your OPT, you have OpenFOAM. So I'll show you. Okay. So you see, this is your OPT file. Within that, you have OpenFOAM 9.
Okay.
Within that, you have tutorials. Okay. Now within tutorials, you have incompressible.
Yes, yes. These
Inside
files are, it is not in my OPT folder. It is in, I shared that one. It is it is in user, lib, then OpenFOAM, then OpenFOAM 24026 tutorials, incompressible. You can check that.
Yes, that is because you are on 240. On which version are you of OpenFOAM?
2406. Actually, last night I have installed because I was traveling yesterday. That is why I installed it in night by my own through YouTube videos.
See, there is a lot of difference between 24006 or 2412 and between OpenFOAM 9, because they are, as I said previously in the intro also, that one is the foundation version, other one is the .com version, that is the ESI version. So most of the set of commands and file structures will be very different. So for this icofoam case, it is at least similar, but for the next one that you have a heat transfer case, in that some files are not present in the .com version. They have been removed or they've merged together. So for the heat transfer case, you might find it difficult.
What can I do right now? It's possible to
See, you can do your simulation in both the versions, that's fine. But there are a set of files that won't be matching according to what I am demonstrating now. And the majority of the crowd here will have OpenFOAM 9 installed. That's why we've gone with OpenFOAM 9, because it's easier to learn as compared to the ESI versions, because most of the files are merged together and you won't understand basically what is going on. Okay.
What can I do? It means, is it,
see, for this case, now you can continue what I'm showing. You can copy that file directly into your run directory and go ahead with it, because for this case, the commands are exactly the same. Okay.
It means that folder I have to copy in my run
Hello,
directory.
am I audible?
Ankit, could you wait a second?
Yeah.
Yeah, go ahead.
I have to copy this icofoam means cavity folder into my run command.
Yes. Within your run command, you've created this cavity case. You created this cavity, you put it within that. Okay.
Okay.
Yeah.
Thank you.
Yes. So who had a doubt?
Hello.
Yes, Ankit.
Sir, in run folder, where to copy this folder? Because I have not found the cavity case folder. I have followed the same step. First, I will do the directory, then ls, but I don't found in the run folder there is any cavity folder.
Could you just refresh your folder once?
Sir, actually, I have refreshed many times, but I could not find.
Okay, so within your run folder, you can just manually create one. You just you make a new folder, and you can do that way also.
Okay.
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 Yeah. So can I go ahead now?
Yeah.
Okay. So yes.
This is Indrashis. I'm saying that I have also installed OpenFOAM version 12. So through WSL, but somehow the files are not matching. I mean, the case setup is not matching some of the files.
Yes, because you have installed OpenFOAM 12. We had told to install OpenFOAM 9.
Yeah, so I saw the website of OpenFOAM version 12 and I installed accordingly through WSL. So after that, I am seeing that many of the case files are not matching. So what to do in that case? Do I need to install it is running in Windows only, but I haven't installed Linux or as a virtual machine separately in the Windows as a host. So what to do now? Means I have not installed the OpenFOAM through Linux system. I mean, the Ubuntu is there, but not as a host in the Windows through virtual machine.
Okay, so Indres, you can just search on Google where exactly are the incompressible cases stored within OpenFOAM 12, and then you copy that into your run directory. Okay.
Okay. Got it. I'll see that.
Yes. So now we'll just go on ahead with the cases.
Hello, sir. Now, when I try to create folder in run, there is a permission denied. So I cannot create the folder. Why this occurring?
Ankit, have you tried doing mkdir in this command?
Yes, sir, I have done it. Same that, but after ls, they have given the that cavity case is fits daily. So it is created or not?
So it is creating a pitch delay but not creating cavity case.
Okay. But when I try to do with GUI, that permission is not denied to create the folders. So how can I do it?
Okay, so you can type sudo and mkdir and then type the name of your folder, that is cavity case or something. Okay.
Okay.
After this, it will ask you to type in your password that you've put when you were installing. So just type in that password and it should create your folder. Okay.
Okay.
Yeah. Okay. So now we'll go ahead.
You say it again, that command, please.
Which one?
That is sudo
mkdir and then cavity case.
Cavity case.
Yeah. Okay. Okay. So now once you entered your folder, so if I type ls, you can see there's a cavity case. So we'll enter that folder also. So you type cd cavity, enter. Okay. Has everyone done this?
Yes. Sir, a minute I'm doing it, sir.
Okay. You can type ls once you're done. So you will find 0, constant and system. Okay.
1 minute, sir. Yes, mkdir cavity.
Sir, OF9 is not found in my terminal.
No. In your cases, you will have only one version. I have multiple versions. That's why I've sourced OpenFOAM 9. You can directly start with the first command, that is this one, cd foam run.
Okay.
Okay.
Hello?
Yes, Indran.
Yeah, I'm saying that like when I first type the CD foam run, it is showing that no such file or directory.
Okay, so have you installed multiple versions or something?
Have I installed?
Multiple versions, or you only have one version, OpenFOAM 12?
No, before 12 I tried to install version 9, but somehow I was facing some problems. Then I installed the OpenFOAM version 12. But it's running in my Windows only, through Ubuntu WSL only. So
No, that
somehow
is
the file is.
so you can do one more thing. You can open the file wherever your folder is, your run directory. Like suppose I have my run directory and I want to, suppose I created a cavity case. I open this, go into cavity case. You can right click and type over here open in terminal. So it will open Windows PowerShell. After that, you can type WSL and it will directly open your Ubuntu at that particular directory. Okay.
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 WSL.
Okay. So has everyone done till here?
Yes.
Okay.
Yes.
So
Yes,
first we will go to the BlockMeshDict. So if I type ls system and I type BlockMesh, okay, or I just type ls system. So basically it will list all the files that are within my system. Okay. So you see in my system, I have the BlockMeshDict. Okay. Let's show you.
Sir, I'm lagging behind. Just a minute, sir. I'm just going.
Okay.
Hello, sir.
Yes, Ankit.
Sir, still I not created the directory. It's showing that cannot create directory file is already exist, but I cannot found it from that. So what to do?
Ankit, can you refresh your system and check whether it
Sir,
has already been?
I have already refreshed many times. Uh, there are lots of folder there in run, but I don't found the cavity case.
Ankit, you're in your run folder only, no?
Yeah.
Because in your run folder, there should only be at max two folders. Since you people have installed OpenFOAM freshly, you will only have one file, that is the test case that you all were testing your OpenFOAM as installed file. Aside from that, you should have nothing more.
But in my run folder, there are many folders are showing.
See, when you're copying your file, you have to copy it within Ubuntu home, and within that you have your name OpenFOAM. In that you will have whatever your name you set, OpenFOAM 9 or your name, and within that you'll have run. Okay.
Yeah. Okay, I will thank you.
So don't copy anything within this run. This run file is completely different.
Okay.
This one is for running OpenFOAM commands in the background. Those you don't touch, so you don't have permissions for these.
Okay.
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 Anything that you want to do will always happen within your home folder only. Because your home folder has been given access to do modifications to any files you want. The other files you don't have access, you'll have to every time type in your password so that you don't go and tinker around with all the background equations that have been set. Okay.
Okay.
Yeah. So once you're done with this, now in my system, I have my BlockMeshDict. Okay. So if you've installed gedit, you can open it through that also. I'll show you through this. So if I want to open it through gedit, I type gedit, I'll type system, and then I'll type BlockMeshDict. Okay. Now once I'm done with that, I press enter. It will open this small dialog box down. So it has opened my BlockMeshDict using gedit. In case you have problems with gedit, there's another way. I'd suggest all of you to do this way only, that open it, double click it and open it in Notepad itself. Since few of you all were having problems with gedit, you can go ahead with Notepad. Okay.
Hello.
Sir, can you show me the gedit code once again?
Okay, so you can type gedit, then you have system and BlockMeshDict. Okay.
Gedit and
basically you're saying that open that file that is within system and then the file name.
Okay, sir.
Yeah.
Sir, it is showing cannot open display.
Okay, that because gedit must have not been installed properly. That's why I'm saying that you open it in Notepad itself.
So where I'll get that file, sir? Gedit.
In your run directory, now whatever cavity case you've created,
okay,
you have your 0, constant and system.
Yeah.
So within system, you have BlockMeshDict.
Okay.
Okay, so you double click it, open it in Notepad. Over here you have it. Okay. Now I'll just.
Hello. Can you repeat it once again after gedit?
After gedit. Okay. So see, instead of going through gedit, go to your folder, your run directory, whatever folder you've created. In that you have 0, constant and system, correct?
Actually, hello.
Yes.
Yeah, I'm not able to locate the folders in my system, like in my users or in my local disk C. I'm not able to find where to get the folders, where to get the, the OpenFOAM folders, all the tutorials folder.
See, that
because
will
I
be
haven't.
in your on the left hand side. You will have this Linux subsection down.
Okay. After
So
that,
you click on that Linux. For the click on Linux, you'll have Ubuntu 22.04 or whatever version you're using.
Yeah, and I can see that it's Ubuntu as well as Ubuntu 22.04. So there are two Ubuntu's which I can see in my system.
Okay, so just see on which one you had installed your OpenFOAM. In case you must have installed it on Ubuntu, then it will be on that. Just check both. Within that, you will have your home folder. Within this home, your name, whatever you specified, and then you have OpenFOAM. Within that, if you have only one version, you will have.
Can you just repeat it, like the steps you have shown?
So you've entered your Ubuntu folder. Within that, you have your home folder.
Right.
So within home folder, you will have whatever
Yeah,
name you specified.
Okay.
Then you will have OpenFOAM.
Yes.
Within that, you'll have again your name folder or OpenFOAM 9.
Right.
That you'll have your run directory.
Yeah. So run directory have, but I don't have the applications and the other one.
No, the application and platform, those are the things that I've created. But in your case, you will only have the run directory.
So I have it.
So within run directory, you will have cavity case. Okay.
Yes.
Okay. Yeah. So within that, you have system, and then you have BlockMeshDict. Okay.
Cavity case. So after that, I will have the system, and I
then
will.
BlockMesh.
So after I put up all those commands that you have given in the.
Yeah, you can. You
which I
can
will
open it through gedit, but in case most of you might have an error with it, so it's better to go with Notepad itself. Okay.
Okay.
So I will go ahead with Notepad only, since the majority of people here will have Notepad at least on Windows system. Okay, so I'll just show you how do you specify. Okay, so this is your typical meshing file or your block mesh file that you will have. So first you will start with convert to meters. Basically, it will be set to default 1. 1 means that whatever units you will specify, it is equal to 1 meter. So in this case, we specified it to be 0.1 meter. Okay. Because our domain, as I said, if you want to specify from 0 to 1, it is 0.1 meter. Let's see this one. Okay. It's 0.1 meter. So first you have the convert to meters, then you have your vertices. Now this is where you will specify your points in space. So I'll just show you the next one. So in BlockMesh, you will have to specify your points within, basically it is comprised of hexahedral. So you will have 6 faces. So you'll have the back, 1, front face, left, right, top, bottom. Okay. So the numbering scheme is you always go anti-clockwise for the meshing thing. So if I have the first point that is set to 0 point, basically at 0, 0, 0, that is my origin. So point 0 is my origin. From the origin, the next point I want it to be at a distance in the x direction at 1. Okay. Then the third point I want it to be at 1, 1 and 0. That is in the z direction, it is at 0. Okay. And then the fourth point I wanted, that is the third point, number 3, is to be at 0, 1 and 0. So from the origin in the y direction at a distance of 1. So the numbering scheme that is there, if most of you have used any, or you have done any coding in C, C++, you know that the numbering always starts from 0. So it will be always 0, 1, 2, 3. So whatever numbering you're specifying, even though you're writing and you say it is 1, but then the background, it is coded in C, C++. So you will have this set as 0. So you'll have points 0, 1, 2, 3. Okay. So your one face has been made. Now the next one is a simple copy of that same 4 points that you've specified, and then you give it a direction in the y. Basically, you give a small distance in the y direction. So in this case, we've given a distance of 0.1. So we want the same points, that is 0, 1, 2, 3, but in a z direction of 0.1. Okay. So I'll show you this in this one. Okay. So you see, this is the very first point. This is at the origin, 0, 0, 0. Then we have 1 point, that is point number 1 at a distance of 1 in the x direction. Then we have point number 2, that is in the distance of 1 in the x direction and 1 in the y direction. So it will be in that space. Okay. And then you have this fourth point, that is in the y direction at a distance of 1. The same thing has been copied. The same one has been copied here. with the only difference being that in your Z direction, you've given a small point. You're saying that extrude it in a Z direction. Okay. The next syntax that you have is your block. Now within this, you will specify the numbering. Okay. So the way you've numbered it, that matters over here. So you will specify the syntax is first you have hex. After that, you will specify the numbering. So you see in the PPT, I will specify it as 0, 1, 2, 3. And then I want to again type that same thing as 4, 5, 6, 7. So you see here I've typed it as 0, 1, 2, 3. And then I have the front face that is 4, 5, 6, 7. So what this will do is it will say that the back and the front face both have to be connected as a single unit. So that will make your one block. Now in our case, we only have a simple block. So it is a single, you have only just one single block. Okay. Then the next, this which is there, you will have your number of cells. Okay. So I am saying that in the X direction, I want 20 cells. And in the Y direction, I want 20 cells. Now, since we are doing this simulation for a 2D mesh, so in the Z direction, you will only give one cell. Okay. So this will become your 2D meshing. If in case you want to do the same case as a 3D, as a 3D geometry, then you will specify some grading in the third direction as well. Okay. And this one will specify your grading.
Excuse me, Evan.
Yes.
Can you increase the font size for recording purpose?
Okay. Is it fine now?
No, it's fine.
Okay. So this simple grading syntax, this one will give you, basically you're giving a grading in your X, Y, and Z direction. You have kept it as 1. So in grading in terms, if most of you now, since you have done MTech and PhD, there are some few students, you must have used ANSYS, correct? So in ANSYS, you've noticed that you call that we call it a
sizing.
Not a sizing. Basically, there's a word for it in ANSYS. From F, I think it was.
Inflation layer?
Inflation, correct. Thank you. So in ANSYS, you have an inflation layer. So the same thing is in OpenFOAM, but over here, you specify it as simple grading. So there are multiple types over here. You have simple grading, then you have edge grading. All of those can be found within the documentation of OpenFOAM. I'll show you that also in a while. So here we've kept the inflation or your grading as 1 in all directions. So it's a uniform distribution. Okay. Then we have the edges syntax. Within these edges, if you have a curve or an arc, you can specify that over here. In our case, we have a simple box it is, so we're not specifying anything. And then last, yes.
Before you move, I just want to ask 2 questions.
Yes,
we are doing a 2D simulation, right? So
yes.
why are we putting one in the Z direction?
So the thing is that OpenFOAM is coded in a way that you can't give just an X and Y coordinate. It will compute everything in a 3D space. But in case we don't want to compute something in the 3D, in the Z direction in our case, so it will just give it one cell. So what it will do is it will take, basically it only has one cell in your that one Z direction. So it doesn't have any computing place or something to go into your Z direction itself.
Okay. Should we put 0? I mean,
if you put 0, basically, that, as I said, OpenFOAM is coded in that way that you have to give at least one cell. That is the bare minimum.
Okay. And another question is in the vertices part. So
yes.
What we're doing is we are defining the control volume, right?
Yes, you are giving a control volume.
And in the part where we put 0.1, we are like telling which way the flow will go.
Basically this is your XYZ coordinate. So over here you're specifying in your X and Y plane, and then we want it the same replication in the Z direction, that you're giving it at a minimum 0.1 distance, since we are only doing it in a 2D.
Thank you.
Okay. Yeah.
So in Z direction, that points of 0.1 is nothing to do with the geometry size.
No, see, you can give it over here as 1 also, because it won't make a difference, because in the Z direction we are only specifying one cell. So it is otherwise not going to compute in that Z direction.
Okay.
Hello.
Yes, Pooja.
Why there is 0.1 in convert to meters? It is something related to unit.
Yes, this is your unit only. So in our case, you see, we've specified the domain to be at a length, basically a length of 0.1 meters in all directions. So you can do this by converting it in the starting only, and then you can specify your units in normal, or you can keep this as 1 meter, but then you will have to specify over here 0.1, 0.1. Okay. So to save time, you can directly type in whatever units you want in this coordinate system of yours, and you can specify your actual units on top, convert to meters 0.1.
Okay, and in the Z coordinate there is 0.1. So it is 0.1 unit in Z direction, or
It will
it
be
is something else.
0.01. 0. Basically you multiply 0.1 with 0.1 again.
Okay,
I will show
so
you once I do the meshing in ParaView, so you can see then what I'm trying to say.
okay.
Can I just ask another question before you move forward regarding simple rating?
Yes, Prithul.
Yeah, so in ANSYS Fluent, so when we use inflation, like we probably use a y plus calculator using the first layer thickness or something, and then
Yes.
we plug in the value, right? So here in simple rating, you have put 1, 1, 1. I mean, what does that mean, or how did you calculate exactly what
Okay,
you put?
so 1 is your uniform. Basically, your grading will work in OpenFOAM. It is, you have the last cell to the first cell, that is your ratio log. Okay. So this
Okay.
one works on a ratio system. So if in case I put 0.1, I am saying that my last cell will be 0.1 times my first cell. And based on that ratio, you compute that and you will get this 0.1. Doesn't make sense?
Yeah, I think, yeah.
Yeah. So we've
Like
kept
it's a growth rate for the mesh, right?
yes, growth rate. In some
Oh,
software you use a
So, yeah,
growth
it
rate.
will be
understood.
Yes. So if you
No,
specify,
can you repeat the what you have said about the simple grading part for the inflation layers, like how you are
Ivan?
doing-
Hello.
yes, Ravi.
Yeah, I just wanted to ask one thing. I mean, here we have made the control volume to be of hexagonal, means of something like cuboid, right?
Yes.
Had we wanted this to be of some cylindrical shape, so what would have been the command for that?
Okay. So you would specify your front plane, and then you would specify, basically you would go in your X and Y direction. You will make basically a circle, and you're saying
Yes.
extrude it in your Z direction.
Yeah.
So that only, as I said, if you want to make any curves or arcs, you can specify that within your edges. Within
Yeah.
this section, you can specify, suppose you
Yeah.
say an arc, and then you specify the points. We will not go too much into this. So there is basically the entire syntax and everything
Okay.
is there in the
Okay. Okay.
documentation. I'll show you the
Yeah. Okay.
documentation
Thank you.
also, where you can
Thank you so
find it
much.
and what you can see.
Thank you so much.
Yeah, and somebody had a question on simple
about
grading
the
part.
simple grading. Yes. Can you just repeat about the growth of the inflation layer, how you are saying?
So
How
in
you
this case now, we specified 1, 1, 1, meaning that the entire domain, whatever cells are distributed, will be uniformly distributed. Okay. Now, in case I specified it as 0.1, you would do some calculations saying basically your simple grading works on a ratio system. It is a ratio of your last cell to your first cell. That is the current ratio. That is the calculation you do. Based on that, you can specify whatever number you get. Like suppose I say that my last cell I want it 10 times large compared to my first cell. So I want the first cell to be smaller and the last cell to be larger. Okay. So I will just run a simple calculation of say 10 to 1. So if I want my last cell to be 10 times, I will specify here 10. So
And
then
this
the
is the
grade
last cell that you're talking about in the X direction.
in the X
And if I want,
direction. Similarly, if you want it in the Y direction, you can put the grading over there also. Okay.
so it represents the how I want to inflate the or like refine or like the machine
Yes.
in that particular area.
So you see, this one is a simple geometry. Now in the next case, when you have a turbulence flow through a channel, that time Manzil will show you how to apply grading and everything. So all of these you will understand sooner in the whole workshop. So don't worry about that. I'm just giving you an overview of how BlockMesh is working.
Is it possible to give a particular first layer height here?
In this case, you want?
Yeah.
You want to add a grading.
Add a particular first cell height.
You want to add a height to the first cell.
Yeah, I will calculate my y plus and then add a particular first cell height to it with a growth ratio of 1.2 something.
Okay. So
is it
but
possible
then
here, or
but then I think you'll have to then adjust the control dict also accordingly to match that, because I think it might give an error later if I give a growth late, because you can see there are only 20 cells and I'm saying to distribute it around 0.1 meter. So if I give in the x direction, it might give some floating point error or something because of the discretization and all that. So we'll keep it as uniform only. In the next case, you can ask Mansil to also do that, because he'll be showing you how to give a growth rate accordingly and calculate your y plus values and everything.
Thank you.
Okay. Yeah.
So like this will create a uniform mesh of thickness, maybe like of 20 mesh in x and y direction, right?
Yes, it will create a uniform mesh. I'll show you all the mesh also once
Okay,
we're
sir,
done with
one
the
more
simulation.
question, sir. One more question. Like
Yeah.
in other software, if here we are doing it dealing with Cartesian coordinate system.
Yes.
So if we are doing like if one person asks if it is cylinder, so if there is something to define cylindrical coordinate system, and from there, like if like assign coordinate system itself, if there is some command is there.
Assigned coordinate system as in?
Here we are dealing with a simple rectangular flow domain.
Yes.
With a problem. Like if it was like some cylindrical system, and from there how we'll define that thing.
So that only you specify basically to make a cylinder, you will have two circles and you're basically joining those two circles, correct?
Yeah, yeah.
So similarly, in your x and y coordinate, you will make a circle. Okay.
Yes, yes.
So if you just break down that circle, it's like just a square with some curves.
Okay, okay.
An arc. Okay. So
all
that
those
only.
things, all those things that has to be done in the edges, right? Inside
Yes.
the edges.
Yes. You specify within edges an arc, and you specify the point that now I want between 0.0 and 0.1. I want an arc, so that I can specify within that. See, wait, I'll show you all. So if in case I type OpenFOAM 9. So if you see in the foundation version OpenFOAM 9, on top you have resources. You can check the user guide. So over here you can see anything, like if you want to find out something about block mesh or something, meshing description. So you can read through this. Each and everything is documented properly. So in case you want to find any syntax also based on the version also you want. So I can click OpenFOAM 9. I can see which types I want. Okay. So you can read through this. You can just type OpenFOAM 9. On top, you have your documentation. You can download also the documentation. Okay.
Okay. That's like one more doubt. Like if my problem itself is dealing with cylindrical coordinate system, like if there is some pore system is there, like some cylindrical systems, accordingly equations will be dealing with r, theta, and z coordinate system. Like our equation will be modeled that way only. So how to deal that thing?
Basically,
In place
you're
of
going
x,
with
y, z, I'll be dealing with r, theta, and z coordinate.
So you're dealing with the spherical coordinate system.
Yes, cylindrical coordinate actually. So like r, theta, and z. Yes.
But then you can break that down into a normal Cartesian coordinate, right?
That would become difficult for like governing equation itself will be written in that way only.
Okay.
In cylindrical coordinate.
So see, if your geometry is too complex, you can always go with snappy hex mesh also. That is another, it's a little bit advanced meshing tool. It's part of OpenFOAM only. What it does is you will specify one normal base mesh, and within that you put your complex geometry and it meshes it according to that.
Okay.
Yeah.
Can I import geometry from some other sources like from ANSYS or AutoCAD?
Yes, you
Or
can
I
do
have
that.
to make.
See, ideally you can always use BlockMesh, because it's an inbuilt tool, and with BlockMesh you have many other utilities that you can do, like in case you want to do some refinement while your simulation is running. So you can use adaptive mesh refinement and all those things. Whereas if you import an ANSYS mesh, that ANSYS mesh will be written according to ANSYS, right? So the background, whatever codes are written, it won't understand. OpenFOAM won't understand how to refine the mesh or something according to that. So you're fixed with that one fixed mesh.
Oh, yeah.
Yeah, but
So
But you
if
can always,
geometry is
yes.
very complex,
So that only,
like
as I was
bed
saying,
width is varying, then
Yes.
how to make here
So
geometry.
that only, if in case you have a very complex geometry, you can always create the CAD file within any software. If in case you're making it in ANSYS also, you can always do that, and then you can use Snappy Hex Mesh to make a mesh for that.
Okay.
Okay. So for Snappy Hex Mesh also, we had held a workshop last year in November. So you can check, it's on YouTube also. You can check how to go about using Snappy Hex Mesh.
Okay. Thank you.
Yeah.
Hi, Ivan. I have a question.
Yes, Asma.
So it's when you said simple grading is about the inflation layer.
Yes.
So when we is it in terms of a 2D domain or is it in terms of a 3D domain? Because let's say like we have a blockade that's located in between the entire computational domain, right?
Yes.
So if you're applying here, though we have said like, you know, it's an uniform sort of a blocks that you're creating in there, 111. But if you increase like a ratio of 10:1 ratio, you're basically applying it to the background or the block mesh itself. So what is the use of applying it to a block mesh rather than, because the inflation layers have to be created on an object so that you can capture the gradients, right?
So you have a geometry, you're trying to say that you have a geometry within that domain and you want to mesh it closer to that geometry, correct?
Yes.
Yes.
But
So
now the question is like, you know, why are we trying to apply that simple grading or the inflation layers on the background mesh or the block? Because this is the entire computational domain here.
okay. So now in this case, it's a simple block. Okay. We don't have any geometry within the domain itself. So in case you want to even have a coarser mesh towards the edges and you want to have it fine towards the center. So as I said, there are multiple ways of doing that. This is the simplest one. Okay. So simple grading. You also have edge grading and you have multi grading. So in edge grading, you can specify a particular edge and you can say that I want a grading of this much on this edge, whereas on the opposite side, I want a grading of, say, suppose 2 or something. So that way you can do using edge grading. Whereas in multi grading, if you have a single block, you can define on that. Basically now over here we're specifying 111. So in the x direction, we're specifying a uniform 10, suppose 10:1 ratio. Whereas in multi-grading, you can specify that towards the left, I want these many cells and I want only a set of grading for this much. Basically, I want a grading of say 10:1 on the left direction and I want 10:1 on the right direction as well. And towards the center, I want it to be a little bit coarse or fine. So you can do that using multi-grading as well. Basically, what it does is it will allot a percentage of cells. Like if you have say 100 cells and you specify a percentage of 50%, so it will say that 50% is towards the left, 50% is towards the right, and then based on that 50% you can give a grading to those 50% cells only. That you can do using multi-grading.
Okay, got it. Thank you.
So that also documentation is there on the OpenFOAM official website, so you can always download those and see that.
Okay, got it. Thank you.
So basically here you told about the inflation layers in the simple grading in the block mesh because this is a simple geometry, right?
Yes.
And so there is no like specific requirement to inflate the layers for in the close proximity of so these simple geometry. That's why there is no requirement to do such things in this block mesh. But I can do it in Snappy Mesh.
Okay.
Okay.
So okay. So once you're done with the block edges, everyone has understood that. Then you specify your boundary. Okay. Now this is where you will specify your patch names. So in this case, we have a moving wall. Now in the patch name, I'll again go back to this one. So the way you name your patches is, suppose I take this right side patch, okay, this one. And if I use the right hand thumb rule and my thumb is pointing outward. Okay, so and if my fingers are curling that, so I will label the whole thing according to that. So if in case my thumb is pointing outward and my fingers are curling around my thumb, basically around my thumb, so I will label it as, say, suppose 1, 2, 6, 5, if I have to label this face. Similarly, if I want to label this top one and my thumb is pointing outward, my fingers will curl in the anti-clockwise direction. So I will label it as 2, 3, 7, 6. Okay. So as you can see in the moving wall, the top part that we have, we've labeled it as 3762. That is in the anti-clockwise because my thumb is pointing upward. Similarly, the fixed walls is specified 3. That is these 3. 1, 2. That is the right side, bottom, and the left side, accordingly to that right hand thumb rule. Okay. So that is the way to label your boundary patches. Also over here within type, if it's a wall, you can specify it as wall. Whereas if you want it to be a patch, that is you want to put some custom boundary condition on it. Say I want it to act as an inlet or an outlet. So I will just simply type patch. Okay. So there are multiple types also. Those also are mentioned in the document itself. So you can always read that. Okay. Front back, if you want, in case it's the 2D domain, if you do not specify any of the front back faces, it will OpenFOAM will directly take those as default faces and it will put that into one. Basically, it will create one patch saying default faces and it will start running it. Your default, basically front and back, since it's a 2D domain, we will take it as empty since we don't have to compute anything in that. Okay.
Could you please explain the front and back part?
Okay. Now, in case you have a 3D domain, okay, I'm taking a simple box. I have the left side as an inlet, right side as an outlet, and everything around it is a wall.
Yeah.
But in a 2D domain, if I want to compute, say, a channel, I am saying that the left is an inlet, right is an outlet, top and bottom is the walls. And in the Z direction, I am extending it to up to infinity in both the directions. So technically, the front and back will act as an empty patch because we are not giving it any wall condition. If you give it a wall, it will start computing the drag and everything, basically your boundary layer separation and all that. All those things will start being created over there. So we'll start computing that also. If you give it as empty, it is saying that within that direction it is empty and you don't have to compute anything in that.
Okay, understood.
Yeah. So this is your BlockMeshDict. So once you're done with this, you can close this. Yeah. Next you have is your control dict. I'll go a little bit fast because the next session also was supposed to start at 12 o'clock. So within this, you have your application IcoFoam. So
even increase the font size.
Okay, yeah, sorry. Okay, so over here you have your IcoFoam. Start time, whatever, it will start at 0, and I'm saying to end it at 0.5. Over here, you will compute your, basically based on a current number, you will specify your delta t. So those sets of calculation you will run before you run your simulation, and you specify your delta t accordingly. If you give this number too high, your simulation will crash midway or it will not compute itself. So keep in mind when you're doing any simulation, if it's too complex, obviously your delta t will be lower. If you're going with a finer mesh, again, it will go lower.
So delta t is a time step, sir?
Yes, your time step. Okay. Then you have your write interval. After how many iterations or write time, like you're saying, delta t, after how many of those you wanted to write some data. So I am saying after 20 of those iterations are done to write one file. So that you can do using this one, write interval, write format, ASCII, runtime, all those are always kept at default. Also purge write over here, that is there in case you're running a very heavy simulation, a steady state simulation, and you're only, you're only interested in the last result. You don't have to see any of the intermediate points or anything like that, intermediate results. So you can specify this as, say, suppose 1 or 2. So what this will do is it will, suppose now if I'm saying after every 20 iterations to write a file. So if I have a file from say 0 to 100 and I give a purge write of say 10. So once it has written 10 files, the 11th file that it will write, before writing the 11th file, it will delete the very first file that it had created. So at a time, it will only save up to 10 folders at the end, the last 10 files. So that you can do using purge write. Okay. Usually it is kept, if you're doing a transient simulation, you will obviously need all the files that that you're computed and written to get your contours and everything. But if it's a steady state simulation, then using PurgeWrite is advisable because it saves your storage space also on your laptop. Okay. So this is your control dict.
For transient simulation, what should be that PurgeWrite? Like, what's the value of PurgeWrite?
Typically, it is kept to 0 only. But in case you have a steady state simulation or you're having some storage problems or something, you can do two things. If you have a storage problem, you don't have enough storage in your laptop or something, you can put your write interval to a higher number. So it will start saving the files at a higher number. That way it is. Okay. After a lot of iteration, it will start saving only one file. Or you can use PurgeWrite to only save, suppose, the last 10 files or the last 5 files in the simulation. But in transient simulations, it's always kept to 0 only because you will need all the files that you've computed.
Okay.
Okay. Yeah. Then we have FV schemes and FV solutions. I won't go too much into these. I'll just give you an overview. Basically, over here, you specify which set of equations you're solving, all of those parameters. In FV solutions, you will have your basically which solvers and all you're using, how you want to solve it, which equation, that basically whether it's the pressure equation or something like that. Pressure based solver and all that. Okay. Then you have your constant folder. Again, in this one, you have all the properties that will remain constant. Okay. So now in this one, we have a new, that is your kinematic viscosity. We set it to 0.001, that is default. If in case you want to simulate for air, you change it accordingly. Okay. And then you have your 0. So within this, you will have your U folder and P folder. U is your velocity and P is your pressure. So again, in our case, we've put a velocity, constant velocity for the moving wall at 1 meter per second. Okay. So that's why we specified it as 1. So once you're done with setting up all your boundary conditions, in this case, we're leaving it the same.
Initially, sir, like we have put some scale of 0.1. So that will be considered here while putting the boundary condition. That magnitude will be multiplied by that. Okay.
No. See, basically, if you see the top section over here, this is your dimensions. So your dimension, this one will set basically this 1 stands for meter. Basically, 1, it is your this. For pressure, it is your pascals, meter.
SI unit.
Yes, your SI unit system. So over here, it is meter per second square. So this one is your time. This one is your length, and this one is your time. So this one won't be converted according to that. So it is running at pure 1 meter per second itself. Okay.
I even have one more question. Is it okay if you
Yes,
can take some question? Okay. So what is the difference between internal field and a boundary field? So you have mentioned there is an internal field over there with an uniform 0, 0, 0. So what is it actually doing?
Okay. So in an internal field, you're saying that so already there's some flow going on. Now if I specify over here as 1, I am saying that the internal field is already set to 1 meter per second, and whatever values I'm giving now, the moving wall, it is starting at 0.1 at 1 meter per second. So you can basically it just saves you a little bit of computational time, but it is negligible. So if you have in case it's the tutorial case, they usually leave it at 0. But in case if you have a temperature, let's go for temperature. That is a more better example. You have your domain that is at, say, suppose you're saying you want to set it at normal HTP at 30 degrees. So I will convert that to Kelvin, and I will say that it is around 293 Kelvin or something. So I will specify that my domain itself is set to 293 Kelvin, and whatever additional temperature, that if I'm giving it from the left or right, as I'll show you in the conduction case, in that way specifying the temperature, and that internal field is also already set. So all of these I will explain that time also. So don't worry about that. Okay.
Okay. Thank you.
Okay. So once you're done setting up everything, so the first thing is in doing your entire simulation, first you will create your mesh. So that you will do using the BlockMesh command. Okay. So everyone just type this in. You type BlockMesh and then you type enter. Has everyone done this?
Yes.
Okay, great. So once you're done with your BlockMesh, then the next thing is you want to run the simulation. So in our case, we're using the solver IcoFoam. Basically, IcoFoam is just your incompressible foam. It is just a solver made to compute incompressible flow. Okay, so I'll type the solver name IcoFoam. Okay. Has everyone done this? Then you type enter. It will start running a simulation. Now, since end time was quite small, so it has computed instantly. So you see the current number over here. We specified the delta t accordingly so that it does not cross current number 1. Okay. Now, everyone has done this?
Sir, can you please rewind it, sir?
IcoFoam.
Yes, sir. Sir, from the BlockMesh, sir. So this is
Okay.
from the.
So you can always do BlockMesh and then run that. Done? Ravi, are you there?
Sir, it is showing BlockMesh command not formed, sir.
Are you in your proper? Okay. Are you in a proper file? You have to be in your cavity case only. You don't have to be within system or anything.
Sorry, sir. I'm not in the system.
Okay, so if you're not in a if you're in your system folder by mistake, you can always do cd ... to get out of the folder. Okay.
Okay, sir.
Yeah. Basically, cd ... is to go one step behind, whereas cd and your file name will take you within that folder.
Okay.
Okay. So once you've done BlockMesh and IcoFoam, you can visualize your data that you've got using ParaFoam. Okay, I'll show you both the ways because I know some of you will have problem with ParaFoam. So the first way is to show it through typing ParaFoam simply within this. Okay. The second way to do, for those of you who have problem with ParaFoam, you type touch dot, say suppose result, not dot, sorry, touch result dot foam. Okay. So this will create a new file. So you see over here, these are your run files that when you run, it will start writing all the data. And when you do that touch command, that time it will create one result folder. Okay. So for those of you who have problem, then you launch your ParaView manually, and then you drag this and you directly put it within that. Okay. Yesterday, I think 3 of you had problems with that. So we had
Yes,
shown you how to do that. Okay.
Yes.
Yes. So I will.
What's the commands are like touch result.form?
Yeah. Result is basically whatever name you want to give. Over here, you can type in your name as well if you want.
Hello, sir.
Yes, Aditya.
The thing is, there's a username is written in green, right? At the starting of every command.
Yes.
Okay. So I'm not getting it. I don't know why it has gone.
Okay.
So what should I do?
Okay. So can you just restart your terminal and see whether that solves the problem?
Okay, but will these commands be gone or
No, if
whatever coding we
whatever
have typed?
commands you've typed, you can always press the top arrow key. It will always save all those previous commands that you ran. So you can always press the top arrow key to see which commands you ran previously. So you see, I started from mkdir. Yes.
Yeah, I'm a bit of lagging behind because I was following how you were working on, but I am actually in my run folder, but somehow I'm not able to create the incompressible directory. So what is the actual directory? Can you tell me?
Okay.
Like,
So if you're in your run directory,
folder.
if you're in your run folder, you can just manually create a new folder. Say suppose I want to create cavity case, you click on folder, create a new folder, then you go within that folder, So I'll show you where your tutorial files are saved. So if you're in Ubuntu, you have Linux Ubuntu. Within that, you have an OPT folder.
Okay, those things are not, it is not there because I haven't still put up the commands over in the WSL and in the on PowerShell.
I didn't understand what you're trying to say.
I mean to say that like I haven't put those commands in my PowerShell because those are not there in my cavity folder, cavity case folder.
Okay, your installation has been done properly? Because if your folders and all are not
OpenFOAM is there in my VirtualBox. OpenFOAM is there, run is there. Then after that, cavity case and PID. So when I click on cavity case, the folder is empty.
That because you must have not copied that. So that I'm showing you how to copy it. You can manually copy it, or you can type in this command. Basically, you open your terminal. I'll show you. I'll open a new terminal. Suppose I'm in my run directory. Okay. I'll open this in terminal. Now I've opened it using PowerShell. I typed WSL. That will take me into the Windows subsystem for Linux. So as you see, I'm already in my run directory. I'll just type OpenFOAM 9 because I have two versions. So if I do just clear, yeah. So you will be at this particular point, okay? So you do CD cavity case or whatever name you specified it as, okay? And you do enter. Okay. So now you type in this command cp-r $foam tutorial. Okay. After that, you type incompressible. Within incompressible, there is an IcoFoam folder. So you will go to that IcoFoam folder. Within that, you have cavity. And within cavity, you have one more cavity case. So we want to copy this entire cavity case within the current directory we are in. So you can just put a full stop. Since we are already within the cavity case, if in case you were directly only in your run directory, you could have typed cavity case and all that. But then now since we already entered that cavity case, you just put a full stop. So the full stop means that you're copying this whole, basically this folder from this path into the current directory. That is your full stop. That is this particular directory.
So I will not write cavity case.
No, don't write cavity case because you're already there in your cavity case, right?
Yes. So I will put a dot over there.
Yes, you put dot. The same command.
What is the usage of this dot?
The dot specifies that you want to copy whatever files you specified in that path in the place that you're currently there. That is your case, basically this folder that you're already in.
Yeah.
Okay.
So now
yeah. So you can just run BlockMesh.
It's saying that no such file or directory.
Just check your this if there's any typo or something.
Tutorial, right? Not tutorials. Tutorial, incompressible IcoFoam, cavity dot.
OpenFOAM tutorials S. Okay. Okay. So I'll just show the. I'll go ahead with the result. So we type parafoam.
Excuse me, sir.
Yes.
I actually typed the command name BlockMesh as you mentioned, but then I'm getting a foam IO error instead of the result. It's showing it cannot run the command. It says some IO error.
BlockMesh.
Yes, BlockMesh and for IcoFoam, both of them.
Which version of OpenFOAM you're on?
9 only.
9 only, no?
Yes.
And you've not made any changes in BlockMesh or anything?
No, as you mentioned how to change whatever things, then the BlockMesh, the same thing only I've done.
Okay, because in BlockMesh you don't have to change anything. So you didn't make any changes, right?
No, I didn't make any changes.
Okay. So it's giving an IO problem.
Yeah.
So when you're typing BlockMesh, it is giving that error.
Yes, BlockMesh and IcoFoam, both of them.
Okay. just do foam clean case. Type this command foam clean case. This will basically just clean the whole case. If in case any previous data or something was written in it, it removes that.
Okay.
And now type BlockMesh and see.
Fine, I'll just check it, sir.
Yeah. Okay. So we'll go with ParaFoam. So since all of you all have already brought your file into ParaFoam itself, ParaView. So on the top left corner, see there's a VTK block color written here. So you can click that drop down menu. You can click on U. Okay. And then I click the play button. Okay. So you can see, since this is a moving wall, but now through this you can't understand exactly what is going on. So I'll show you a way to plot the streamlines. So just below your this U, there is this streamline of.
Excuse me, sir. Can you repeat it again, sir? After
Okay.
after opening the paraform.
Okay. So after opening ParaFoam, you typed apply over here. There was one apply button. It should be bright green if you've not already clicked apply.
Sir,
Okay.
but it's not open, sir.
What is the error that is giving?
Sir, in my pipeline browser, only built-in is appearing, sir. No cavity.open form. Sir, I can't see any cavity.open.
See, wait. You're using this only command, no? ParaFoam.
Yes, sir.
Okay, so when you're typing ParaFoam, this way it is showing?
No, sir.
Okay. Have you run your case? Have you done icofoam?
Yes, sir. I have done icofoam, sir.
And in your case itself, can you see these kind of things? If there are some additional files written?
So, one moment.
Just one thing, like I'm in a cavity case, but somehow I'm not able to go back to my cavity folder by giving cd dot dot.
Okay, so you can't go back to your cavity.
Yeah, because I'm in my cavity case run now in my PowerShell.
It's cd space dot dot. Okay.
cd space dot dot. Sorry.
Yeah.
Yeah.
Okay. Okay. I'll just go ahead with, for those of you who've already done this. So you click the apply VTK blocks and you have U, and then I click the play button. Okay. Now, if I want to plot some streamlines of how the flow is going about, so there are multiple ways to do that. Below your U file that you've just clicked, below that you'll find this icon. It says streamlines. So you click that. Okay. So this one will first plot over line, but we don't want a line. We want it to plot over the whole domain. So you do this, you change. So within down here in seeds, you will have a seed type. You click on point source. It will generate this one small circle like spear like thing. Okay. Has everyone got this?
Yeah.
Okay. Then you can change the radius of this spear. Now we want this spear to completely cover this whole domain of ours. So I'll specify it as 0.1 or something. Yeah. So 0.1, you see it is covering the whole domain of ours. Okay. On the left side, you have this small icon to show spear that you can switch on and off. I'll just switch it off. And then below that, you have number of points. Okay. So you see, if I click apply now, if I keep this number of points as 100 and I click apply, it will only make just these many lines. So specify this at around, see, 10,000 or 1 lakh. I put that. You see, it has created some nice lines, streamlines. I'll just put it to 1,000. You see, it has created some nice streamlines of how the flow is happening. So since these sections were a wall, I can show you that also. So you see, this was a wall, the sides, and this top wall is moving. So as it moves, there's some circulation that is happening within this cavity case. Okay. So there's one more way. You can decide the streamline only. there is this glyph also. Yes.
Excuse me. Can you please explain again from the strip? Yeah.
Okay, from Streamline, I'll just delete this. So everyone has this. So over here on top, just below your this U that you have clicked, there's a Streamline tracer. You click that. Okay. Subhash?
Yes, yes. Yeah,
Okay.
please.
Yeah. So then below the apply button, you see the seeds is there.
Yes.
Under that, you have a high resolution line or you have point source. So click on point source.
Yeah.
Then click on the radius that is there on sphere parameters. Okay.
Okay.
And set it to 0.1. Press enter.
Okay.
If you want, you can keep the sphere. I'm just switching off the sphere. There's a on off button over there for sphere.
Okay. Mm-hmm.
Okay, I'll switch it off.
Basically, this defines the area where we will have this,
yes,
the path.
Yes, correct. And the number of points that you want to specify, just specify it as around 1 lakh or 10,000 or something like that. Okay, you specify it as 1 lakh. 1 lakh will make it too many. You specify it as around 10,000. So this way you can get your streamlines.
Okay.
I'll show you one more way in which you can help. It will help you visualize how your flow is going about. Yeah. So you see, the top wall was moving. So based on that, how the flow in the whole cavity is moving around. So you see there's a circulation. So the flow is happening here and then it moves in the circular direction.
Can you just repeat the vector part?
So see, beside the streamline only, there is this globe-like thing. That is your glyph. Okay.
Got that.
Yeah. So you click on that and then in orientation, you click on U. And in scalar array, you click on no scalar array and click apply. So basically what this orientation will do, it is saying that put the vectors according to how the flow is happening. That was for U. And then scaling, basically if I put scaling also to U, it will basically make these arrows. If there's a high velocity, it will make the arrow larger. If there's a lower velocity, it will make it smaller. Okay.
So this is kind of velocity vector.
Yes.
That is plotting. Okay.
Hello.
Yes.
Hello. So,
Yes.
can you just show your like the PowerShell ones like, to get the comments? I missed some comments. I think after I didn't run the so yeah before in the cavity from the cavity case. I just want to take the screenshot.
Okay, so you want the cavity case, right? So first, once you open your cavity case and everything, you type BlockMesh.
Yeah, that is done.
Then after that, you type IcoFoam.
Okay, wait a second. No, before this, like in the cavity, I have typed gedit system BlockMeshDict. So it opened, but it was showing some warning.
That warning it will show, that is normal.
Okay, so after that?
After that, you close that gedit and you type BlockMesh.
BlockMesh, okay.
Yeah. After BlockMesh, you type IcoFoam.
IcoFoam, okay.
And once you're done typing IcoFoam, click type ParaView, ParaFoam. Yeah, basically this command.
So all this is in the same cavity folder, right?
Yes, everything is in the cavity folder only. Okay.
So it's showing no such a file or directory.
Just check.
You mean to say like BlockMesh and IcoFoam, ParaFoam all separately I need to do?
Yeah, the commands are all separately.
In the bash BlockMesh is showing that no such file or directory.
You'll have to just once check your directories whether it is proper and you're in the proper folder.
Yeah, I saw that it's in cavity in system. It's in system. The
Okay.
BlockMeshDict.
So you don't have to go within your system. Go out of your system. Do cd dot dot, cd space dot dot.
Okay.
And now you will be in your cavity folder.
But I can see in my PowerShell that I was already in the cavity folder.
Yes, so you have to be in your cavity folder only. All the commands that you're running, that will be within your cavity folder itself. You don't have to go within your system folder and type those commands.
Can I open a new PowerShell and from the cavity folder itself?
See, in your PowerShell, you've typed WSL.
Yeah, it is. WSL, yes.
And now it is open proper Ubuntu environment, OpenFOAM environment. Now once you go into your cavity folder, run the set of commands that I told you, and through that it should run fine. Okay.
Okay.
If someone else had a doubt.
Sir, I was trying glyph.
Okay.
Sir, I
So
do have the same
mismatched
issue, sir.
attributes. U is a point attribute, whereas U is a self.
It's okay. You can always see some videos on glyph and all. I was just showing you how to basically to help you all visualize the whole flow, how it is going on. You don't have to necessarily do that. Okay. I'll just show you all how the meshing was. So you see, this is a uniform mesh. And you see in the Z direction, we've only given a distance of 1. So because we don't want to compute anything in that Z direction.
Excuse me, sir.
Yes, Siddharth.
Yeah, the block mesh error is still not rectified actually. It's showing that there's an unexpected line on an unexpected word on line 19 or something of that sort.
Okay, so you can open your BlockMeshDict and go to line number 19 and see if there's anything typed wrong or something.
Okay, that's the only error, right? Because I checked there also, but I don't seem to see anything.
Okay, just confirm if there is some semicolon or something missing.
Okay, fine. I'll just.
Yeah, because just check, because like normal C++ code, if your semicolon or something is missing, it will give you an error. Sometimes by mistake, if you backspaced it or something, that might be the problem.
Excuse me, sir. So actually, I'm running with that OpenFOAM. Mine is 2024 actually. In that folder, that the cavity in cavity, it is a BlockMeshDict folder is there.
Yes.
Whatever you showed. Okay. I'm running with this command, that BlockMeshDict. It won't.
No, you don't have to run BlockMeshDict. You have to run BlockMesh.
The BlockMesh.
Yes, only BlockMesh.
Can you just scroll up to show so that you can show the command in the cavity? Yes, in the cavity folder for the block mesh.
Can you?
Okay,
Yes,
okay.
yes. Hello.
So you type BlockMesh.
Block. Yeah. Then after that, I have to run.
Yeah. After that, if you want to run your simulation, then you type IcoFoam.
Okay. Yeah. Then. Then after that, ParaForm.
Yes, after that, ParaForm.
Hi, everyone. Another question.
Yes.
So, do we have to be case specific when we are trying to type in block mesh? Could our M be uppercase or could it be lowercase? Is it acceptable to do it anyways, or does it have to be specifically uppercase?
No, the thing is that in OpenFOAM, you will always have the very first letter small, and then if there's a new word, like I have para and then foam, then the word that is following another thing, we always capitalize it. So even in BlockMesh, the M will always be capital. In IcoFoam, the F will always be capital. In ParaFoam also, F will always be capital.
So it is sensitive to the case,
Yeah,
right?
because in
Okay.
yes, because in the back end they've typed it as when you type block mesh, that time only the meshing will happen. So that keyword is already specified in the back end. So you can't just type anything you want.
Okay, thank you.
Sir, right now I'm in ParaView.
Yes.
Can you say it again, please?
Yeah.
Sorry.
Okay, I'll show you again. In ParaFoam or ParaView, you can click this green apply button on the left. That will load your case.
Yes.
Okay. And then you can click on the top left corner. You see this VTK blocks. You click on U. And then you click the play button. So you can visualize your contours. Okay. Now, if you want to see some streamlines, just below that U, you have this streamline tracer option. So you click that. Okay.
Maybe mine is somewhat different to yours.
Yeah, that the version of ParaView might also make a difference. So you can always check these because as long as you can see your contours and all, that is fine. Streamlines and all, it must be kept somewhere else in your version. So always you can see some videos or something. Those are readily available always. So see, there's another way you can open the streamline. On top, you have these some options. You have like file, edit, view. Can see those?
Yes.
Yeah. So click on filter. Okay. And on filter, go down to alphabetical.
Okay.
See, on alphabetical, then it will open all these other options. So you go to S and you see the stream tracer. You can click from here also. Okay. Once you, yeah. So once you click on that, you can scroll down. You can see seeds. Can you see the seeds option?
Yes, sir.
Yeah. So instead of high resolution line, click on point source. So it will make this sphere appear. Yeah. So you can change the radius of the sphere. There are the sphere parameters. Just change it to 0.1 and type enter. So it will make it large. Okay.
Yes.
So then you can switch off the sphere if you want. If you want to keep it on also, you can keep it on. Below the sphere parameters, there is this number of points. Okay. So change that to around 10,000. Okay. Once you're done with that, click apply. It will make your streamlines.
Thank you.
Okay. Yeah.
Excuse me.
Sir, one more thing in like post processing itself.
Yes.
Like suppose I want to have a velocity profile at the maybe at some cross section itself. Like this is itself a cross section,
Yeah.
but if I want to draw a velocity profile at a particular maybe line.
Yeah.
So
So
like
there is
in
so there is a velocity this plot over line option. I'll show you all when we are doing the conduction case.
Okay. Sir.
I'll show you all then. Wait 1 second. See.
Excuse me, sir.
We have to mention somewhere where we want to draw the profile. So that line itself, and from there maybe an extraction of data from there maybe we can do.
Sorry.
Like suppose I want to draw the velocity profile. I want to get that data, and from there like first maybe post processing in some other cases. So that can be done.
So that see Ismail, those things I will show you in the conduction case.
Okay.
Because now Manzil will start with the turbulence case. We're already behind schedule. Okay. Yeah.
Okay, sir.
Excuse me, sir.
Yes.
Sir, I checked the BlockMesh directory again, and then there is no error in the code. It's the same as what you have typed or what changes whatever you have made. It's the same thing.
Okay.
And it's still showing the error.
Could you just type in your BlockMesh in the chat? I will just check it once because Manzil will start with this one turbulence module.
Fine.
Okay? Yeah.
Sure.
Also,
Manzil,
one more thing, like how we can save this file. Like there will be some file that will be saved, and maybe we can. It's already saved in the folder itself, right?
Yes.
The result is saved only. Yeah.
Yes, the result is always saved.
Okay.
Manzil, you can go ahead.
Okay, thank you, Ivan.
Yeah. Sorry for the delay.
It's okay.
So good afternoon, everyone. It's me, Manjul Sitaula. This is assistant at FOSSEE. So welcome you all to the basic CFD workshop in OpenFOAM. So I think I've been disabled to share my screen. Can you, the host can enable that?
Yes, sir. You can share now.
Okay, fine. Okay, is my screen visible?
Yes, sir.
Yeah. So welcome you all to the basic level CFD workshop using OpenFOAM. So this training is aimed to be a beginner level training session. It is aimed for the beginners, and these tutorials will be done in the foundation version of OpenFOAM, that is OpenFOAM version 9. So actually there are two versions, that is .org and .com version. So we are going with the foundation version. So if you have any queries, then please feel free to post a query in the chat as well as during the session. So the basic outline of this tutorial is that we will go through the basic process of CFD. This will be a brief overview, and then we will be simulating 2D laminar flow in a channel, and then we'll move on to the simulating the turbulent flow in the channel. So our problem definition. So we want to set up a case for the laminar flow through the channel first, then change our regime to the turbulent flow using K epsilon and K omega model. And then we want to post-process the results in ParaView. So I will just brief this the CFD process. So as Professor Nani has already described the in details about the process of CFD. So basically, the first process will include the domain modeling and physical modeling. So this means that we need to have a basic mind map of what we want to achieve or what physical phenomena that we are simulating and what are the possible outcomes that we want to achieve. So if our physical process depends only on the 2D or the in 2 dimension, or the flow is changing in the 2D streamwise direction only, and there is no changes in the span-wise direction, so we can simplify our 3D domain into the 2D domain. So this comes under domain modeling, or else we can also use symmetry planes, like to if the flow is symmetrical, so we can use the symmetry plane. So that also comes under domain modeling. So basically, before we start the simulation, we need to have the mind makeup of what we want to achieve. And the physical modeling is simply it means that how we want to represent our physical process in terms of mathematical equations and mathematical representations. So suppose if we have a heater or we want to simulate a case with heater, then we don't want like a physical component heater in our simulation. We can just replace that with the appropriate boundary conditions. That is, we can use the temperature boundary conditions instead of using the heater as a physical component. So this comes under, this is the first process that we want to do before we dive into the simulation part. So after we are ready with this, that after we have a mind map of what we want to do and what we want to achieve, then we will move on to these next step, that is the domain discretization, which is also referred to as meshing or grid. We can call it the grid generation process. So it is the grids where we solve our equations. So basically, we have our equations in the PDE forms or differential equations form, but we cannot solve it directly in that form. We must make it converted into the algebraic equations that I think you have already had a lecture on the first lesson. So the third process is the equations discretization. That is, we are converting the process of that we are converting the PDEs into algebraic equations, and we form the matrix system of a matrix with the global matrix, local matrix. And in order to solve that matrix and find our unknown variables, we need to find a solution method for that. So that is So that comes from the solution method, like how we want to solve that matrix. So it may be like the Gauss-Seidel methods and so on. So moving on to the case structure, I think I don't need to explain much on the case structure. So we'll eventually get to these case structure and folders in a short while. So you can see a brief overview there with what files are included in which folders. So 0 and .ori contains initial and boundary condition files, whereas the constant contains the physical properties, as transport properties. It contains solvent properties. It contains the mesh files after mesh is generated. So system allows us to control our different parameters. So in system we have control dict, BlockMeshDict, every schemes, every solution. So in control dict we have the we can assign time steps, end time, output controls can be provided in the control dict. So we will eventually see this while we dive deeper into the simulation in the case setup. So as I've already said that before we run the simulation, we need to have a mind map and mind makeup like what we want to achieve. So first of all, we are doing it in a 2D. We are doing a 2D simulation. This is the first step. So our 3D that the dimensions in the 3D direction or the in the Z direction do not affect our simulation. So this is basically the 2D simulation. And next is we are doing a laminar flow simulation first. So the laminar flow includes that we are doing the Reynolds number in that is less than the critical Reynolds number. So this Reynolds number should be in the laminar regime. So according to our Reynolds number, we will calculate our average velocity, that is our inlet velocity, and our kinetic viscosity is also provided. So you can see in this slide. So all the values, and we have calculated U average using Reynolds number of 500. So L determines the characteristic length. So in this in our simulation, we have used height, that is 1 meter, as the characteristic length. So basically, there is also a concept of hydraulic diameter. So this is but when the width, that is the 65 meter is very large than the height, then we can just use the height as the characteristic length. Otherwise, we can also otherwise if it is more like a square shape, then we can use the concept of hydraulic diameter as well. So from the Reynolds number of 500, I've calculated U average. So you can also calculate this on your own using the calculator. So you will get a U average at 0.005, and then we will use these values in the boundary conditions. Okay, the next part is the domain discretization. So basically, before moving into how to discretize our domain, so I would like you to go to one of the site and download some files so that it will be easy for me to explain. So please visit the spoken tutorials website of FOSSEE. So just type spoken tutorial FOSSEE in your web browser. So you will be directed to this interface, that is this page, and you can see that we have spoken tutorials that that is made by FOSSEE. Just click in the spokentutorial.org in this website and get inside the website. Is my audio clear to all of you?
Yes, sir.
Okay.
Yes, sir.
I think it is not loading.
Hello. Is this session about turbulence application of turbulence module in the
Hmm.
OpenFOAM? Okay.
Yeah, first we will do with the laminar regime, and then we'll move on to the turbulent regime.
Okay.
So I think this website is not working now. It's on this website. Okay, so let's move on to the slides. Actually, I wanted you all to download a file from this website.
Mr. Manjil, I think the second link is open.
Yes.
I think the second link is open. Can you hear me? Mr. Manjil, we are not able to hear you.
Okay, it's working now. Okay, fine. So basically, you type spoken tutorials in your web browser first, spoken tutorials FOSSEE, and then you can go on to this second website, that is cfd.fossee.in. As you can see, not the first one. The first one is I think it is running slow. So let's go into the second one, spoken tutorials CFD FOSSEE. So click on that. So you'll be directed to this page. So at the bottom, I think there is when you can see at the left side of the page, there is a green highlighted with the spoken tutorial. So please click on that spoken tutorial. So under the lab migration project, so there is written with green highlighted. It is a spoken tutorial. So just click on that. So you will get directed to this page. So this is spoken tutorials page. So you can see that you can go. Here is the click here to access the OpenFOAM spoken tutorials. That is here in the second last link, I think, above the to install OpenFOAM 7. So there is one. Click here to access the OpenFOAM spoken tutorial. Just click there and wait for some time. So you are directed to the spoken tutorials, the tutorials for the OpenFOAM that is made by FOSSEE. So you can see here all the tutorials that are available to learn OpenFOAM. So I want you to go to the ninth tutorial, that is simulation of a 2D turbulent flow in a channel using OpenFOAM. So just click on that. So I think all of you are following me. If anybody is lagging, then please ask me to wait or repeat it. Okay. Now you will be directed to this space where you will also have a video of the tutorial case. So you can always look at it after the in your free time or after this workshop also. There are many other tutorial cases also available in this website. So scroll down, and at the right hand side you can see that there is a code file name. There is a interface in where there is code files and there are files available. So just click on that code files. So after you click on code files, you can see that the code files are downloaded. So it must be located in some in your download folder. So just unzip this. Okay. So extract this. So after extracting, now you can see that we have a 0 constant and system folder inside that. So this is the basic structure of OpenFOAM. So I think you have downloaded this, and you can, after downloading, you can access it inside that. So you can see that there are 0 constant and system folders inside those in these files. So what I want you to do is just go to system and the BlockMeshDict file, because we need to first make the mesh, then proceed to the simulation part. So first we'll look at the BlockMesh, how to generate mesh. So just open your BlockMeshDict file. Okay. Okay, now I'll show you my slide along with this. So actually, in this downloaded one, there is no mention of 0, 1 to vertex, but for the ease of understanding to the users, I have created a separate file, but the coordinates, all the files are same. But just for you to understand, I have commented out some things. So the file is same. Right, let me do this. So what I want to say is that these and these files are same, but what I have included is I have commented some vertex number in this, so that it will be easy for you to understand. So
Sir, increase the font size, please.
Okay. So this is not actually required. This is a comment. This will not be executed because we have commented it. So this is for you to understand. So now let's look at this slide and this. Okay. So first of all, before doing that, let me help you visualize how is our flow and from which direction is the flow moving. What is our flow direction? So we can see that in this 3D domain that we have an inlet face here shown by this cursor and outlet face at these faces. So they are all together: inlet face, outlet face, the back face, at the back of these 3D domain, and these block 1 and block 2 as the front face. So we also have the top face and the bottom face, but I have not written yet the names, but there is also a top face and the bottom face. So we can see that the flow is coming from this direction where there is inlet and the flow, and in this face there is outlet. So you have already learned to make the domain using a single block, but now we are making a block 2 over block 1. So basically, to make a single block, so let's first look how to make a single block. So in order to make a rectangular block, how many coordinates do we need? Actually, we need 1, 2, 3. That is this coordinate, this coordinate, this one. That is the 4 coordinate in the front face and the 4 coordinates in the back face. So actually, in the front face we have 0, 1, 2, 3. So I have named this 0, this coordinate as 0, this coordinate as 1, this coordinate as 2, and this coordinate as 3. So after I have named in the front face using this 0, 1, 2, 3, now I also need to assign the coordinate that is the x, y, z of these coordinates. So actually this is just naming of the coordinate 0. This I refer to this as 0 coordinate, I refer to this as 1 coordinate, I refer to this as 0 coordinate, but they have their own x, y, and z points. So in order to make this block 1, we need actually 8 coordinates. That is the front 4 coordinates, and there is also a back face at the back which requires 4 coordinates. And after we join this front and back face, then we will be able to create a block. That is, we will be able to create block 1. Similarly, for block 2, we need this coordinate, this one, and this one in the front face, as well as in the back face. We need 4 coordinates. So at this I have written 0, 6. So this referred to as 0 is at the front face and 6 is at the back face. So I think you are getting this. And this 1 is at the front face and 7 is at the back face. And this 2 is at the front face and 8 is at the back face. but we can see that the between 4 coordinates are shared by 2 blocks. So we can see that we can use the same coordinates 2, 8 and 3, 9 to make 2 blocks. That is because these coordinates are being shared between these blocks. So in this way, we can make block 1 and block 2. Now let's move on to our BlockMesh file. So you can see that now okay. So you can see that the 0 coordinate that is I have named as 0, that is the origin 0, 0, 0. Now the 1, I have named it as 1 coordinate, that is this coordinate, which is in the front plane, that is 0 plane. So this 0 represents z direction. Now in the back plane, that is in the z direction of 0.1. I think you can visualize this. So this 0.1 is at the z axis and at a distance of 0.1, the back plane. So the first coordinate is 0, 0, 0, right? The first that the 1 number coordinate would be 65. That is x-axis it is in 65, and y-axis it is still 0, and it is at the front plane. So the z direction will also be, the z coordinates will also be 0. But now we move on to the 2 number coordinate. That is this coordinate, 2 number coordinate in the front plane. Actually 8 number coordinate is in the back plane. That is in the z 0.1 distance. But 2 is in the front plane. So 2, we can see that how can we give the coordinates for 2? That is, we can provide it as x-axis it is still at 0, but in y-axis it has moved some distance of 0.5. So actually we have a total distance of 1 in the y-axis, but after after doing it half, we have 0.5 and 0.5. So the coordinate of 2 would be 0, that is x-axis is in 0, and y would be 0.5, and z is 0, that is it is in the front plane. That is the number 2 coordinate. Similarly, number 3 coordinate would be this, that is x-axis 65, y-axis 0.5, and it is in the front plane, that is at 0. So similarly, after we complete the front plane 0, 1, 2, 3, 4, 5, now we move on to the back plane coordinates, that is number 6 coordinate. So 6 number coordinates, you can see there here that we are moving now z to 0.1, that is we are doing for the back plane. So it would be the same as 0, 1, 2, 3, 4, 5, but we will just keep z as 0.1. So actually these are the same coordinates but in the back plane. So just we can change the coordinates of z to incorporate this effect without changing the other x and y coordinates. So I think you understood this, how these coordinates are formed and how blocks are created. So we can, to create block 1, we need 0, 6, 1, 7, 2, 8 and 3, 9 coordinates, that is 6 coordinates. Similarly, to create block 2, we need 2, 8, 3, 9, 4, 10 and 5, 11 coordinates. Actually this 5, 11, this is for nomenclature, just to for the users to understand. You don't have to do and comment down 0, 1, 2, 3, but it would be easy if you, for the beginners, if you can do this way. Okay, now we need to create a block. We have assigned our coordinate. Our coordinates are ready of all the vertices are ready. That is, to make a block we need vertices. So our vertices are ready with the prescribed coordinates. Now we need to use these coordinates to create this block. So now I want to create block 1. So what is block 1? So using these coordinates. So at the front plane we have 0, 1, 2, 0, 1, 3, 2. Actually, to make the blocks, the convention is you move in the anti-clockwise direction or you move in the clockwise direction. That does not matter, but you have to follow the same convention in both the blocks. So
excuse me, Manjit, sorry to interrupt you. So it's already 1:15, almost 1:14 now. So maybe after 2 minutes we can take a lunch break and then we'll come back and continue.
Okay, ma'am. So I will finish this BlockMesh, then we can, I think, have a break.
So another 5 minutes. What do you think?
Yeah. Another 5 minutes will be fine.
Okay, fine. Thanks.
Okay. You can now see that to create block 1, we need the coordinate of 0, 1, 3, 2. That is, first we will include the front face, that is the front plane coordinates, and then we will include the back face coordinate, that is 6, 7, 9 and 8. But we can see that 0, 1, 3, 2, that in that convention only we need to assign the back plane coordinates also, 6, 7, 9, 8. We cannot do 6, 7, 8 and 9 because we have done 0, 1, 3, 2, right? If we had done 0, 1, 2, 3, that is 0, 1, 2, 3, then we could have done 6, 7, 8 and 9, that is 6, 7, 8, 9.
but we need to follow the same convention while creating the blocks. Similarly for, okay, I have created the first block, that is 0, 1, 3, 2, and 6, 7, 9, 8. Now this, after that, this after you assign the coordinates to the block, now you have to assign how many grids you want to generate on that block. So this is the x-axis grid, this is the y-axis grid, and this is the z-axis grid. So I have already said that we are doing a 2D simulation, and that was our first step that we have already processed. So we don't want to simulate in the z direction. That is, the z direction won't affect our flows, that won't affect our results. So we can just assign any value of z coordinates. So I have assigned here 0.1. You can assign it at 0.2, 0.3, 1, 2. That won't affect our 2D simulation. And you can assign any coordinate number here, 1, 2, 3, 4. That won't affect our simulation, because we are only trying to do a 2D simulation, not a 3D simulation. Okay, I think you understood how to make a block, and these are the number of grids in the, that is, I need to make 75 grids in the x direction. I need to make 30 grids, or we can 30 boxes in the y direction, and a single grid in the z direction. And okay, so after that I am doing a simple grading. So simple grading means that so for the laminar case, okay, for the laminar case, I think you have already now I don't need to show the slide that we have made the blocks out. You know how to make the blocks. So let's move on to the grading. So grading actually means like biasing in ANSYS. We have bias factors in ANSYS. So if you want to capture the gradients at the boundary layer effectively, then you need a very fine mesh at the boundary, and you can have a coarse mesh near the center of the flow. So our if it is rectangular, we have a rectangular channel, so we have to make a very fine mesh to capture the velocity gradients or the gradient values in the near the walls. We can have a coarse mesh at the center. So this simple grading will help to control these size of meshes near the walls or at the center. So basically, for the now at the first case, what we want to do is we just want to do a laminar simulation with just simple grading of 1, 1, 1. So this means that our grid size is uniform along all these blocks. That is, it won't all the sizes of the mesh will be similar. So if the mesh is if one of the mesh is like 0.1 meter, then another mesh in the x direction would also be 0.1 meter. So this is a uniform grading if you provide 1, 1, 1 or 1, 1 and 1, 1, 1. So I will stick with this for now. I want to do a laminar case now, and I will change it, and I'll show you how to change these values also, so to make a growth layer or to make a biasing in the y direction, which we will do for the turbulent cases. And we should also do for the laminar case, because we want to capture the velocity gradient, and there is a boundary layer formation in the laminar case as well. But for the basic understanding, I am just sticking to the uniform simple grading now. Okay, now after we make the blocks, we have made block 1, and this is for block 2. So we have completed to make our block. So edges, we don't have any arcs in our domain. So you can see that from the BlockMeshDict, we can create the CAD model as well as we can mesh it inside this BlockMeshDict. So we don't want any CAD model from outside or third-party software. We have just created a model that is a 2D CAD model, and now we have also made a mesh for this. So using this number of cells. So this is what BlockMesh can do. So you can make a mesh without having to import any CAD models like in third-party software, where you have to make a CAD model first, then export it in the import it in the different software and such things which have to be done. But here we are creating the domain and meshing it inside the BlockMeshDict all together. So the edges are not required. Now for the boundary, so you can see that we have created the boundary names at lower wall, upper wall, inlet, outlet, and front and back. So you can see at this presentation that there are altogether 6 faces. That is the inlet,
outlet. So it is inlet, outlet, and we have front and back. That is we have written block 1 and block 2. It is the front face, and this is the back face, and this is the upper wall, and the below is the lower wall. So now, if you there is also a convention for writing these boundaries. Okay, now we have named our boundaries as these lower wall, upper wall, and we can see that the walls are of type wall, whereas the inlet and outlet are of type patch. So whatever is not a wall is a patch. So if there is no wall, then you need to keep it as type patch. So inlet and outlet, we have assigned patch, and for the walls we have assigned the wall boundary condition, and for front and back we have assigned empty, because this is our 2D simulation. We are not interested in the span-wise effect. So we are also stream-wise. We are only considering the stream-wise direction. So we have just kept front and back as empty. Now how do you name this using these coordinates? So actually all this we need to do it using the coordinate that we have used here, the number of coordinates. So we'll start from 0. This is 0 coordinate, this is 1 coordinate, this is 2 coordinate, and using this coordinates we need to create block, and using this coordinate we need to assign the faces as well. So you can see that. Okay, let me teach first from the inlet face, because it will from the inlet face it will be easy. So you can see that actually inlet face is this face, right? This is, but this is in a 2D, so you need to visualize in these. There is also face in the span-wise direction, in the span direction. So using this 0, 6, 2, 8, and 4 and 10, using the 6 coordinates 0, 6, 2, 8, 4, 10, we need to define our inlet face. So you can see that we have defined 0, 6, 8, 2, 2, 8, 10. For using these 4 coordinates only, we have declared we have made our inlet face. But there is a convention for that. So what we have done is 0, 6, 8, 2. So 0 is in the front plane, 6 is in the back plane, 2 is in the front plane, 8 is in the back plane. So what we can do is you can use a right hand rule. So, and you can point your thumb either outside or either inside. So if you point your thumb outside, then you need to follow this convention throughout when you assign the faces. And if you point your thumb inside, then you need to use this convention while doing for the other boundaries as well. So here you can see that 0, 6, 8, 2. We are doing it. We are pointing our thumb inside while doing this convention. So 0 is in the front plane, 6 is in the back plane, 8 is also in the back plane, and 2 is in the front plane. So if you using right hand rule, if you call your fingers in this direction 0, 6, 8, 2, then you can see that your thumb will be pointing inwards of these inwards of these edges or of these faces.
Excuse me, Manzil.
Yes.
Sorry to interrupt, but I have already explained all of the face and all that to them, so you can directly go to the meshing part. That will save some time also. Okay.
Okay, fine. So that means that you need I should we do some time limitation.
I've already given them an overview of how to specify the points in BlockMesh, and the case structure and everything is already specified to them. So you can go ahead with the remaining things. Okay.
Okay, fine, Ivan.
Yeah.
So you can see that we have we know how to create a mesh or to disguise our domain using these coordinates and all this. So now I'll not dive deeper into these, how to do these conventions and nomenclatures. So after our block mesh is ready, now we are ready to generate mesh.
Manzil.
Yes.
Can we do the meshing and all later, like the hands-on part? Because
okay.
want
Yeah,
to
we can do that
lunch.
later. Yeah. Okay, then we can do this in the next session after our lunch. We will start with meshing process and then do the hands-on session after lunch break.
So
it's 1:25 now. So if we take a lunch break for 1 hour, we should come back at 2:25. So should we take 1 hour break or 45 minutes? You please suggest.
I think 45 minutes would also be fine for the break.
Yeah, 1 hour.
1 hour, right? Because
Okay,
some
okay.
people may have to walk to the
Yeah,
hostel
missus.
and come back.
Okay,
Yes,
okay.
yes. So 1 hour we can take. Then in that case, in the evening, please stay with us for half an hour more.
Yeah, no problem, no problem.
Okay, okay. So we are coming back around 2:25 then. And
Okay.
please don't be late. Please try to join around 2:20 so that exactly on 2:25 we can continue.
Okay, definitely.
Okay, okay. Thank you so much. You can leave the meeting now and rejoin. Okay, so welcome back. Hello. Yeah, so welcome back after the lunch break. So we will be starting at 2:25 sharply. Manjil is here. So yeah, so from the session that was taken by Evan and Manjil, if you want to have a quick chat with them to clear your doubts, you can go ahead. We have 3 minutes more. So if you have some quick questions, we can take it, and then 2:25 sharp, we'll start.
Hello, ma'am. Am I audible?
Yes, Aditya.
I had a doubt actually. My terminal, see, in the terminal, whenever we type a command, there's a username written in green color always at each line. So what is happening is at times it just goes away and the commands I'm not able to run. Then I have to restart it again and type all the commands. So I'm missing out most of the part of the session, what is going on. So is there any fix to this?
Do you have any answer, Evan, Manjil?
So Aditya, you're on OpenFOAM 9 only, no?
I'm on 12, OpenFOAM 12.
Okay. And your Windows is Windows 11 or 10?
11.
Okay. You know what? Try installing OpenFOAM 9 and see if the problem persists. If after that also it is going on, then we will have to see that, because in OpenFOAM 12 exactly that issue, why is it coming, it I don't exactly know, but in 9 it shouldn't come, that's for sure.
Okay, fine.
Yeah, because maybe that WSL and your OpenFOAM might not be able to link properly, or some issues there with that. That's why midway only it is basically disconnecting itself. That could be one
Okay.
problem.
Okay.
Because if from the terminal only your user ID is switching off in the middle, that does not happen. Because we have not seen this error ever happen. Usually it is either WSL will not work completely or your OpenFOAM might really not work completely. It is not like it's working half and after it stops then.
Okay, fine. Understood.
Yeah. Just try reinstalling OpenFOAM 9 and see if that thing again comes. Okay.
Okay, thanks. Okay.
Yeah.
Okay, thanks, Evan. So Manjil, we can continue. There are only 63 participants, so they will be coming in. But then if you don't start now, we'll be late. So let us start.
Okay, ma'am. So welcome back, everyone. Okay, now let's begin where we left off. So we had actually, I think my screen is visible, right?
Yes, Manjil.
Yes.
Okay, and my sound is also audible. Is it clear?
Yes, Manjil, everything's fine.
Okay. So we have left off here after finishing our block mesh or mesh generation. Now we'll start setting up our case. Now I would like you, all of you, to open your terminal. So basically, you can just open Ubuntu. So I think all of you have opened Ubuntu. Now I will type one command. This is because I have different versions of OpenFOAM installed, and I have LAS, the OpenFOAM 9 version with OP9. So I'm typing this. But if you have only a single version installed, you don't need this command. Okay. After this, now follow me with these steps. So type run. So if you type run, then you'll be directed to the run directory that
Manjil,
we
can you
have
increase the
created.
font size?
Okay. Okay. So you can see that after typing run, you will be redirected to the run directory. And if you type ls, then you can see that this in my run directory, I have multiple files or multiple folders, but in your run directory, there is only, I think, cavity case. So let's create one more directory in this run folder. So let's create a directory called Laminar. So type this command mkdir laminar. So we are creating a new folder in the run folder. So now if you do ls, then you can see that a new folder called laminar is created. So you can, I think it is also visible in your terminal. Now we want to copy a test case to this laminar so that we can edit that template. So let's use the previous case as our template case. So what I would like you to do is, I would like you all to type this command to copy from the cavity case to the laminar case. So before doing this, you can also get inside to the laminar folder. So just type cd laminar. So now you are inside the laminar folder that you have just created. Now we want to copy from cavity case to our laminar folder, right? So we need to type cpr. So where is our laminar? Now where is our cavity case? It is inside run, inside the cavity case. So just copy this address, location path, then right click, it will paste in the terminal. Just right click will paste this. Now we want cavity case, right? So just type cavity cavity case. And inside the cavity case, there is another folder called cavity inside your cavity case. Okay, now we want the zero system constant that is inside the cavity to be copied in our laminar folder which we have created. So to do this, just put an asterisk and put a space and then dot. So this will copy the folders that is inside the cavity folder, which is inside cavity case, in the laminar folder. So if you do this, so all of you follow this first. So basically I've copied this location here and then use an asterisk. So why I use asterisk is because I want to copy, there are different folders inside cavity, right? Zero, constant, and system. There are 3 folders. So I want to copy that 3 folders in my laminar folder which I have created, and we want to run the simulation on this folder. So after this, press enter. So after this, if you press enter and then you do ls, you can see that you have copied the zero, constant, and system from the case that you have run. But I think there are other folders inside the cavity because you have already run the simulation, right? So what you can do is, before copying, you can do foam clean case. After copying, you can do foam clean case or foam clean tutorials if that works, and it will delete all the other folders. So type this command. Because I have not run the cavity case, so I have only zero, constant, and system folder inside the cavity. But if you have run the case, then there will be additional time folders. So we don't want that for now. So after you copy, just run foam clean tutorials and see if that will clean everything except zero, constant, and system, and let me know. And do ls. So if that cleans or not, one of you can just reply me. I think everyone is following me on this. So if I'm a bit faster, then please let me know. Okay, you can ask your questions by unmuting yourself.
Actually, I couldn't join earlier due to connectivity. I was just asking, is this I mean, did I miss anything, or is this the first? I mean,
No, we have just started I think it's just 5 minutes after we started. This is the first terminal that I'm running.
Okay.
So from the MK.
Okay. So I tried up to CP dash R, and it says that it cannot. I mean, no such files on the directory.
Which what?
Followed every command. That's CP line. Yeah, that one.
CP.
Yeah.
So actually, what you can do is CPR and then the location of your folder, that is the cavity folder. So in my, it is located in OpenFOAM Manjil 9. This is the username. Run, and inside that run there is cavity case, and inside the
Do I
cavity
have
case there
to
is
put the
cavity.
No, I don't. Okay. Okay, understood.
You should not include Manjil 9. It should be your own location.
Yeah, I got that. Thank you.
So anybody have any problem in this, or have you followed up till now? One of you can, if you have problem, you are facing problem, you can unmute yourself and ask me. So I think everybody inside the Laminar folder, you have Zero, constant, and system folder. So now you can also see this by going in from the file explorer section. So if you go inside Ubuntu, inside your home, inside this, and so let me make this. Okay. So inside this, if you go to OpenFOAM, and you have your own folder that is created, and inside your own folder you have your Laminar case that we have just created, and inside the Laminar case you will have Zero, constant, and system folder. So everyone is followed till now. Please raise your hand and ask questions if you have not.
Inside Laminar flow, the folder is empty.
Sorry, what did you say?
I typed the same as you said, but inside Laminar flow, our home, this folder is empty. It is showing.
It is empty.
Yeah.
So did you run this command cpr gravity to?
Hello.
Yes, I did. But
So
yes.
Okay,
this shows that no such file directory.
Manjil.
Yes.
You can show them how to copy it manually only, since they must have saved it in different locations. Some of them must have kept it in their downloads or not. So you can just show them how to manually copy and paste it in the file explorer itself.
Okay.
Actually, when I did ls, mine shows 0, 0.1, 0.2, but yours shows only 0, constant, and system. So
okay, did you run foam clean tutorials?
No, I didn't.
You try this and say try this command first.
Hello. Is it
And
possible
do
to
ls.
hello? Is it possible
Yes,
for you
yes.
to show again how to create the Hagen-Poisson parabolic one in the run folder? Like,
No. We are not dealing with the Hagen-Poisson flow. We are just this I have kept in here because I had run the simulation earlier.
those are already run. Right.
These are not. This will not be in your run folder.
Yes.
You
So
will
now,
only have the cases that.
so in run, I will write CD laminar, right?
Yeah, no. Okay. Let me start from the first. So just type run at first. So this will direct you to your run folder, right?
Sir, I have joined now only. So like earlier, my command is showing like earlier whatever you have shown that for the case of what was the case? Cavity
Okay.
case.
I will start
From there.
it
Okay.
from first again. So everybody, please follow me on this. So after you open the terminal, just you need to type run. So you will be directed to the run folder. Okay. After that, just type ls. Now, if you type ls, then you can see that I have multiple other folders because I have run many simulations in this inside this run folder. But in your case, there should only be cavity case, right? So that is inside, when you go inside the run folder, that is in Ubuntu, home, and then OpenFOAM. Inside this run folder, there will only be cavity case. So if you type this command,
Yeah, I can see like I have here cavity case and PIDS daily. That was yesterday.
okay,
That
that
was
was
the model. Okay.
yeah. That will be, that two folders will be there,
Yeah.
but apart from that, there will be no additional folders. So what I want you to do is just create one folder called Laminar by running this command. So press enter. Now we will what we are doing is we are creating a Laminar folder. But I have already created a folder called Laminar, so it said that cannot create directory. If you have not created, then just type mkdir Laminar.
I'm sorry to interrupt, but could you please explain what that command form clean tutorials do exactly?
So after you ran the complaint tutorials, did all of the time step vanish or not?
Okay, it clears the time step data, right?
Yeah. So actually, what it does is it will revert it back to the original configuration that was previously. So it would clean all the files. It is like cleaning the folder and only keeping the original folders in this folder in the system. So the simulation that you have run, it will clear all those time steps and all the simulation data by this command.
Okay, understood. Thank you.
So I think you have all created a folder called Laminar.
Understood. Thank you.
Okay, fine. So you have created a folder called Laminar. So if you do ls, then there should be like a folder that is called Laminar being generated.
Hello, Manjil.
Yes.
John here. So I think on the terminal, because your username is different, their username is different, people are making mistakes. So can you show them by the GUI version only, like from the folder only, create and just copy? That will be much simpler, I guess. Or
Okay,
are some of them? Yeah. Here only you show them, because what is happening is otherwise everybody has different username and they don't know what they are doing. So here it will be much quicker.
Okay, sir. Okay, so what now apart from the terminal, you can do it manually as well, like copying the folders. So in your run folder, you must have cavity case, right? And you have also created a folder called Laminar. So in your run directory, there must be this cavity case, and then there must be a folder called Laminar. And if in another folder, it might be piece daily, which you have created yesterday. So what I want to do is copy this zero constant and system, only the zero constant and system, not the other time directories, just the original folder, that is zero constant and system. Just copy, and then after you have created a folder called Laminar, then you just paste it here. But by doing this, you can see that some additional files are being generated. So you can just delete this, because this but when you do it manually, this kind of files get generated.
Just a quick question, like I wanted to know, like should I copy the zero constant system from the cavity case or cavity, or does it make any difference?
No, we are just using as a template case, so you can just copy from cavity only the zero constant system inside the cavity case.
Okay.
So have you all done up to this? Like you have copied?
Yeah.
So you can. Okay. So
I
I
mean,
think.
if time allows, if time allows, could you please show me how I can do that using the terminal? I mean, copy the zero and the other folders.
I think Manjil, for if you want to complete the tutorial, it will just keep delaying. So see, there are simple commands you can do that. You can search online. Let Manjil finish. Otherwise, he will not be able to demonstrate. He has to demonstrate a laminar case as well as a turbulent case. So I think it is just basic copy paste so that you can see the other things that are important things will be left out if you keep interrupting it. Yeah.
Sure, answer.
Okay. So you can see these afterwards. So you can see that by manually copying, we can see that an additional folders will be created. So you can just delete them. Now we have in the 0 we have P and U, and in the constant we have transfer properties, and in the system we have our BlockMeshDict control every skin and every solution. So now what I wanted to do is that I have asked you to download from this website some code files like simulation of turbulent flow in a 2D channel. I have asked you to download these code files. So you go to that specific location where you have your downloaded code files. So actually I had my in the download section, and I had extracted this on this. So this is our case. So you can see that in the constant folder, we have another folder called Turbulence properties. So I think you have basically gone through the downloaded code files that I had asked you to download, and you get inside it and go to kepsilon and go to a constant folder, and you can see that there is a file name called Turbulence properties. Just copy this, Control C, and then you just paste it in your laminar folder inside the run directory. I think you get this. So in your laminar folder, you have constant, and inside the constant, there is a turbulent properties file missing. You just copy that from the downloaded code files and paste it here. Now you can see that we have two files, transfer properties and turbulence properties. Now I think we have the required files. Now see that if you do it manually, we can see that our new additional file is being generated. So you can just keep it, or you can just delete this. So now we have all the required files to run our simulation for the laminar case. Okay. So I think everyone is following me till now. So if you have not followed me, if you are facing problems, then please let me know up till now. Okay, fine. So now we have our template ready to run our simulation, but we can see that we had copied from the cavity case. So that if you go inside the system in the BlockMeshDict, so actually this is not the actual block mesh that we want to generate our mesh. This is for the cavity case only. So we want to replace this with our with the downloaded ones. So if I go downloads inside the downloads, and the code that I downloaded, that is simulation of 2D turbulent flow in a channel. So you just go inside it, and from the system there is a BlockMeshDict file. Just copy that, copy this, and then go back to your laminar case that is on the run folder. So you can just open multiple tabs and then switch on and switch this between these tabs like this. So you can see that now you can see that inside these laminar folder, inside the laminar folder in the run directory, there is the system, and system has BlockMeshDict file, but this is not the required file. That is the original file. So we want to replace this. So just paste it here. So now you have replaced it. Now if you open this, then you can see that you have replaced the original file with the new one inside the BlockMeshDict file. So these are that I demonstrated earlier. This is the BlockMesh file. Now you can see the additional file generated. Let's keep it. Now after our BlockMesh is ready, After we have copied the block mesh from the downloaded section to our to this Laminar folder inside the run folder. Now just what you can do is now go to your terminal. Now go to terminal, and after going to the terminal, type run. Yes.
Sir, in a constant folder, turbulence properties.
Yes.
We have not enabled laminar, right? Right now we are
Yeah,
doing
yeah.
laminar.
We will change. Yeah, we need to change that. So right now we are doing turbulence. It is, I think, set turbulence. We will change it to laminar, but let me first create mesh. That is how to create mesh, and then we'll see to it. Okay.
Sure.
Okay. So in a terminal, type run. This will get into the run directory. Now inside the run, there must be a laminar folder created. So just type cd laminar. So this will direct you inside the laminar folder. So I have, so you can see that I'm into this address, that is OpenFOAM 109 run and laminar. This is username. It will be different from mine. So now because now our setup is ready to create a mesh, because we have copy pasted like we have brought the BlockMesh files from the downloaded code file to our original this working directory, that is laminar. So if you type BlockMesh now.
Just a quick question. Can you show where to download that exact code for the turbulence one? From where to download?
So okay.
Okay. Okay, I have got it.
So actually, it is available in the spoken tutorials website.
Okay.
So you can, and here in the spoken tutorials, you can see code files here.
Right.
Okay. After you have done these these steps, like you have created first, what we have done is we have created a folder called laminar. So inside after creating the folder, we have copied from the cavity case that we had already run. We have copied the zero constant and system folder from the cavity case to our laminar folder. Right, that was our first step. Now, after we copied from the cavity case to the laminar folder, that is not the required. There are not the required files inside the in this laminar folder. So what we did was we downloaded from the spoken tutorials website the required files, and then we copied those files, that is the BlockMesh files, into our constant, into our system. That is, we replaced it with the downloaded ones. And also we added a file called Turbulence properties in the constant by copying from the downloaded ones to the laminar folder. Now you can see that after I run BlockMesh, a new folder called polymesh is generated. So inside the polymesh, you have this set of files. So you can access this later. So after you run BlockMesh, this will create a polymesh file inside the constant folder. Yes. So this is the now the important thing is you want to run a laminar case. So in this turbulence properties file, you open the turbulence properties files, which is located in the constant folder. So right now you can see that we have assigned the simulation type as RAS, which is runs model, but we want this to be laminar instead, because we are doing a laminar simulation. And if you do this laminar, then you don't have to delete this. This won't affect this. So we need to assign our simulation type to laminar. So this file is located inside the constant folder in the turbulence properties. So if you have this file missing inside the constant folder, then I request you to download to copy paste this from the downloaded code files.
Is it possible to visualize the mesh now?
Yes.
Can you visualize the mesh?
Okay. So I think everybody have followed it till now. So let's now we have also created our mesh. So let's just type paraFOAM.
Could you please repeat what will be the simulation
Now click
type?
apply. Yes.
What will be
What
the
did you say?
simulation type?
Laminar.
Yeah, what
You
will be
need
the simulation type? Laminar. Okay, thank you.
Laminar. You need to assign as laminar case. So you just type paraFOAM dash built-in. In case your paraFOAM is crashing, sometimes it crashes. So I will refer to this command paraFOAM dash built-in. So you can see the command here paraFOAM dash built-in. So now you can see that now after paraFOAM will be opened. Now you need to apply the green. You need to click the green button that will be highlighted in green. Just click apply. And if you want to visualize the mesh, then you just click surface with edges. So now see that you can see that there is a grading applied here, right? So we have very fine mesh at the walls where we need to capture the boundary layer properly and the gradients properly. So you have, so why is this? Because if you go to your BlockMesh file, so if you go to your case, so if you go to your run directory and laminar case, so this is my case that is inside the run directory. I am going inside the laminar case, and inside the system, I am going inside the BlockMeshDict. So we can see that in the simple grading, we have applied a grading in the y direction, right? So, and if you visualize this, there is only grading applied in the y direction, not in the x direction, because we have in the x and z direction, we have just applied one value of uniform grading. But in the y direction, that is this in between, you can see that we have applied the certain number to this y direction to create a grading. So we have this amount of cells, 75 in 30 in the y direction, and we have applied this grading. So how do you calculate this grading? So that might be a question. So basically, this grading refers to the ratio of the last cell to the first cell. So for the laminar case, okay, okay, I think we can stick with this grading for now. If you want to create a new grading, okay, let me teach you how to do it to create a grading. So if you want your first cell height to be okay, you have a first cell height. Let us create a first cell height with diamond with the 0.002 meter in the first cell. Okay, so this will also help you in the turbulence case later, how to make the grading. So you just go to your web browser and type BlockMesh grading calculator. I request everyone to go into this. And I think it is the first site that will, okay, you must, that after you type that BlockMesh grading calculator, there is a first website. So just click inside that. And now you can see that there is this interface open. So now you want to, like, you need to assign, first you need to have the input parameters in order to develop the mesh. So what we have now is, so let's see this. So if you let's suppose that we want to create the first layer, right? First layer, say first cell with 0.002 meter. That is the first layer height would be 0.00 meter. So what we can do is we can just in the drop down option, we can click width of start cell. So we can provide width of start cell, and then if you want to do a first cell height with 0.002 meters, just type 0.002. And there is an option called total length. So we have our length of 0.5 meters in the block, first block, because we have two blocks which is of 0.5 meter height, and the upper block is also of 0.5 meters height. So first we are doing for the first block, that is block 1, we are specifying the grading, how to do the gradings. And we have assigned the number of cells as 30. So you can see that in the y direction, we have assigned number of cells to be 30. And we have our the height as 0.5, that is the length as 0.5. This is just I'm doing it for reference so that it would be easy to do setup in turbulent case. So if you do this, then you can see that total expansion ratio comes around 28. So this value is the ratio of the last cell to the first cell. So we can see that our first cell is, hello. Okay, we can see that our first cell is 0.002 meter, and we can see that our last cell is 0.05 meters. So if you do the ratio of these two values, this would give the total expansion ratio. So in OpenFOAM, when you calculate these grading parameters, it is actually the ratio of the last cell to the first cell. So you can just type it after you get, we have a total expansion is 28. So I just typed in 28. Fine. Similarly, in the second block, that is in this block, in the second block, we want our grading to be okay, we want our grading to be this way. That is, in the first block, we have the first cell as very fine mesh, but in the second block, we have the last cell as very fine mesh, right? Because we will start from this direction, from the y direction, while we have assigned the blocks. So we can see that in this block 1, our first cell is very small compared to last cell, but in the block 2, we can see that our last cell is very small compared to our first block, first cell height. So now what you need to do in this grading calculator is, the number of total length is also fixed, the number of cells is also fixed, but instead of giving width of start cell, you can give width of end cell. And you want your first cell that is in the so you want this first first layer height from the upwards direction in the block 2 to be 0.002. So I am doing keeping this as 0.002 and press enter. So you can see that now the total expansion ratio comes to be 0.035. So because we have the last cell very small compared to the first cell, so while doing the ratio, the value is very small. So just keep this value 0.035 in your BlockMesh file. 0.035. So I have chosen to keep my first cell height at 0.002 meters, and accordingly I have calculated the grading parameters. So what we need is, we need the length or dimension of our height or dimension of our block, and we need the number of cells, and then we can calculate it accordingly. So just press Ctrl S to save the file. So I think you have you know now how to calculate the grading. So in this way you can calculate the grading, but in turbulent case, the y plus is not important. So I've just to make it fine, I've just used reference at 0.002 meters as the first layer height, first cell height. So after you have done this, so you have edited this, you need to run the BlockMesh again, so that this effect will be incorporated in our mesh again. So let's go to terminal. Okay,
Can
now
you
let's
click the vertices once?
press Ctrl C. So this will close the paraform that you have. Yes.
Hello.
Hello.
Sir,
Yes.
can
Yes.
you
Can
click
say it again?
So can you please show the vertices once? Okay.
This is the vertices. You don't have to type this because it will take time for now. So I have just asked you to copy paste from the downloaded files. So if you go on typing this, it will take much time, which we will be on sort of time. So after this, just press go to terminal. If your ParaFOAM is opening, close the ParaFOAM, or you can just press the Control C in terminal itself. This will close the ParaFOAM. Control C. Now run the BlockMesh again because we have changed something in the BlockMesh and we want this to be
Sir, how I
incorporated.
can go in that Laminar terminal actually? Because my internet got disrupted, so I have left the meeting. Right now, when I'm typing ls, it is showing that is in cavity case, Laminar, and pits daily. So different
Go type CD Laminar. It will get inside the Laminar folder. CD Laminar.
terminals are there. How I can go to Laminar? Okay, no space.
CD space Laminar.
Okay. Okay, now I'm in
So
Laminar. So
so you have not copied from the downloaded.
I have copied. Abhi copied that mesh thing from
Okay, fine.
Epsilon file. Yes.
Okay, fine. So that's okay. So after you edited that part, just type BlockMesh.
Okay.
So what I changed was that I changed the grading, and I also taught you how to change the grading. So you
Yes,
can
sir,
always
yes.
refer to this later. If if you have on your free time, you can do this. So I have chose the first cell height to be 0.002 meters.
Yes, sir.
Actually, we don't have a y plus value in the Laminar simulation, so I have chosen an arbitrary value of 0.002 meter, so that y plus will be equal to 1 or something like that. Okay, after you do this, just run BlockMesh, and then you can.
Hello.
And then you can.
Just one quick question. I wanted to know that about the. Can you show the script of the BlockMesh? Yeah, just can you scroll to the towards the left side, a bit towards the left side? Yeah. BlockMesh. Yes. This the way the cells are arranged in the hexagonal. Can you tell me it is I need to arrange it clockwise, and these two hexagonal segregation is for the two blocks, right? And so it will be
Right.
segregated according to the number of domains, or if the geometry has many different domains to be simulated, then I need to segregate in different row. And so can you tell me how these cells are segregated, like 0, 1, 3, 2, 6, 7, 9, 8? Like, is it clockwise or like any?
Okay, I think you have missed the session
Yes,
before.
yes.
So actually, Ivan has also demonstrated that. Okay, I will tell you once again. Then what you do is, so this is it is visible.
Okay.
So this slide.
I got it.
So you can 0, 1. You either go anti-clockwise or you go clockwise, but it should be the
Okay.
same convention.
Okay.
Okay.
Sir, after doing BlockMesh, I have to do IcoFoam, right?
No. We are only at the BlockMesh now. We are not running in the simulation. We are just creating mesh, generating mesh for now, as of now.
Hello?
So after you have created the BlockMesh, yes.
Yeah, actually, my terminal got closed. Can you show me how to navigate to Laminar?
Okay, just you type open air Ubuntu. After you run Ubuntu, after you launch your Ubuntu, then just type run. Okay, this is okay. I have to alias it first. So after this, type run. So you will be directed to the run directory. Now inside the run directory, you have your laminar case, right? So type cd laminar. This is telling you to go inside the laminar case. So in this way, you can direct yourself to the laminar folder. Did you get it?
No, it's showing no such file or directory.
Okay, so I think you have not created laminar folder.
I think so.
So if you type, okay, I think we have missed that part. Okay, we'll come back to that later. So just if you type ls, then there should be a folder called laminar created.
Okay, no, it's not showing. Only the run file is
Okay.
showing.
You have just joined now, or you are from before?
No, I joined 15 minutes ago.
Okay, fine. Okay, so what you can do is, first of all, type this command mkdir laminar to create a folder called laminar.
Okay. Yeah, done.
So now if you do ls, then you have a laminar folder created.
LS, yeah, laminar, yeah.
Yeah. After that, you what you should do is, now inside the laminar, what you should do, you need
Hello,
to copy. Yes.
Manzil.
Yes, sir.
So, what is your plan after this? Is Deeptanshu going to demonstrate?
Yes, sir.
So I think you then, if people will keep missing, and then we will not be able to do the whole thing. So
Okay.
you keep your pace also, and don't answer all the queries, because now somebody will say that I have not downloaded the case. Now if you keep showing them, then see, we barely have how much, 20-25 minutes left. So you have to run the case,
Okay.
explain to
Okay.
them, show the turbulent case also. So you judge now which are the what I can say, queries which are genuine. So answer only genuine queries. Now if somebody says, now I have not copied, now I have not done this, so don't entertain them, because now really we are short of time, because after
John.
that then he also has to demonstrate. Okay.
John,
Okay, sir.
there is a
Yes.
live streaming also. So if someone is missed something, they can go the
Yeah,
live
yeah,
streaming and
correct.
watch that.
Correct.
Yes,
So
yes, you
because
can
now
go.
we have only 20 minutes left, so those who have, so those who are really struggling, so what you can do is you observe now whatever is going on, and if you miss some steps, you can go back and look at the recording. So you also understand that for us, if we keep answering every query, we will not be able to complete the content that we have planned for this workshop. So okay, please bear with us. Those who are a little bit lagging, so please observe what is going on, and you can ask doubts on those if you're not understanding something. So those will be the doubts which we can entertain, and that will be helpful for you, rather than we have not copied or something. So please understand the situation. Okay,
Okay. Okay, sir. So right now, we have already created our mesh. Now we will see the boundary conditions. So what, you just open your file explorer, go to the run folder, go to your laminar folder. The run folder is located in Ubuntu. So you just go to the run folder and go inside the laminar folder. And inside the 0 folder, you have boundary conditions for P and U. Right. So what we can do now is, we just can, because we are short on time, so we can copy from the downloaded code files the P and U files inside these boundary conditions. So what you do is, you go to your downloads folder, and or where you have downloaded your code files from the spoken tutorials website, go inside that, and you go inside that. So actually, even it is a KF silent case, the mesh is same, the domain is same. So we can only change some parameters to change it from laminar to turbulent case. So actually, so I'll just transition from laminar to turbulent case in this way. So we do not need epsilon k nut for the laminar case. So just copy the P and U file. Just copy this P and U file and paste it in your laminar folder inside the 0 folder. So go to your laminar folder, go inside the 0 folder, and then paste it here. Okay. So now you can see that now I want you to open the U file inside the laminar folder. Open the U file. So you can see that we have assigned the inlet as for the U velocity boundary condition. So we have assigned velocity boundary condition at the inlet. So it is a fixed value of 20 meter per second. But what I had shown you in my presentation, that we are doing a laminar case of Reynolds number 500. So we want our average velocity to be 0.005 meter per second. This is for turbulent case, right? So now we want to change it to 0.005. This is for the laminar case. So I have actually taken the files from the
code files of the spoken tutorials website that is done for the turbulent case. Now I'm changing it to laminar case. So we are operating on the Reynolds number, which is in the regime of laminar, in the laminar regime, and the value of the average velocity is 0.005, which I have calculated using this formula of Reynolds number. So after you do that, you have provided a fixed value at the inlet. So you have provided outlet zero gradient boundary condition. The zero boundary condition, what it does, it takes value from the nearby cells and keep it as its own. That is, the gradient at this outlet is 0. So what is near to the cells, what is the value? It will take the values from that cells only. It won't calculate. So we have assigned upper wall and lower wall as no slip boundary condition. I think you know what is no slip boundary condition. And always keep in mind that this syntax, that is, these capital letters are very important. That is, you need to always worry about this capitalization. That is, the first one is 0, the first one is small letter, and this one is the capital letter. If you miss this, then this will give you errors. So, and we can see that we have our front and back as empty because we are doing a 2D simulation. Okay, now our this is ready. Our U boundary files is ready. Now let's go to the P files. So you can keep the P files as it is because we don't have any values. So actually, in the outlet we have a fixed value set to atmospheric pressure. So you need to do this. So in the inlet, the zero gradient boundary condition, we calculate from the velocity itself. So upper wall, lower wall, and front and back as empty in both these U and P files. Okay, now this is our boundary condition is also ready. Our transport properties, let's see what is inside. So it should be, you can see that the kinematic viscosity is set to 0.01, but in our case, the kinematic viscosity would be 0.18 minus 5. So you should also change this value. So let's change this value. So now we have set the value to 1e minus 5. Yeah, I think you got this. Okay. So we have also changed the turbulence properties as laminar, as also fine. And in the system, now what I want you to do is you just paste all these control dict, FE schemes and FE solution from downloaded files, from the downloaded code files. So just copy this control dict, FE schemes and FE solution from the downloaded from the code files to the to your run folder where there is a laminar case. Okay, here is my laminar folder inside the run directory. So I would like you to copy this. Okay, so you can delete these extra files. This is the artifact of doing it manually. So you can now we have all the files ready. We have like edited the turbulence properties file, transfer properties files. We have also made the P and U, set up the P and U boundary conditions. Now let's look at the control dict file. So in the control dict file, you basically have to assign the start time, end time, and always note that which solver you are using. We are using here SimpleFOAM, and SimpleFOAM is a steady state solver for incompressible and can also use turbulent flows. So we are using a steady state solver. So actually the end time and this delta T do not matter in the steady state simulation, but to match with the framework of OpenFOAM, this is used to just match the framework with the other code files as well. So this is the right control, right time. I think Ivan has already explained this how to set up these and these values. So actually SimpleFOAM is steady state solver, but this time step is not important. But what is important is okay, this is the discretization schemes. They are the FV schemes. So how do you discretize the temporal schemes, the time scheme that you are using steady state? If you are using a transient, then you must assign it as Euler. That is Euler is for the transient transient simulations. So these are the for the simple form. It is just steady state. So these are the the divergent schemes. So how do you discretize this? So these you can go to it later. And then FV solution. So in the simple algorithm, this on the relaxation factors is very important, because this will have to have an stabilization of the solution. So you should set these values and study about these values properly, because these values will decide on how much you want to change the gradient and get a new value. So this relaxation factor is very important in the simple form. So I think we are already ready with the files. So I've changed all these required files. So now let's run the simulation. Okay, let's go back to our terminal where I have run laminar case. So as I'm using simple form, I have already run BlockMesh. So I'll type simple form. So it says transport properties. Right, let me check it.
Manjil, you copy the transport properties from the setup only, because
Okay, fine.
this
So actually,
cavity case was for IcoFoam, right? That's why the file structure is different. So you explain to them that the file structure is different and copy them. It will work.
So so what you do is we had copied the turbulence properties file from the downloaded files, but this transport properties file was copied from the cavity case. So this is creating this error. So what I want you to do is just copy the transport properties file from the downloaded code files into our laminar file, laminar folder. So go to your home, go to your OpenFOAM, and then run folder. Go inside laminar, go to constant, and then paste it here, replacing the old transport properties files. So you can see that this is quite okay. You can see the syntax is different. In the previous one, we had not assigned transport model as Newtonian, but this and it was in the error. We can see that it was asking for keyword transport model is undefined. Now we have defined transport model as Newtonian. So we have resolved this error. So you need to see the errors and then fix it accordingly. Now if I type if I go back to the terminal and then type simple form, now you can see that the simulation is running. So just type simple capital F and you can press tab. It will and have to type it all. So we have so our simulation is complete. It has come to the end. Okay, so you can see that in these folders that inside the laminar you have created these additional datas are stored here. So in simple form, it will stop when the simulation will converge, or when it reaches the end time. So after the residuals is also very important. So in the FB solutions, there is there is a tolerance. Yeah, I think this is the residual tolerance. So after it reaches the residual converges to these values, then the simulation will stop, or it will stop if it reaches the end time. So we have we have our files ready. So now let's visualize in the ParaFOAM.
So let's type paraFOAM built-in.
Sir, I'm facing issue with like simple form while running the simulation.
What is the issue?
So it is showing that a foam fatal error actually cannot find file. Laminar 0 nut karke is there.
Which file is missing?
It is showing that Ismail run laminar 0 nut cannot find file. It is showing foam fatal error. It is showing.
No, it is saying which file is missing.
Laminar.
NUT is missing, Manzil. I
Yes,
think
yeah,
he has not replaced. He has not replaced the what you can say RAS to laminar in the turbulence properties.
Okay.
Which files?
So you need to replace the so you go to your
Transport as
laminar.
well. Okay.
Transfer model is missing.
No, NUT is missing something. NUT.
Okay, so what you have not changed is, so you go to the constant, inside the constant there is a file called Turbulence properties. So just open that file in your laminar folder.
Yeah.
And have you set it to laminar?
Which one I have to suppose to set
You can
laminar?
see your simulation type as laminar. There is
Simulation
RAS.
type RAS is there, yes.
Okay, you just change it to laminar.
Okay, in place of there is no hyphen, right?
No. So because we are doing a laminar simulation, so we must change it to laminar.
Okay,
Okay,
small.
fine.
Small.
Okay, after this, then you can run the case.
Okay, simple form. Okay.
Okay, so what you can do is basically you can copy all these downloaded code files and replace with these test cases. That would be easy. Instead of copying one by one, you can copy all at first, then you can run the simulation.
It's running, sir. It's running now.
Okay, fine. So let's view in paraFOAM. So after I click apply, so you can see that our result is ready. Okay, so I'll only demonstrate one thing in this ParaView. So apart from that, you just learn to post process on your own. So let me plot a value. Okay, I'll show you. So I will plot a line in this domain and see the velocity variation along the y direction. That is, I want to see the boundary layer formation. So I want to create a line that is a vertical line in one of the cross section. So you can see that there is an option called plot over line. You can see my cursor, right? The black cursor is you can see that. So there is a icon here with this plot over, or you can also do go to your filter. Okay, let me close this and open it again. So okay, now it's running. So you go in the first, you can see in the first row there is the option called filters, and it will open a drop down menu. So you can go to alphabetical, and when you go to alphabetical, there are so many filters in there available. So you just select plot over line. So it is here, plot over line. In the filters alphabetical, there is an option called plot over line. So select that. So it would come here, plot over line. Now where do you want to plot your line? I want to plot in somewhere. Is this the domain length? That the domain width is 65 meters. I want to plot it around 60 meters. So you can see that in the left hand side there is an option called 0.1, 0.2. So you can just type 60 meters in the x direction, and you want your y direction from 0 to 1. So you can visualize here 0 to 1.
So it is running from the bottom lower wall to the upper wall. And then you want in the fixed z plane, that is, let's plot it in the 0 plane, that is in the front plane. 0, 0 means z is the z value coordinates 0, which is in the front plane. Now let me click apply. So after this, don't forget to click apply. So now you can see that the velocity u magnitude is ready. Now let's you can see that in the second row there is a place called time, and when you click on this time, there is a drop. There is a 50 written in just left to the right to the time. So if you click that, there will be a drop down menu. So go to the last time step. That is 1000. Okay. Now what I want to do is you can while you are in these contours, you can always go to these left hand side and then scroll here. So you can see in this left side there are various parameters: 0.1, 0.2, x-axis, y-axis. So scroll down, and you can select here which do we want to plot in these values. So I will just disable p, and I want to see the u magnitude. So you can see the u magnitude. Now we can see that the maximum velocity in the rectangular channel flow is always 1.5 times of our the average flow. So if you multiply 0.005 with 1.5, this will give 0.0075. So you can see that at the center, the velocity has reached 1.5 times of our average flow. So by this, you can say that we have studied that is 1.5 times, but we can also see it in our simulation. So in the rectangular channel, it's 1.5 times. So I just wanted to show this. So our I think you have followed this till now. So you can also plot various results, like you can plot streamlines, velocity vectors, and all these in the post-processing part, but you can do it on your own. So after this, now let's we need to simulate for the turbulent case as well. So
Sir,
I will
can
take
we, sir, one question here. Can we extract this data, like this line graph
yes,
you
yes,
plotted
yes,
u magnitude?
yes. I'll teach you that. Okay.
Okay, sir.
So okay. So what you can do is just there is an okay. Okay, I think this is again hanging. It
Okay,
is
sir, I
not
will explore, sir, online. It will
okay.
be like, it
You
is
can
post
explore.
processing only,
Yeah,
like we'll
it is
explore.
possible to extract these data. Okay,
Okay,
so
sir,
you
thank
can you just search on your own. Okay, I now close this in post processing and then move towards the turbulent case. Hello, how much time do we have now for this next case?
Manzil, go ahead with the turbulence part also. After that, Diptanshu will demonstrate the GUI.
Okay, fine.
Yeah.
Okay. So I'll
Target 15 minutes, right? 10-15 minutes, because Diptanshu will need half an hour. So by 4:15 at least we want to hand over to Professor so that he can demonstrate the other advanced cases. So I think 10 minutes, 10 to 15 minutes you have. So you just explain to them what are the files, and maybe if they are not able to do, they can at least look at it. If they are able to do, then
okay,
good.
sir.
Okay. Yeah.
Okay, sir. Okay, sir. So, okay, let's explore the turbulent case now. And now we have already known how to do a laminar case and how to set up our first cell height and the grading values. Now, it would be easy for us to set up the turbulent case. So now, again, I want you to type open terminal, fresh terminal. So just open a fresh terminal. But let me close all this. After you open a terminal, you need to type run. Okay, I need to type okay, then type run. You should start from this. Now this will direct you to the run directory. Now I want you to create a new file, new folder called Turbulent. So if I do ls, then you can see that your new folder called Turbulent is being created, right? So after you create the Turbulent, now go to your file explorer and go to your run folder Okay, where is my run folder? So if you go to your run folder, inside the run folder, there is a new case called Turbulent, but the cases is empty here. So what I wanted to do is copy paste from the downloaded code files, all the files into this terminal manually. We won't do it from terminal now, so just copy paste it manually. So go inside the downloaded code files. So inside the k epsilon, so copy this zero constant and system, and then paste inside the turbulent folder. Now you can see that when you do it manually, there is an additional file formed, so that won't be a problem here, but it looks bit complex. So okay, so fine. So I think the case is ready now. We just have to block mesh and then run output. But now let's dive into how we select these values and all this. So you can
Sir, you are not audible.
Manjul, are you there?
I think Manjul has lost connection.
Yeah. Okay.
Is there any chance, Ivan, that you can continue?
Yes, ma'am. So the next thing is that we will go to the turbulence case. So wait, just let me load the case over here. I'll then share my screen.
hello, was I?
Okay, Manjul. Yes,
Yeah.
Manjul.
Oh,
Yes, Manjul, please
was
continue. Actually, you are not audible, so I requested Evan to continue. I thought you lost connection.
okay. From where did I lost the connection?
You are starting the turbulence case, Manjul.
We have copied that thing from download section.
Okay, fine. So you have copied already that part. So that is that means our setup is ready. So what I was showing was just what is the turbulent, what is the modeling. So we are using Reynolds modeling, which is the Reynolds average Navier-Stokes equation. So we want to when we average those equations, we get an additional Reynolds stress terms, and we need to model those Reynolds stress terms in terms of the mean flow. So actually the fluctuating flow in terms of the mean flow, and in order to model this, we need the eddy viscosity. We need artificial viscosity called the eddy viscosity, and in order to model this eddy viscosity also, we have different models like the K epsilon model, K omega model, and the K omega SST model, and other models are also available. But we will just focus now on the K epsilon model. So is my sound clear to all of you, or is it breaking?
It's fine, Manjul.
Okay,
Yes.
fine. Okay, so what we want to do is we want to model this eddy viscosity in terms of the K epsilon values, or in the K epsilon model, or in the K omega model, we want it to model is in terms of K omega, and the K omega SST model is the blend of K epsilon and K omega models. So I think I don't have much time to describe on what this model is and how this model performs in which type of y plus values, or which type of like the which performs best near the wall and the log region. So you can always refer to the spoken tutorials. So what I suggest you is there is in the spoken tutorials there is an there is an additional file called the if you scroll down, additional reading material, there is a file named additional reading material. So you just click on that. So this will open your PDF. So in this PDF, it is very detailedly explained on what are these models and what are the wall functions, and so which performs based in which type of y plus values. So actually, at a log region that is y plus greater than 30, the K epsilon is regarded to be effective, and in the viscous top layer, K omega model is regarded to be effective. So if you can choose these models based on the y plus values. So right now we will be choosing a y plus value of 100. Okay, you can see that. So y plus value of 100 means that our y plus lies in the log-law region. So in this log-law region, when the y plus lies in this log-law region, we need to use wall functions in order to incorporate the viscous sublayer. Because when we use y plus very large, that is the first cell height will also be very large as a coarse mesh. So we cannot resolve the viscous sublayer properly. That is the very near to the wall, the gradients, all those things. We cannot resolve it properly because our mesh is very coarse. So in order to incorporate that, in order to incorporate or resolve this viscous sublayer, we need additional wall functions. If you select y plus value greater than 30, but if you have y plus value very less in the viscous sublayer, then we can it is not required to use the wall functions. So you can see that in the viscous sublayer, the viscous sublayer is y plus is equal to u plus. So this is you can see that there is a curve here because this x-axis is in the logarithmic scale, so it is a curve. But in fact, this is linear in the linear axis. So and in this region, it is in the linear axis, it will be a curve. So you can go through this, what are all functions, how to what are the parameters, all these in these files, and then study detailedly. So now I would like how to set up these values. So right now we will select y plus of 100. We are not selecting y plus 1 because it will result in a very fine mesh, and then this will also increase the computational time because this and also results in poor mesh quality sometimes. So we are choosing y plus 100. Now after you select y plus, you can see that you can calculate the first cell layer using this formula, first cell height. This yp is the first cell centroid height, not the actual height. It is the height of the centroid. So yp is this value, and the total cell height will be double of this. So you can see that it is calculated here. So using this height, we have calculated the expansion ratio as 15.4. So you can see that if you go to the one where you have copy pasted these from the downloaded code files, and you go inside the BlockMeshDict, you can see that the values in the y-axis grading is 15.4. So this is actually this value. So I've also taught you to calculate this on your own using grading calculator. So if you go to this calculator, and the total length is 0.5, number of cells, it is 30, right? Number of cells is 30, and you want the first cell height to be let me see.
It is number of cells, is number of layers here.
No, number of, you can say that is a number of layers or the total number of cells in that block in the y direction. Okay, so you can see that the first layer, that is the cell height is 0.0031. So if I type the first, let me see, with the start cell and 0.0031, so you can see that actually the total expansion ratio comes out to be 15.43. So this value is calculated here using the calculator on our own, but this website will calculate it in the back end. So you need to use this expansion ratio value. So expansion ratio, I have already explained about that. That is the ratio of the last cell to the first cell. So we have used the 15.4, and to calculate this value, just you can alter these end cell and first cell. So you can do this on your own, or you can just do 1 divided by 15.4. So this will also give these values. So just to divide 1 divided by 15.4, this will give these values. So I think the block mesh is also ready. I have not changed anything from the Laminar case. I have just changed the grading. So you can see that how grading is done in the in this block mesh. There is also options for multi-grading, so you can also look at it later. Okay, so our so we have selected the y plus in the 100 in the log layer region. So this is done. So we have calculated this. Now we will just look at the KF model, and we'll complete our session. So in order to calculate K, this is the formula. So we have considered the isentropic turbulence was that this gives the formula of 3 by 2 u. This formula, you can see that. So the detailed calculation is provided in this PDF, so you can always go back after this session also. So this is for the pipe flow. This is the formula to calculate the turbulent kinetic energy K. So I is the turbulent intensity. So for the pipe flow, it is given by this formula. So here is the calculation provided 0.0261. The value of K is calculated here, and epsilon is also calculated here. So it is very important to initialize these parameters very properly, because this will control, or this will affect the accuracy of our solution. So
What I want is
yes. Am I audible?
Yes, you're audible.
Yes, Manjit, you're audible.
Okay, fine. So, okay, now we have these values available to us from these calculations. Now we will just use these values in the boundary conditions. We'll do that. So what we can do is, now let's see our case. So go to our turbulent case. Now go to the 0 folder where our boundary conditions are stored. So now you just open the U folder first. Let's see the velocity boundary conditions. So it is just keep as it is. That is a 20 meter per second, because we want a Reynolds number of 200 as 2 million. So from this, when you calculate, we get the average velocity, that is the inlet velocity at 20 meter per second. So inlet outlet, do keep as it is. So that is the same as the laminar case. So I want to just show the extra file, that is K epsilon and K epsilon nu t. These are the additional files that are required for turbulent case. So after I open this, okay, let me first close this and open it again. So now this is for the epsilon. So let's first see for the K. So you can see that so you can see that we have calculated K to be 0.4087, which is a rounding off to 0.41. So we have initialized, this is the initial values that we want to initialize our solution with. You cannot choose an arbitrary value, because this will lead to inaccurate solutions and also might lead to divergence. So it is always advisable to calculate it properly. And also the K omega model is very sensitive to these free stream or initial values. So this calculation is should be very proper. Okay, so these and we have seen that turbulent density value is 0.0261. So in order to calculate the inlet, we have okay. So we have used the turbulent density. So we have calculated the Kf from the turbulent density, and the value is kept here. So you can look at this. It is available in SRC boundary. These boundary conditions will be located in the source code, so you can see to it. I will show you one. Okay, if at the last, if sometime remaining, I'll show you where these boundary conditions will be available in the source codes. Now outlet will be 0 gradient, and you can see that we have used the wall functions, because our y plus is in the range of 30, that is in the log region. So if you have y plus in the log region, you need to use the wall functions to resolve the boundary viscous sublayer properly. So you can.
So sorry for interruption. There is few details that are different. Like in your case, here it is type. Like in inlet, there is type, intensity, and value. Whereas in what file I have opened, it is type, mixing length, and value is there. And internal field uniform is 0.61 is there.
0.61.
Yeah.
I think you downloaded it from the 0.61. That you are looking at the epsilon file. That is, I'm showing the K file. That is turbulent kinetic energy.
Sorry.
Okay, look at that. So I'm not going in detail inside these boundary conditions and all this. You can. Okay, I'll show you first where you can find these boundary conditions.
Mm.
Uh, Hello. Just one question. Like
Yes.
in the outlet region, the end there is no end effect. That's why. Can you tell me the one it is zero gradient over there? There is no value of in the outlet region. So
Mm.
can you tell me the physics at the outlet?
So actually, the zero gradient boundary condition, what it does is it doesn't calculate on the boundary, but it will take the value from the internal cell, that is the cells near to the boundary. So whatever when you solve these equations, and to it, that means the gradient is zero in that part.
Okay. Right. Hello.
Are located in these like basic boundary conditions are the fixed values, zero gradient. So here it is also case sensitive. So you can see these are the boundary conditions for the basic and for the constant and all these. Okay, you can explore these on your free time. But the boundary conditions are set here. And also, if you want to see whatever turbulence models are available in OpenFOAM, so you just go to the SRC folder, and there is a folder called momentum transport models. So go inside this, go to incompressible, go to areas, various transport, that is various turbulence models available in OpenFOAM. So you can go inside the source code, and all these things you can do on your own to explore it more. Okay, now we have boundary conditions available from K. So for the epsilon, this is the boundary condition. So we are defining the based on the mixing. This is the formula to calculate. So 0.07 into L is the mixing length. So our L characteristic length is 1 meter. So 0.07 into 1 would be 0.007. So we have kept 0.007 as the mixing length. And we have initialized the epsilon with the calculated values of 0.61. Okay, and we have used the wall functions. This is required for these cases where y plus is very larger. And nu t also requires the now nu t will be calculated. You can see that nu t will be calculated using this formula c mu k square by epsilon. So it is calculated. We have kept the boundary condition is calculated because it calculates on its own. But the OpenFOAM calculates these values on its own. But we need to assign all the wall functions to these cases also for the walls upper and lower wall, and the front and back is kept as empty since this is 2D simulation. So I think now these boundary conditions are ready, and now after we have the boundary conditions ready, so let's go to transfer properties. And the turbulence syntax, the keyword used is RAS, and we have the RAS model as K epsilon, turbulence on, and the print and asked to print coefficients. So you can change this to K omega. So you can change this to K instead of K epsilon. You can change plus. So you can change it in the turbulence properties file. So after that, the system file. So we have a BlockMeshDict. I have already explained. I have also taught you how to calculate these gradings, and this control dict. I have used the simple form, which is a straight solver.
The time step is not important. It is only kept for the framework because it is a steady state solver, and the FE schemes FE solution that does it is same as in the previous case. Okay, now let's run the simulation. So let's open our terminal. Run. Now I think you are in the run folder. So first, so what you want to do is boot inside Turbulent. So first type run. So you are in a run folder. Go inside Turbulent. Now inside Turbulent, there are these files that we have copied from the downloaded code files. So just type BlockMesh. This will generate the mesh. So we can see that our mesh is generated. Now, after the mesh is generated, now let's run the simulation using simple foam. So I've also ran the simulation. So you also do on your system. So simple foam, the simulation will stop after the values are converged, or even if we have a larger time, if we have a shorter end time, then it will after the end time is reached, it will stop the simulation. So there are two ways of doing the simulation, but we should ensure that the time step. Okay, so am I audible? Is my voice clear, right?
Yes, Manjul.
Launch the ParaFOAM. Okay, after that you click apply. Okay, now again I need you to repeat the process. That is, let's go to the last time step. Instead of 50, you select there and go to the last time step on that is 1000, and then go to filters, go to alphabetical, go to plot over line, and then you need to plot a line at a distance 60 meters in the x-axis. So you can see that I have kept 0.1 in the x as 60, 60. So 0.1 and 0.2, 60, and y I want to do it in the front plane. So I will just keep 0. Numerous plots because we have epsilon, k, nu t, we as well in the turbulent case. So let's first visualize the results one by one. So in this left hand side, scroll down, and you have the option to untick and tick these parameters which you want to plot in the graph. So first let's just see the u magnitude and untick all these. Okay. So I think the simulation it needs some time more to run because it's quite parabolic. But in turbulent, we have the velocity contour as a flat profile. So we can see that this is quite getting it's quite near to the parabolic. But after you run some more time, this will eventually change to the flat profile. So because we have already studied that the turbulent flow in turbulent flow, the velocity profile will be flat in comparison to the laminar flow. So after you have visualized the U, so you can see now untick this and see the value of K. So you can see the turbulent kinetic energy. So you can see at near the wall, the turbulent kinetic energy. Okay, 0, 1. So these are the plots for turbulent kinetic energy, and if you want to see for the epsilon, and these are the values. So you can just tick and untick these parameters, and in order to export these coordinates, you can click on these side of this layout one. There is option for plus. You just click on plus, and you get this interface. So at the bottom there is an option called spreadsheet view. So click on spreadsheet view, and these and what you want to extract from this simulation. So just click on this yellow icon. You can see here the yellow icon, and here are all options ticked, but we don't want all these options, so just untick them and just tick which is required. If you just want u, epsilon, k, nu, t, and p, so you can just tick these options, and these are the values. Now in order to extract or export this data, at the end there is an option export spreadsheet. So just click there, and you give your file name, give the file location, and click on OK. So you can export these data as well. Okay, so just you can do it plus and in this way, and you can visualize the results and process this accordingly. So what results are important? So you can compare with the k omega and k epsilon as well between these two models. So in order to do the k omega, there I'll just give you how to do that. We have brief overview on how to do it. So go to your transport properties, just set these values to turbulence properties. Just set this value. So just set this keyword to k omega RAS model, and you need a different file. Instead of epsilon, you need a file called omega. Right. So what I would suggest you is you go to the spoken tutorial website. So there is another tutorial called as that is tutorial number 10. So in this tutorial number 10, in the code files, and k omega and how to set up this value. So right now the website, the server is not working, so you can check it later. So instead of epsilon, what you need to do is you need to calculate omega. So to do that, I think I have here. So you can see that omega can be calculated from epsilon itself by using this formula. But the transport equations for this k, epsilon, and omega will be different. The epsilon and omega transport equations will be different, which will be solved in the internal cells. So it will get a different value. Just to initialize this, initialize these boundaries to that document in the next tutorial available in the spoken tutorials website. So right now this.
Sorry to interrupt. One doubt I'm facing in the ParaView. My time is till 1 second. Like my simulation didn't run. So what might be the problem? Is it in the like what might be the problem? Like this, I run the BlockMesh and as well as the after that the ParaFoam. But somehow in the ParaView I can see in the ParaFoam I can see the time is still 1.
So did you copy all the files from the downloaded files?
Yes, I copied the all the transport properties as well as the turbulent properties from the.
No, not just that files. I asked you to copy all those folders from that code file into into our turbulent folder.
Yeah, I think I did.
Because I think you have. Okay. So you can open your control dict and match and see there what are the inputs. So just open your control dict. And see if this is the same.
What is it?
Okay, I think now I will take queries and all the issues that you are facing. So if anybody is facing any issues, then you can
Sir, like in my case, ParaView is not directly getting launched. Like it was problem for yesterday only. So
yes,
what
yes.
I have to do, I have to put it touch result.foam and I have to save it to some other folder, and then from there I have to open ParaView in ParaView. But
Yes, yes.
this result, when I'm doing, it is showing like multiple option to open. Like when I'm dragging to open, it is
What?
showing like a reader.
Okay.
Okay, please.
Okay. So what you do is you scroll down,
Okay,
and
there is a lot of option.
you can see option called OpenFOAM
OpenFOAM
Reader.
reader. Okay,
Okay,
OpenFOAM reader is
select
there.
that.
But still it is showing error is showing, sir.
What is the error?
Error in C DVD something. Error
Okay,
in C
so
common
so
execution
did
model.
you
Okay.
did you copy all the
Yeah, I have all the three files, like in three folders. I have copied three folders from there only.
the time step is also there, time step folders?
Time step folder. Okay, let me. It will be in a constant, right?
No, in the outside, just inside the directory, turbulent directory. If after you run the simulation, like
There
so,
are 0 to 1000 times different folders are there. Yes, constants are there. System is
okay,
there. Yeah.
Yeah, that thing is not there in my turbulent folder. So, but
My
I can
simulation
see
is
the
completed. My simulation is there because I able to see there were 1000 times it was there.
okay. Try what is the form file that you have created? I think the form file is wrong. Turbulent.form, the capital letters, all those. Have you checked that?
Yeah, like I have
mine is
created the result file as touch result.form. So my result
Okay,
file
you
is
have
like
used
result
all
cell.
small letters,
Small,
capital small letters
no,
in form file.
F is capital. F is capital.
No,
Form is
okay, that's the problem. So just make
okay.
it small.
Okay. Thank you.
yeah, I can see the my simulation didn't run like, but my control did all the steps are like as far as you that you have shown, like in the control did.
Okay, so have you run BlockMesh first?
Yeah, I have run BlockMesh. Yes.
So BlockMesh is running. Is it
Yeah.
fine? It is fine, right?
Yes, it's fine. Yes. Then I ran the paraform in the turbulent
No,
folder.
and simple form. Did you run simple form?
Okay.
Because you need to run the simulation first before visualizing the results. So
Sorry. I didn't run this.
okay.
Manjil, can we now ask Diptanshu to start?
Excuse me, sir.
Okay, excuse me. Okay, John sir, what time do we have now? 2 minutes?
Yeah, you can take a last question because we want Diptanshu also to finish. After that, Professor Chandan also has to start. So
Okay.
we are
Okay,
already
sir.
very late. So
Okay, let me take one last question, then
Sir,
we'll end this.
I have one question. Like, how can we simulate, like, animate the simulation that we just performed?
Okay, fine. So,
so
okay,
those
I'll.
are available, huh, Manjil?
Hmm,
On see, if you search on YouTube for ParaView, there are a lot of tutorials available wherein you can learn all of those. I think if you have any other technical queries, you can take that. So demonstration queries now, please don't take that. Take any technical queries if you
okay,
have,
okay,
because how to use ParaView and all
okay,
those things. Lot of tutorials are available on YouTube, like saving and all those things.
Like I have like one question. So like if there is multi-physics involved, like I have to solve that like sub ionic fluid is there to transport. So if I have to solve Poisson equation for electrostatics, and from there I have to solve generally I'm talking about perspective for microfluidics. So there will be creeping flow model will be there. So I have to solve pressure, velocity, and electrostatics is there. So and there is
okay. So you
coupling,
need
like
to.
body force will be coupled from there because
So this requires a different solver. So we
okay.
can you can use these solvers. There are various solvers in the OpenFOAM. So you just go inside the SRC and see all the available solvers to get problem. So the problem is related to multiphysics and such
Electrokinetics, yeah.
problems, electrokinetics. So you will have different solver for these type of problems.
Okay, it's like these files like constant file and zero file, and that will be accordingly
Yeah,
modified.
that
Yeah.
will be that will only be the U folder, P folder. Only the boundary conditions will be modified. The file structure, the folder structure will be same.
Okay. Thank you, sir.
So Ismail, for your reference, you can look at our I think last year's workshop in which we had demonstrated electrohydrodynamic cases as well.
Okay, sir.
So
Thank you.
that was a combination where electrohydrodynamics, so electric field, magnetic field effect on fluids, that was also shown, and there we had demonstrated how to write your own custom solvers to solve those equations.
Okay, sir. Thank you. So, like, where
So
I can find that thing, sir?
so the recordings will be available on YouTube. You can
Okay,
search
sir.
FOSSEE's previous. I think it was a 6-day workshop.
Okay.
So that recording is available. So in that, Mr. Swapnil had demonstrated that from IITB. So that will help you. It will give you perspective of what can be done.
Okay. Thank you, sir. Thank you.
Okay, I think we need to wrap this now. If there are no more questions, so
Sir, for LES model, is there any tutorial file like for K omega, K epsilon? There are files. So if I have to apply a model, is there any similar kind of file?
which model?
LES in the
I
turbulence model, in turbulence case, if I have to apply LES model.
yeah, you can use. I think the tutorials are not available in the Spoken Tutorials website, but you can refer to other tutorials where you can use instead of the simulation type, you need to set it to LES and then do it accordingly. So you can. This is a different part. This is not run simulation. So you can visit the other websites to how to formulate that, how to formulate those.
Okay.
Okay, I think we need to wrap this up. So thank you for your time and attention.
Sir, one last, like, there is FOSSEE IT, like IT Bombay. There is a FOSSEE page, is there in YouTube?
Yes.
FOSSEE IT Bombay. Okay.
IIT Studio Bombay is also there. There is also a page for FOSSEE. There is also YouTube channel for FOSSEE.
Yeah. Thank you, sir. I forgot. I got it. Thank you.
Okay. Thank you, everyone.
Yeah, thanks a lot, Mandir. So next we'll go ahead with Diptangshu's session on the GUI part of OpenFOAM. So FOSSEE IT Bombay has been developing GUI since a couple of years and Diptangshu, along with his team, has developed some modules to solve some of the problems of OpenFOAM. So it's a very unique presentation from FOSSEE IT Bombay. I hope you all will learn a lot. And you will actually start learning how to use GUI to solve, to use OpenFOAM. So over to you, Diptangshu. You can start your session.
Thank you, ma'am. So hello, everyone. I'm Diptangshu, and I'm currently working as a research assistant at FOSSEE IIT Bombay. So I'll give a quick demonstration about the GUI GUI for OpenFOAM that we've been working for. So let me just share my screen first. My screen is visible, right?
Yes.
Okay.
Yes. Go ahead.
Let me just move this away from. I will place it here. Okay. So currently our GUI is developed as a Blender add-on. So if you are not aware, Blender is an open source software that is mainly used for 3D graphics and for creating 3D art and 3D animations, and also for visual effects. So it has a very nice Python API that can be used to make add-ons on top of Blender software itself, so that Blender's features can be reused for other fields. So in our case, we have made an add-on to ease the process of case building inside OpenFOAM. So currently we have a UI for BlockMesh for BlockMesh that helps us to create BlockMeshDict files in an easier manner. So I will give a quick demonstration here by making a Venturi tube case. So usually what we do is we write out the BlockMeshDict files by ourselves by hand, or maybe we use some third-party tools to convert them to generate BlockMeshDict files. So here we can just generate the BlockMeshDict files inside of Blender, and it is really helpful for newcomers if they want to understand how BlockMeshDict works. So I will just demonstrate how it is helpful. So this is the initial screen of Venturial. So it is available in the right-hand side tab in the 3D viewport. So here I can just select which my case directory. So I will open a temporary directory that I have here, and I'll click on OK. So this is the directory where my output dictionary will be stored. So moving on to the next tab, which is geometry. So here we will generate which blocks we need. So since I'm making a simple Venturi tube, I will need 3 hexahedral blocks. So hexahedral is the default type of blocks that I need here. Hexahedron is basically cubes. And I can set the number of cells that I need. So let's say I will take 20 cells in each direction. And I will generate my blocks. So here you can see I have 3 blocks that have been generated. And then once these blocks have been added to the viewport, I can modify their shapes however I like. So to make a Venturi tube, what I will do is I will just expand these to double this size, and let's drag it a bit backward. Okay. So this can be my inlet over here. And in this block, I will drag it, let's say 3 times, or maybe 2.5. And let's drag it outwards. Sorry. Here. So here we have a shape of a basic Venturi tube. So now that our basic shape is ready, we will select all the blocks that we have, and we can compose them to make a single mesh that is going to be our final mesh structure. Now we can modify upon this mesh as we like. So let's start by adding all the data present in this mesh into our internal software. So we will first do get blocks. So here you can see all the block data is similar to the one that you see in your BlockMeshDict file. So here you have the type of the block that you have, and you have the vertex ordering of your block. And then you have the grading, which is simple grading for now. In future, this will be changed so that you can have edge grading as well. And you will also be able to change the grading scale in your over here in the future. And next up, we will list down all the vertices that we have in here. So as you can see, I have just at a simple press of a button, all the vertices are then gathered around here. So the work of this tab is done here. We'll move on to the next tab, which is edges. So the edges tab is used to generate curves in your mesh. So for example, if this were a pipe, I would have to generate some curves along the edges to represent that, okay, this edge is a curved edge. But since it is a simple Venturi tube, it is not needed. So moving on, which is boundary. So here we can mention the boundary conditions for our mesh. So for example, this was our inlet. So I can click on new boundary, and I can just mention that, okay, this phase is my inlet, and I want it to be of a patch type. And once I enter OK, you can see that this edge has been recorded over here. I can do the same with our outlet. This will be our outlet, and it is a patch, and enter. And I will select rest of the faces. Just a moment. Okay. So all the surrounding faces are selected, and then I can just add new boundary, and I will just name it wall, and it is also a type wall. Or maybe I can just name it pipe. That will be better. It's better to have different names than the boundary type. So once I click OK, so you can see all the boundary types has been registered over here. So then I can safely exit out of edit mode. And then in the visualize tab, you can visualize all the features that you want. So let's say I want to check the vertex coordinates if they are right or not. So I can just click on this tick mark over here. And then that will enable the vertex indexing. And then I can also see vertex coordinates over here for each of the vertex. And then I can also see the boundaries that have been assigned over here. So currently these are showing only the colors, and then I have to match the colors over here with the boundary type, which vertices the boundaries are having, and what is the name of the boundary. So with that said, this mesh is now ready to be exported. So if I just generate BlockMeshDict over here, this in the run tab, you can see BlockMesh is generated in the bottom here. So yeah, in our directory, this is the generated BlockMeshDict file. So as you can see, it is generated by Venturial and all our data is here. So this file can be used inside of OpenFOAM. So I will just copy this and I will paste it in a sample file that I have ready. So yeah, I will replace this and let's open up OpenFOAM, and then I will just show it in ParaView how the file looks like. Okay. So I have started up OpenFOAM. Let's go to the directory that I had. And in here, I will run BlockMesh. So the BlockMesh tool runs, and then I will visualize using ParaView. Okay, and apply. And here you can see the Venturi tube that I have made. So if you are wondering why it is vertical, when in Blender it was horizontal. So it is because in Blender, the axis orientation is different than that of ParaView. So in Blender, y-axis is horizontal, the x and y plane is horizontal. While in ParaView, you can see that the x and y plane are vertical. So along the vertical is the y-axis. And I can also enable the edge lines. So that shows you that all the cells are also rendered here. So this is how you can use the GUI to quickly make BlockMeshDict files. And it is also easy for beginners. It also makes it easier for beginners to understand each aspect of BlockMeshDict, what each aspect does and how it matters, how it affects. And currently development is going on for a GUI for Snappy Hex Mesh. And we will also shortly start our development and do a release for the solution modeling GUI. So this is the current state of the GUI for OpenFOAM. And if anybody has any questions, they are welcome to ask in the chat box. So if anybody has any questions, they can ask, or we can move on with the next presentation. Then.
There's one question that says how to use Fluent Mesh in OpenFOAM. Okay, I'll just quickly I'll just show that. There is one command. I'm typing it in the chat for everyone to see. You can use the command Fluent 3D. Wait. Fluent 3D mesh to foam. And then you type in whatever mesh file you've created, .msh file. So in this one, I'll type here file name .msh. So what you'll have to do is when you create your mesh in ANSYS, you will have to export it in the .msh format. Also, you have to make sure that in ANSYS you've enabled the whatever this you're writing it in, that MSH file, that it is written in ASCII format. So in your settings, you'll have to go and enable that first. After that, you'll have to export that mesh file, the .msh file, put it in OpenFOAM within. Yes.
Are you showing any screen on?
No, I'm not showing any screen. I'm just explaining. I've written it in the chat. So the command basically you copy that MSH file within your run directory or the case that you're running. So in our case, if you had the cavity case, you would put it inside your cavity case with your zero constant system. And then you'd have your .msh file also over there. So then you open your terminal, and instead of doing block mesh, now you will do fluent 3D mesh to foam. You will put your file name, whatever file name was of your that MSH file, you put that file name .msh and you press enter. That will convert your fluent mesh file into a file that is readable by OpenFOAM. And then after that, you can go ahead with all the remaining solver commands that you have, icofoam, simple foam, whichever one you want to run. Okay.
Excuse me, sir.
Yes.
Sir, how does this OpenFOAM handle the dynamic mesh?
So for dynamic mesh, there are tutorials already readily available. Basically, in the tutorial file only, you will find anything.
Sir will
that
demonstrate. Evan,
Yeah.
sir is demonstrating that next.
Yeah. So now Professor Chandan Bose will come. He will demonstrate how to basically do all the dynamic meshing and all that. So he will explain all that. Okay.
Thank you, sir. Thank you, sir.
Yes.
Also, on another note, if anybody wants to use the GUI for when OpenFOAM, I have pasted the link to the release in the chat box. So you're welcome to use it and test it out. And your input will be, we need input from you guys on how you like the GUI and what other changes or what other features you would like on the GUI itself. And if you have any more questions regarding the GUI, please put it in the chat box and we will address it.
Any questions for Diptanshu from the participants? There's a question in the chat box. Can any of the team members take up the questions? Uday Shankar. Uday Shankar has posed a question.
Uday Shankar, you're asking this question regarding the GUI or in general in OpenFOAM? Okay. So in OpenFOAM, you want to set up how to simulate a turbulent flow over airfoil using an ANS-based method. Okay. So in OpenFOAM, if you go in your tutorials where I'd shown you all in your OPT file, there are some tutorial files already available that use flow over an airfoil using the RANS model. So what you can do is copy those files and run them as it is to see how they've implemented all of that. Then accordingly, if you want to change any velocity or something, you can make those changes and you can go ahead with your simulation or any type of application that you want to go with. Okay.
You with me, sir? Sir.
Yes. Who's speaking?
Sir, I'm Raviteja, sir.
Okay.
Sir, how can we run this? Sir, I have a body like airfoil, sir. How can I apply polyhedra meshing or like polyhexacore meshing to that thing, sir? Like we do in Fluent with meshing, sir. How can we perform those activities in OpenFOAM, sir?
So you want to go for an unstructured mesh?
No, sir. I have to, sir. I mean, I want to go for a structured meshing, sir. How can I do that in OpenFOAM?
Okay, so you basically want to just mesh an airfoil, right? Flow over an airfoil.
Yes, sir.
Okay, so you can basically for the airfoil itself, there are two approaches to this. You can in BlockMesh use the spline utility to define your whole airfoil and then break your domain itself within different blocks. Or the second approach is you can use snappy hex mesh in which you can specify your, basically you make a CAD file of your airfoil itself and you put it within that domain. And then using Snappy Hex Mesh, you can make your 2D geometry, 2D meshing file. Basically with Snappy Hex Mesh, you'll have that CAD file within it. So that way only.
Okay, sir. Thank you, sir.
Can I add a point here? Sorry, I'm Chandan. So basically, I just wanted to add the fact that if you have already used ANSYS and you know how to mesh it, ANSYS Fluent or any other sophisticated meshing tools such as Pointwise and other softwares, you can always import your mesh into OpenFOAM. That's basically one very useful feature of OpenFOAM, that OpenFOAM allows any third-party meshing software exported mesh to be imported as polymesh within OpenFOAM. So apart from that, there are two other very powerful meshing tools which are open source available. One is called GMSH and another is Salome Mecha. So these are two meshing tools you can explore which are open source, and you can also make the mesh there and then import it into OpenFOAM. And there are different utilities, such as for GMSH, there is GMSH to foam. For ANSYS, Fluent Mesh to foam. These utilities can be used to import the mesh within OpenFOAM. Hope that is helpful. Thank you.
Yeah, thank you so much, Professor Chandan. Thanks for the answer and thanks for joining this workshop. We all welcome you here. So I hope there are no more questions from the participants and we can go ahead with your session. Right. So participants, he is Professor Chandan Bose. He has joined from the University of Birmingham. He is a faculty member there at the Aerospace Department. And he is presently our principal investigator for the OpenFOAM team of FOSSEE. So over to you, Professor Chandan. You can start your session.
Thanks. Thanks for the kind introduction. I will just try to share my screen first to see if I can share it. And let me know if you can see my presentation. Right. Can you see my presentation?
Yes, sir.
All right. So before I start, actually, can you please let me know how much time roughly I have?
45 minutes is okay.
All right. Okay, sure. So should I go ahead?
Yes, please.
Okay. Hello, everyone. I hope I'm audible properly. So I'm Chandan. I'm an assistant professor of aerospace engineering in the University of Birmingham, UK. And in this brief session, what my objective is to basically demonstrate to you what are the different features for particularly dynamic meshing or moving body problems related to external aerodynamics, but not only aerodynamics, it can be used for any other applications. And what are those features that are available in OpenFOAM which you can use to simulate your own moving body problem? All right. Now, before I basically go into the agenda of today's talk, feel free to stop me. I don't mind that to answer your queries in between, but because the time is very limited, I would prefer you to post your questions in the chat box, which I can then at the end take the questions one by one and clarify your doubts. So moving forward, I basically, let me see. Yeah, moving forward, I lead a group which is named as Bio-Inspired Fluid Structure Interaction Laboratory in the University of Birmingham. And we are basically interested in different aeronautical and also in general fluid structure interaction problems. So some of the topics that our group actively focuses on are bio-inspired microaerial vehicle, unsteady aerodynamics, fluid structure interaction, aeroelasticity, and in general, broadly computational fluid dynamics. And we have basically multiple funded projects going on currently, mostly funded by Royal Society, University of Birmingham, EPSRC, etc. And mostly, as you can see from the ongoing projects, we are very much focused on using the knowledge of fluid structure interaction and learning from nature how we can implement these natural mechanisms into the futuristic aerial vehicles that are basically the primary focus of our group. And among all the research interest, the one which is very close to my heart is basically bio-inspired flapping. So currently we are focusing a lot to understand how the naturals, birds and insects actually use bio-inspired fluid structure interaction to actually increase their aerodynamic efficiency, and what is the role of very much unsteady nonlinear vortex dominated flows in the underlying increment of aerodynamic efficiency. So this is the simulation that you can see, that which we are actually developing a GPU enabled a fluid structure interaction solver, which can actually aim to simulate hundreds of such butterflies flying together and understanding their nonlinear physics. Now, hopefully you have got a brief idea about my research interest. Now, before I go into the actual topic, just to assure you that I am the right person to give this demonstration to you. So I am working with open source code developments, including OpenFOAM from my PhD days, more than 10 years now. I have been given the responsibility to lead the FOSSEE OpenFOAM project, and I'm member of the OpenFOAM Technical Committee for Documentation and Tutorial, and currently an editor of OpenFOAM Journal. And different works from our group have been featured, including in OpenFOAM Journal cover. So as you can see, these are two of the covers that features our work in the OpenFOAM Journal. Now, with that brief introduction, let's basically try to look into the features of dynamic meshing within OpenFOAM. And as you have already got the idea from the rest of the 2 days session, that OpenFOAM is a very broad code library that can be used for multiphysics simulations in a very broad term. And fluid dynamics, heat transfer are just one subsets of these libraries. You can do many other things such as magnetism, phase change, etc., etc. Now, this particular topic, which is dynamic meshing, is actually applicable to any of these themes or any of these particular solvers that you want to use. So they are not limited to aerodynamic solver. However, for the focus of this talk would be more like external aerodynamics problem, because I guess the audience is more interested towards that. And even within dynamic meshing techniques, we have multiple different type of algorithms or approaches by which we can actually implement the dynamic meshing to move a body or a structure within our computational domain. I'm sorry for the sounds that is coming from outside. Hopefully it's not too disturbing. So among all these different algorithms, I would mostly focus on two majorly. One is mesh morphing, another is overset meshes. But I will just give you a glimpse about other type of dynamic meshing techniques such as moving meshes, sliding meshes, adaptive mesh refinement. Now, what are dynamic meshes actually? So, and why do we need them? So dynamic meshing strategy allow the mesh motion. As I told, that it enables us to implement a moving body simulation for whatever application that we are interested in. And now to allow this mesh motion, we have to modify the governing equation of our problem. And this kind of approaches can be actually considered in different kind of algorithmic framework, such as one is arbitrary Lagrangian Eulerian framework, where mostly we will implement this mesh morphing type dynamic meshing, where you can see this is my scalar transport equation, and in the convective term of our governing equation, we have to modify the velocity term to a relative velocity term by including the mesh velocity UG here. So that's basically the underlying mathematical change that we need to do to incorporate this kind of mesh motion. Now, as I said, that this mesh motion can be actually implemented by deforming your mesh. That is one of the very popular approaches, which is called morphing, We can do this by adding or removing new cells in terms of remeshing our computational domain. We can use sliding of one mesh region over another mesh region, or we can actually use overset meshes, which means that we use multiple different type of mesh at the same time, overlaid with one another, and then apply the motion to one of these mesh zones, and then interpolate the solution back to the background Eulerian mesh region. Okay, so here the take-home message is that dynamic meshes should be compatible with all type of physical models. So it is not limited to only solvers that we use for fluid dynamics or heat transfer. It can be used, the same framework can be used for any type of multiphysics problem. Now, dynamic meshes are useful for, as I already told, to incorporate prescribed body motion, where we want to simulate a moving cylinder, for example, very benchmark problem that you can see. And you can see in the left where it is having a mesh morphing, you can see as the cylinder is moving up and down with a prescribed velocity or displacement, you can see that the cells around them are actually getting deformed to accommodate that motion. And that is basically called the mesh deformation or mesh morphing technique. Now, there can be other types such as rigid body motion, fluid structure interaction. And how fluid structure interaction is different is that the body motion is not prescribed. The body motion is calculated based on its interaction with the unsteady surrounding flow. And then last but not the least, we have mesh refinement or unrefinement, where we consider a particular scalar variable, and then accordingly to capture the change in that particular scalar variable, we can refine the mesh locally or unrefine the mesh by actually creating, as you can see in the rightmost part, creating new cells or dividing the cells into much smaller cells. All right. So that is called the adaptive mesh refinement. And the middle, you can see, which is named as AMI. It is called arbitrary mesh interface technique, where you can see, I will come in more detail, but here in this case, we use the sliding technique, where we have multiple different mesh regions, and one of the mesh regions slides over the another type of mesh to incorporate the motion, such as here, it's a pitching airfoil. All right. So going forward, the next one, as I basically mentioned briefly, that OpenFOAM also has a overset mesh capability. And that is actually can be seen in the animation in the rightmost part here, where you can see that the same problem of the pitching airfoil has been implemented in 3 different approaches. So the first one is arbitrary mesh interface, where you can see that the one region of the cells close to the airfoil is rotating by sliding over the other type of outer cell region. And then middle portion is where it is deforming the cells, which is mesh morphing. And the rightmost part, you can see the overset, where we have 2 different disconnected meshes, which is the first one, the upper mesh region is actually moving over the background Eulerian type of mesh. Okay. And then the solutions gets interpolated at the interface of these 2 mesh region. Okay. So how to set up this dynamic mesh cases? So that should be your first query, right? So now you have probably have done different tutorials with stationary bodies or some sort of lead driven cavity or channel flow problem. You know how to use different solvers, how to set up the different flow condition, such as by changing their viscosity, velocity, changing boundary condition, etc., etc. But if we want to incorporate this dynamic meshing technique, what additional setup requirement is there for an OpenFOAM simulation? All right. So the first one is that these dynamic mesh motions are actually they are controlled by different code libraries that are already written within OpenFOAM framework. So we don't have to code it separately, but we need to call those functions and then prescribed the motion, whatever we want to incorporate in terms of the motion of the body. And the file that we need to actually include additionally in this case is called the dynamic mesh dict. Okay, it's a dictionary file which actually declares and defines the motion of the body, and it should be located within the constant folder. I hope that now you are clear that in the general setup of the OpenFOAM cases, we have three different folders. One is 0, one is constant, one is system. Now the constant folder where we locate different flow properties like transport properties, turbulence properties, and the mesh directory, which is called polymesh. There you have to include another additional dictionary file, which is called dynamic mesh dict. Okay. Now, for moving body simulation, as I've already told, you have to assign a motion type. Okay. And that motion type has to be associated with either a patch, which is a boundary, or a cell region, or it can be associated to the whole computational domain itself. So I'll show you examples for all these three. Now, for example, going back to the animation, just to make it clear to you, in the first problem, which is arbitrary mesh interface problem, we assign this motion to actually a whole cell region, right? Because we are rotating the whole cell region into the inner part of the motion. Okay. And that can also be implemented in a different way by assigning this motion to the patch, which is just the airfoil patch. Okay. So that's why you have to take into account that you can do it in different way. One way of defining this motion type is either to assign it to a patch or to a cell volume or cell region, or in a different case, different problem, which I will come in a while, we can assign the motion to the whole domain. The exception is adaptive mesh refinement, because in this case, we have to set a refinement criterion that what is the physical quantity that we are trying to capture, and that will be in terms of a scalar field basically. And then we have to set that refinement criterion within this dynamic mesh dict so that then leads or tells the code to refine the cells locally based on the change in that particular physical quantity. Okay, now that we know where to actually define different motion, the another important part that needs to be changed in this setup, that is the boundary condition. So as you know that within the 0 folder, we actually have different boundary condition and initial condition defined depending on whether it is a wall, whether it is a patch, whether it is even within walls, if it is a slip wall or no slip wall, etc., right? Now, for example, for the previous example, if you want to give the motion to the airfoil, which is a patch, if we want to mention or prescribe a motion type to that patch, the boundary condition has to be changed. Okay. So that even though that's a wall, that has to be changed to the type of moving wall velocity or calculated type of boundary condition, so that the code knows that the velocity on the wall gets changed or as the wall moves, right? Like the airfoil which is pitching. So just to show you schematically, where does this change? So in the whole tutorial case structure, you can see that within the constant, there is polymesh and then other properties, system 0, and within 0, you have basically the initial and boundary condition given for pressure and velocity and other fields if there is such as temperature. Now, within constant, we have to include this particular dictionary file that I told, which is dynamic mesh dict. Okay. Now, I'm not going into the details of the source code because I don't think most of you have the background or I have the time to do that. But if you really want to see where the source codes are located, or if you want to take the source code and modify it to your own mesh motion function, you can actually go to your installation folder and it doesn't matter that I have a version 2112, it can be any version. If you go to the installation directory, you will have a folder called src, which is called source codes. Okay. And within the src, you can actually search for this dynamic fvmesh file, and this will lead to dynamic fvmesh, dynamic mesh, fv motion solver, rigid body dynamics, and so on and so forth. So these are the mesh motion libraries that are already written within the OpenFOAM framework, and you can use it. All right. So particularly, I would suggest you to look into the dynamic mesh folder, and within that, there are different motion solvers. And also there is a library called 6 degree of freedom rigid body motion, which enables you to incorporate fluid structure interaction. Right. Now, the next part is, as you know that you now know how to set up the dynamic mesh dict and how to prescribe the motion, and then how to change the corresponding boundary conditions in the 0 folder. Next is, how do we change the numerical schemes or numerical solution algorithms that are needed to get a converged solution for a moving body problem, right? So we need to adjust the solver settings according to our physics, what physics particularly we are trying to capture. And it is needless to say the fact that dynamic meshes have more stringent stability and accuracy requirement compared to the static meshes, because we are either deforming the meshes, or we are moving one set of mesh in the other set of background mesh, etc. Now, during simulations with moving bodies, the boundaries or mesh or the domain will experience strong instantaneous acceleration, large displacement or deformations, and fluctuations in linear angular velocities. And that is the reason why we need more stringent stability criterion or accuracy requirement or higher tolerance value. Now, particular to the adaptive mesh refinement simulations, the meshes will change and the cells will become smaller and smaller, or they will, if we go for unrefinement, we will join different cells to get a bigger cells, etc. Hence, the cell volume will change. Therefore, if you are aware, or if you have gone through any basic CFD course, you know that a stability criterion named CFL number, or basically it is also called the Courant number, will change from refinement level to refinement level. So we have to include, instead of a fixed time step or a fixed CFL number, we have to include a adaptive time stepping or adaptive CFL number to get a converged solution. It's extremely important to control the CFL number and be sure that it remains within the limit of the stability. So if you are aware that most of the CFD schemes for like PISO, Simple, Pimple, we need a CFL number of less than 1, which leads to a converged solution. So we have to make sure of that case, otherwise our solution will diverge. Also, it is recommended to always monitor the mesh quality when dealing with morphing meshes and adjust the numerical methods, because if the cell deforms too much, the non-orthogonality or the skewness of the cells go beyond the set tolerance value, and that leads to the divergence of your solution. And of course, you can imagine intuitively that dynamic meshes are intrinsically unsteady. So we have to take care of the unsteady conditions of our CFD schemes. And they are computationally very much expensive. So I think this gives you a kind of big picture of how these moving mesh problems are different compared to the problems that you have done with static meshes. Right. So quickly going into the mesh morphing case, and I'm aware of time. So can someone tell me how much time I'm left with?
20 minutes are there still.
Okay. All right. So that will be enough. So I will basically give you the brief overview of how to implement this mesh morphing and how to implement the overset method, and also with what kind of approach we take in these two different moving mesh mechanisms. And also I will briefly show you basically what are the other type of dynamic meshing case. So for mesh morphing, as I told, it's also it's a mesh deformation case where we deform the mesh by moving the body. It's also known as mesh diffusion or mesh smoothing technique. Now we can define the functions by predefined functions or by including our trajectory or kinematics in the form of a table. And with morphing meshes, large displacement with large time steps will likely to result in low quality meshes, as you can imagine, because it will lead to a very large value of CFL number. Now, the time step also must be chosen in such a way that the mesh motion can be incorporated accurately with a converse solution. So not only the mesh, we have to also make sure that our time stepping is appropriate. Now, also when using mesh morphing, the solver will report the mesh quality. So you need to, as you run the simulation, you need to see how the mesh quality is changing as the body is moving. All right, so take a basic benchmark problem such as oscillating cylinder, the one I have actually shown you. So what are the kind of available functions that we can use within this dynamic mesh dict? So for example, I have taken a mesh as shown in the left, and the moving boundary is the cylinder where we actually apply the motion, right? So the base dynamic mesh dict will look like this, where we have the mesh motion library, which is mentioned as dynamic motion solver FB mesh. We have the motion library, which defines different type of motion, which is lib FB motion solvers. And also, then we have different type of motion functions or motion libraries within this. And we are choosing here displacement Laplacian, and within that displacement Laplacian coefficient is chosen as a diffusivity case for inverse distance. And then we give the name of the moving boundary, which is cylinder here. All right. So this is a standard setup of how we set up the dynamic mesh dict. But here I'm just showing you a list of different type of solvers or different type of diffusivity methods, as well as different type of motion that you can incorporate here. Okay, so that's not the only option. Now, for example, if we choose angular oscillating displacement, it basically gives you a pitching kinematics, which is rotating. You can also set the pitching velocity by angular oscillating velocity. You can do oscillating displacement, which is like a translational motion. You can have oscillating velocity. You can also have time varying mapped fixed value, where you can actually kind of give a table with a time varying arbitrary motion if you want to. Okay. And there are different type of diffusivity methods also, and I will show you some visualization so that you can understand what they are. And this is a very important solver which is available, which allows us, which is move dynamic mesh, which allows us to actually see how the mesh moving even without solving the governing equation. Okay, so if you set up this case and you run move dynamic mesh, it will actually solve the mesh motion equation only and will allow you to see how the mesh actually moving before you actually run the actual solver. Now, this is an example of how we give the more different motion functions, such as in this case, we are using oscillating displacement function. So I'm giving the amplitude, which is a vector. So the first one is the X amplitude, Y direction amplitude, and Z direction amplitude. So in this case, you can see we are giving an amplitude of 4, and everything is in SI unit in the Y direction, which is 4 meter is the amplitude. And omega, which is the rotational velocity, we are giving as 6.28, which is almost like 2 pi. And the value uniform is a input so that we can visualize it in ParaView, right? And in the boundary condition, as I said, within the 0 folder, we change the boundary condition of the cylinder patch to moving wall velocity. All right. And then we choose different type of motion algorithms such as diffusivity function, etc., etc. And accordingly, we change our FV schemes or FV solution scheme to allow us to move the body. Now, this is an example of actually which I simulated exactly giving the function that I just showed you. So it is a prescribed motion where the cylinder is translating up and down with a given amplitude and a given omega, which in radian per second, which is the rotational velocity. Now, we can also incorporate, instead of giving an inbuilt function such as this oscillating displacement, we can actually give a table where we give the displacement value of the body with time and then tell the code to move the body accordingly. And this is how you can see first we are giving y directional displacement, then giving x directional displacement, then bringing it back diagonally. So this is an example of how you can incorporate arbitrary mesh motions. All right. Now, this is an example of how different diffusivity function actually changes the motion, or not changes the motion, sorry. The motion is the same, but it changes the deformation of the mesh. So you can observe that with diffusivity function inverse distance, how the mesh is deforming from the boundary to the cylinder. And by changing it to exponential diffusivity function, the deformation type is changing. So these are very useful for incorporating very high displacement oscillations where we need to, without changing the non-orthogonality or the skewness of the cells too much. Okay. Now, we can also include multiple moving body. That's very useful. If you want to actually include two cylinders instead of one, and then give different type of displacement function, this will be kind of another example where you can see in the first example, the two cylinders are moving up and down, and the second cylinder, the first cylinder is moving up and down, and the second cylinder is moving horizontally. Now, having said that, as you see that we are using deforming the mesh within these two bodies, we have to be very experienced how to make the mesh and how to change the solver setup so that our solution converge. Okay. Now, this is an example where we use a prescribed pitching airfoil, and we also use two tandem airfoils by using two different motions in the upstream and the downstream. We can change the frequency and amplitude of each of these airfoils in the motion function. Now, the last example on mesh morphing is a fluid structure interaction example where we do not define the motion function, but we allow the cylinder to move with the surrounding unsteady flow. And due to the aerodynamic force that the surrounding unsteady flow generates on the body, and we basically, this is you can imagine it as a spring mounted cylinder, and we can study the vortex induced vibration of it due to the vortices set by the cylinder. So for that, the only thing that will change is the library function and the motion function. As you see here, we are using rigid body motion instead of the Laplacian library. Okay. And also along with that, because this is FSI, we have to have a structural solver, which in this case we are using symplectic, but it can be a Rangakuta method. It can be a Newmark beta method, which basically use numerical integration to solve the mass spring damper equation for this cylinder. Right. So again, I will come back to you if you have any questions, but due to the sort of time, I will first demonstrate another type of mesh motion algorithm, which is called overset mesh. Now, in contrast to the morphing mesh, in the overset mesh, as you can imagine that the mesh is not deforming. Okay. So there is no deformation in the mesh, which allows us to incorporate a very high amplitude motion, because our mesh will not diverge due to very high skewness or high non-orthogonality. But in this case, we have different component meshes. As I told before, that in overset mesh, we use different disconnected meshes. And in this case, the example in the right, you can see we have a background mesh, then we have a refinement region, then we have a cylinder mesh. And in this overset meshes, we call them separately as component meshes. And there is a connectivity between these three component meshes, but they are not connected through the mesh, but they are connected through the solution in terms of interpolation between these overset surfaces, which are basically the outside surface of each of these mesh. And overset patches, this is very interesting that they can intersect with each other. So that can actually allow us to bring two bodies very close to each other, which is not possible by using mesh morphing. And however, the con is that overset meshes can add numerical diffusion to the solution. So as we all know that the interpolation is non-conservative, so this is comparatively less accurate compared to using mesh morphing algorithm. Okay. But there is a way in which we can reduce these interpolation errors, which is basically if we keep the cell size close to the overset patches, similar to the background cell size, that minimizes the interpolation error. All right. So as I said, there is a workflow of using overset mesh. We can actually generate different component meshes and then merge them. Then we have to define the overset patches where you can, which one you can see here in white dotted line. These are the overset patches where actually the interpolation happens. Then we have to assign priority, like the cylinder mesh here is the with the priority, higher priority, because we are actually interested to resolve the flow around cylinder. Then the next priority is the refinement regime, and the background mesh is the last priority. Okay. And then to solve this problem, we have to define a particular interpolation scheme and other related CFD schemes which are used by the code of the overset approach. So again, in another terminology, we name the three different cell types as whole, interpolated, and calculated. So the whole is the cells within this cylinder where we don't care about the flow and we don't solve the equation. Interpolated are the cells in the overset patches where the interpolation happens. And apart from these two, all the other cells are actually calculated where we need to solve the governing equation. Okay. Now, as I mentioned that for overset mesh, we need different type of interpolation schemes, and they change in terms of their accuracy and the intensiveness in terms of computation. So we have cell volume weight, we have inverse distance, least square, and we can try different interpolation technique and opt which one is the better accurate within the computational cost that we can afford to, right? So this is an example of prescribed motion, for example, that I have shown you before, that we have one disconnected mesh, which is one component mesh around the airfoil, and we have another mesh, which is background. So we do not have any refinement zone here. So we have only two different mesh zones. On the other hand, the next one shows you again the fluid structure interaction of a cylinder where we have two mesh. One is the mesh region around the cylinder and the other one is the background mesh. There are different interesting features that we can implement in overset mesh, such as, for example, we can define a refinement zone and then move the refinement zone with our body, which is useful in simulations of different type of problems, such as you want to simulate a seed passively flying with your turbulent wind. Now, if you want to capture the flow around that, your computational domain has to be ideally infinite, which you cannot do. So what for that kind of very large computational domain, we cannot afford to have very fine cells all throughout the domain. So we define a separate refinement zone around the body that we need to capture and then move that refinement zone along with that body. Right. So with that, I think I will take 5 more minutes to kind of show you what can be the other different type of dynamic meshing techniques. So the next one is moving meshes. And this is an example where we move the whole domain itself. Okay. And if you can intuitively imagine the application of it, and the major application of it is a problem like sloshing. For example, if you have a tanker, oil tanker moving with a tank filled with oil, and with the motion of the truck or the tanker, the oil inside that tank actually moves, and it creates a fluid structure interaction, particularly if the container boundary is not very rigid. and they create a dynamics which is called sloshing, and it can be also seen in other type of problems, but this is one that is coming to my mind in this respect. So you can here, instead of moving a particular mesh region within the computational domain, we can actually use this rigid body or the rigid body motion to move the whole domain. And the library for that is called the dynamic motion solver mesh, and the motion solver is the solid body. And within the solid body, we can use axis rotation motion, linear motion, multi-motion, rotating mesh motion, SIP dynamics, 6 degree of freedom, etc., etc. Okay. Next one is the sliding mesh that I have already told you, which uses an arbitrary mesh interface to do the interpolation at which one region of the mesh slides over another region. So in this example, as you can see that the inner rotating zone slides over the outer static zone, and thus we incorporate a pitching motion in an airfoil. But in this case, we have to use appropriate boundary condition, which would be the boundary condition would be cyclic AMI. And we have to define two different patches which are neighbor to each other. Okay. And then we have to kind of like say or actually declare that this is the AMI patch 1 and the other one is a AMI patch 2, and they should interact with each other to interpolate the solution back and forth from one mesh region to other.
चालेल श्रेयस प्रदीप राहुल आणि कोण चार
Sorry. I'm going to end it in 1 or 2 minutes, so be patient with me. So the last type of adaptive mesh, the mesh moving mechanism is adaptive mesh refinement. As I said that in this case, particularly the mesh divides themselves into smaller cells or they join to make a bigger cell depending on a refinement criteria. And that refinement criteria is based on a scalar field that we want to track, and which is named here as quantity of interest, which is the physical quantity that we want to track. And then we can actually give tolerance criteria such as what will be the size of the smallest cell or what would be the maximum cell size, etc., etc. And this is an example of a dam breaking example, kind of, where you can see the refinement actually captures the water level, which is alpha water, which is the volume fraction of air and water. And by capturing that, we can capture the interface of that. And the dynamic mesh dict here looks like something like that, where we have to define the field as alpha water and then other control parameters like what will be the maximum refinement, what will be the maximum cells, etc., etc. And important part is that in this case, we have to correct the fluxes and check for the tolerance criteria at every iterations. With that, I stop my presentation here and happy to answer if you have any questions. So I can open the chat, but if we have time, anybody wants to unmute themselves, please unmute and ask me. Right. So basically moving mesh and dynamic mesh have different motions or same. They are the same basically. If we are moving a mesh, we call the case becomes dynamic. That's why we call them dynamic meshes. So this dynamic mesh can be a component of the mesh, can be a cell zone around a patch, or they can be the whole computational domain as I have shown you. Right. There are no other questions.
Sir, is learning Snappy Hex Mesh enough for OpenFOAM? Do we have to learn any ICM, CFD or any other software?
It depends on the problem that you attempt to capture. So Snappy Hex Mesh is good enough for even in very 3D complex meshes, but it has known issues in capturing the boundary layer very well. For example, maintaining the Y plus distance or the first cell distance over the body. And this is all becomes important if you want to capture a very turbulent flow, right? And you want to basically resolve the flow to a very small scales. And in those cases, snappy hex mesh might not be the best option. So you might want to use a bit more sophisticated mesh.
So what is the next available option?
If you want to go for open source option, as I said, you can try to learn Salome Mecha. It is a very sophisticated open source tool which allows you to do a 3-dimensional meshing. You can learn GMSH, which is again an open source thing. But then if you are already having licenses of softwares, commercial softwares, you can go for ANSYS Fluent meshing or Pointwise, which is very sophisticated. But this now belongs to Cadence, which is basically has some license cost for it. So I see there are some more questions in the chat. Which dynamic mesh method useful to solve boiling flows or combustion? Again, I mean, as I said, any of these dynamic mesh methods can be implemented depending on what you want to capture. I think adaptive mesh refinement is a very popular approach for combustion system, because if you want to basically capture, for example, flames or other things, you can set the quantity of interest and use adaptive mesh refinement. For overset grid, how difficult it is for a geometry with full of curvature or distinguish between the whole interpolated calculated cells? Yes, this is a very important question, because yes, it is difficult unless you actually define the mesh in a way that the cells are very much refined around those features, such as, you know, roughness or such as holes, etc. So your mesh has to be very fine to actually appropriately capture those changes in your surface. But in terms of dynamic meshing technique, there is no problem, as far as I understand. Next is for complex analysis like turbo machinery analysis. What type of mesh will be a good fit? I think for turbo machineries, a lot of people use this sliding mesh technique, such as using arbitrary mesh interfaces where you can slide one mesh component over other. How it different from Snappy XMesh? What do you mean? Can you unmute yourself and ask, clarify what is different from Snappy XMesh? Let me move to the next question. Can we give some idea on hypersonic intake FSI? Now, these are very specific applications, and I think that's not the motive of this workshop. You can talk to us separately. We can help you with that. After importing geometry from ANSYS, is there any use of BlockMeshDict file? No. If we incorporate geometry or mesh from ANSYS, now what do you mean by geometry? If you incorporate just the geometry in terms of STL file, you have to use snappy hex mesh to mesh it using that STL file. But if you incorporate the whole mesh, you do not need BlockMeshDict because you already will have the polymesh folder. Okay. So can you please repeat other open source mesh apart from Snappy XMesh? One is GMSH. I'm typing in the comment. One is GMSH. Another is Salome Mecha. So these two are very powerful open source meshing tools. Sorry, I made a typo. GMSH. All right. Any other questions? If not, then thank you very much for your attention. I hope it was helpful.
Thank you so much, Professor Chandan. Thanks a lot. One more question I can see. If you could take that, then I'll go ahead with the conclusion part of the
Can
workshop.
both generate structured mesh? Yes, Salome Mecha and GMSH both can generate structured meshes. Okay, how to implement an appropriate momentum source term in Navier-Stokes equation, etc., etc. So for that, you need to rebuild the solver and modify the source code of the solver and recompile it. And I think I have some tutorials in my YouTube channel, but again, we don't have time to demonstrate to you how to do that now. Thank you.
Thank you so much. So I'll just go ahead and let them know how to participate in the FOSSEE project and
Yes,
what are
sure.
all offerings we have for them. Not only for the student, but also for the faculty members and the industry people who have joined today. Okay, so let's just allow me to share my screen. So is my screen visible?
Yes, I can see it.
Yeah. So I'll just go to our parent website, which is fossee.in. It is so simple, FOSSEE, fossee.in. Because here you can see that just minimize this. So we have just announced our summer fellowship. You can just click here and apply. Okay, and how to apply? Just scroll down and there's a registration form. You can see the registration form here. And once you go to the registration form, it will prompt you to select the FOSS that you're interested in. So as I explained in the morning, that FOSSEE deals with many other FOSS along with OpenFOAM. So all these projects are available for OSDAC, eSIM, okay, Focal. So everything is available. So for OpenFOAM, we have OpenFOAM CFD and OpenFOAM GUI. Both are there. Okay, so just you'll just have to view the screening task. It is already here, and just attempt it, and the selection will be based on this, on the score of the screening task. Okay, now let me go back. Okay, so here you can see all the tiles of the software that we promote. And once you click on any of the tile, for example, now I'm clicking on OpenFOAM, it will take you to the page of the CFD OpenFOAM page. So for OpenFOAM, you can just type cfd.fossee.in. This is our website for the CFD project under FOSSEE. So let me just show you something very interesting. I just mentioned about the case study project and research migration project in the morning. So once you click here in the case study project, you will see the completed case studies tab. Okay, so once you click it, you can see a repository. And there are 168 completed case studies now. And please believe me, these are all done by students like you. These repository, I mean, all these solved cases are not by IIT Bombay students. They are, I mean, they are, but they are not only by the IIT Bombay students or IIT Bombay professors. So in the morning only, I said that it is not confined only to IIT Bombay. FOSSEE project has, it has reached out to all the parts of India and abroad as well. Okay, as you can see today, Manjul Situla joined as our team member. He has joined from Nepal. Okay, so he is our one of our very esteemed team member. He is our research assistant of FOSSEE project. So, and he is from Nepal. So it's really happy that we can, work with students or persons who are outside India as well. If I scroll down, you can see the names of the universities, and Anna University, Amit University, ITB is also there. And the majority is ITB because Professor Janani Sri Mulidharan, who just took the session in the morning, she offers a course in her, MTech IIT Bombay students. And they actually submit the case studies as a part of their course. Okay, but rather than that, we also have many other universities listed. Just 3 universities from Nepal. Okay, and we have a long list actually. Similarly, we have a list of completed research migration project. We have a list of lab migration project. Okay, and now let me come to how you can apply or how you can work with us. So as I mentioned that we have already announced the semester-long internship and it is going on. So that option is closed for the year 2025. But you can actually apply for the summer fellowship. And apart from that, the case study project and the research migration project, they are open throughout the year. So if you said today you have learned some part of OpenFOAM, you have just started learning. Okay, so please go ahead and learn, and you can refer to the resources tab here. Let me show you. So once you click on the resources tab and go to the first point here, you can see a list of spoken tutorials. Okay, I don't know that today there was a problem in the spoken tutorial website, but now it is working. So there are 11 basic tutorials and 2 intermediate. So please start from scratch with the knowledge that you have today. You can just build up on that knowledge, okay, and create an expertise for yourself. I would suggest you please go through all this. And I'll also, after this workshop, all the registered participants will get an email as to, I mean, we will share you a list of references. So apart from these spoken tutorials, what else can you refer so that you can gain expertise in learning OpenFOAM? Okay, so just go through this spoken tutorials and then apply for the summer fellowship. And if not, by chance, if you are not qualified, don't feel disheartened, because it is up to you. If you have the willpower, you will definitely make it. Okay, so just learn, using OpenFOAM to solve simple cases at first. Just take any case of any choice of yours. Okay, and just collaborate with any of the faculty members at your institute, and take his guidance, and try to submit a case study project. Try to solve any simple problem on CFD. And first, I would suggest you to take up a case study project, and the next level will be the research migration project. Okay, so and the team from IIT Bombay FOSSEE, we will support you if you have any issues with OpenFOAM or while using OpenFOAM. Okay, so please go for it. If at all you cannot make it for the FOSSEE summer fellowship, please try and submit one case study. So today I can see now there are around 72 participants. So I would request all of you to please take it up very seriously and please go for it. And we also award honorarium certificates, and just you can see in the repository, we actually acknowledge your work in this FOSSEE URL. So in the completed case studies, you can see this name. So suppose you are successful in submitting a case study, so your name will be there, your university will be there, and your work will be here. And also, while learning OpenFOAM, you can refer to any of the case studies which are listed in this repository. So you can download the case study, you can download the abstract first, read it, and then go for the details and download the case study and refer to it. So this is how you can participate in the FOSSEE project under OpenFOAM category. We have a list of faculty partners as well. So they are our faculty partners. You can see their photo and their name. They're listed here. After this workshop, we can go back and refer. So they actually guide students like you, and they actually work with us and replicate what all we are doing at IIT Bombay. They are sitting at their institute and doing that. We are really grateful to them and thankful to them. And we also work with the industry people who are CFD professionals in the industry. And here is a list of 12 such people from industry. We have Dr. V. Ashok from ISRO. We have many other people from other companies. Just go ahead and browse their profiles. So they also work with us. They also guide the students and fellows like you. If you're lucky, you'll be one of their employees in future. Okay, so with this, I'll stop sharing, and I'll be happy to take up any questions from you.
Ma'am, can you tell me how to submit a case study project again?
Yeah, how to submit, etc. They are all listed. I just go to the case study tab. I just stopped sharing. Otherwise, I could have showed you once again. So there are guidelines of submitting the case study. So each and every you will find the template and all the details of submitting the case study there. There's a link called guidelines for case study. Okay, thanks to you.
Thank you, ma'am.
Yeah. Any other questions? So if you don't have any more questions, I'll request Professor Sandeep Juluru. Are you there? From Sandeep University, Nashik. Actually, this workshop was proposed by them, by Sandeep University, Nashik, and so I would really want to thank them for taking the initiative for organizing this workshop. And over to you, Professor Juluru, if you want to say a few words.
Yes, ma'am. Very thanks for giving us this opportunity. First of all, I would like to thank Payal Mukherjee madam and the FOSSEE team IIT Bombay. Once we have given a proposal to conduct this workshop, so they have happily accepted our proposal, because the OpenFOAM is a very new software which many of the academy are mostly depending upon the commercial software ANSYS. So with this FOSSEE, I would like to introduce the OpenFOAM to our students and to enhance their knowledge on this OpenFOAM activities so that they can develop their career in the CFD. So that is the main motto for promoting this workshop. So and once we got the approval, and Madam has enhanced this to next level by inviting all the CFD enthusiasts from the national and international level. I'm very happy to see the lectures provided from the morning session to till evening. So everyone has given their maximum inputs to our students, and around 30 plus students have participated in this workshop. And everyone was very happy with the presentation and the hands-on experiences given. And at the last, the lecture by Professor Chandan Bose has immensely inspired our students. So because of that, this workshop is very fruitful. Thank you. Thank you to one and all once again.
Thank you so much, Professor Juluru. So I can see that some of the people are some of the participants are asking about certificates. So let me clarify that for this one-day workshop, we don't award any certification. We give certificates when we do a longer duration workshops, like 4 to 5 days workshop. Then actually the actual learning happens. So today it was just an initialization session. You just got to know how to use or how to learn OpenFOAM. We just gave you an introduction kind of thing. So this one-day workshop is not, we don't consider it to be certified that you have learned anything. So to give to actually, if you want certification, please submit a case study or a research migration project. Okay. So any more questions? We just have a couple of more minutes. Otherwise, we'll end the session. It's almost 5:30.
Difference between case study and research migration project.
Yeah, cases are small problems of CFD that is solved using OpenFOAM, and the research migration project is once somebody is referring to a research problem which is already been published in any renowned journal, that research problem is referred to and replicated using OpenFOAM. That is research migration project. It is basically one level higher as compared to the case study project. So case studies are for beginners, I should say, and research migration is more applicable or effective for the people who are doing PhD or research work. Oh yes, so thanks, Evan. So please note down the email ID. Our email ID is contact hyphen all in small contact hyphen cfd@fossee.in.
Madam, if required any HPC facility, can you get it from the research project? Research migration project, if you need any HPC sort of things.
No, we don't support that.
Okay, that you have to say no.
Yeah.
Ma'am, can you please repeat?
This program will be welcome to international. Yes, it is. It is. International students also can apply. Yes, somebody else was asking any question.
Ma'am, can you please repeat the mail ID?
Yeah, so it is there in the chat box. I'll just type it once more. Just refer to what Ivan has typed. Contact, CONTACT, contact hyphen CFD@fossee.in. It's there in our website also, cfd.fossee.in. So all the information are here, our email ID, our resources. So, and after this workshop, we will get back to you with more resources that you can refer to, and you can gain expertise in OpenFOAM. Okay, so thank you all for joining. We will close the session today. Thanks a lot to my team members and Professor Janani and Professor Chandan. So with that, one more question. If selected, I can get scholarship for on-site. No, you cannot get. Sorry, that facility is not there. Okay. Yeah, thank you. Thank you, everyone. And namaste and Jai Hind. Bye-bye.
Thank you, everyone.